Good morning, ladies and gentlemen. May I have your attention, please? So, on behalf of Leadvent Group, let me welcome you on our second day of the conference. And same as yesterday, I'm just going to share a couple of organizational remarks with you. All the coffee breaks will be held same place as yesterday, meaning in the foyer. For the lunch, we will go downstairs as yesterday. Also, please let me remind you to fill in the evaluation forms to rate our speakers. And as I mentioned, the link with the presentations, you will receive 1 week after the conference, so during the next week. Now, without further ado, let me welcome our chairman, same as yesterday, Mr. Andrew Billingsley. Andrew, the floor is yours. Thank you. Enjoy the conference.
Thank you, Teresa. Good morning, everyone, and welcome back. Yesterday gave us a clear message. The scale of what is coming is huge. The gap in today's systems are real, and the sector is finally ready to talk about them honestly. We heard operational truth, not theory. We heard where the bottlenecks are, but where the opportunities sit and what scalable actually means. Today is where we turn that clarity into direction and build off day one. We've exposed the problem, and now today we need to start shaping that blueprint. The standards, the partnerships, the technologies need to be developed, and the operational models that will define how we scale in time. So let's not lose the momentum of yesterday. Let's pick up on it. Let's stay practical and ambitious and keep thinking in systems. Keep thinking collaboration. Let's get started. So without further ado, it's my pleasure to welcome Dr. Pierre Gérard to the stage. He's a senior expert in composites and head of recycling programs at Arkema.
Thank you, Mr. Chairman, and good morning, everyone. I have a little bit the pressure to keep you wake up for during this morning presentation. And I would like to thank also all the organizers for giving me the opportunity to present closed-loop solution for what we name thermoplastic wind blade recycling, mainly through what we name the ZEBRA project. ZEBRA meaning Zero Waste Blade Research. Indeed, this ZEBRA project is a joint strategic and cross-sectoral consortium. So a group of industrial companies I joined both together to develop what we name and to at the end of the program to manufacture two full-length blades of more than 60 meters, what we name a blade ZEBRA 1 full glass and the blade ZEBRA 2, which include also a carbon spar cap, with the goal to eco-design and to have the ability to fully demonstrate the closed loop of recycling with this new solution, and to further develop this circularity by developing some new materials. So this project was shared between different work packages. So the first work package linked to the material and subcomponent validation and mechanical and process trials. It was mainly led by Arkema for the development of what we name our helium resin, which is a new liquid thermoplastic acrylic resin. And the goal is to substitute some standard thermoset used for the manufacturing of a blade. That could be epoxy or polyester that we discussed yesterday. Bostik, it's a subsidiary of Arkema, and we develop metacrylic structural adhesive that fit for structural bonding with the nature of the helium resin, but also in terms of eco-design, same chemistry. That means that will also help us in terms of recycling. Owens Corning, who developed some new ultra blade fabric for the manufacture of the blade, and I guess Alessandro is there in the room. So if you have some specific question, please ask him during the break on Canoë, which is a technological platform located in the southwest of France, where I am located, and which help us to develop and to manufacture some the process on some coupon material for characterization. For the work package 2, it was managed by LM Wind Power. It was based on all the raw material that has been developed in the work package 1 to be able to design the blade and just to assess, compared to a standard blade, what is the modification that we need to take into account in order to manufacture the prototype blade that will be realized in this work package 3. And then the work package 4 was based on a process optimization, mainly infusion process on automation. It was led by IRT Jules Verne. IRT is an Institute of Research and Technology, and they also manage this ZEBRAS program. But I will not disclose any result from this work package 4 in this presentation. On the work package 5, managed by Suez, and also Ronan is there and in this room. So again, if you have some specific, so Suez is a recycling company. So if you have any specific question raised to your mind for Ronan, please ask him during the break. Sorry. So this work package 5 intends to manage what we name the post-industrial recycling by managing the recycling of the manufacturing waste for that, and also to consider, okay, unfortunately, it will not occur before 20 years for this new solution, but the end-of-life management that we name the post-consumer recycling. And finally, because it's very important for us as well to assess the technico-economic and environmental of this solution. So it has been managed by ENGIE to carry out such a study in this work package 6. So now in the work package 1, again, it was mainly devoted for the development of what we name our helium resin, okay, which is now familiar with all the wind community, because we intend to develop this resin a few years ago now. So helium, as I already mentioned, is a liquid acrylic thermoplastic resin that can be processed like traditional thermoset resin. But the main value proposition is a full recyclability through a circular loop, and we intend to demonstrate that at a full scale through this ZEBRAS program. Fast room temperature polymerization. Indeed, we do not need any heated mold. That means that we could have some benefit in terms of energy consumption on cycle time reduction, and also to have some high mechanical performances. Okay, similar to epoxy for the static properties, and we could have also some higher properties, mainly from dynamic properties like damage tolerance, toughness, and also damping properties. So at the end of this work package 1, we confirm the technical feasibility and maturity of this new system, new resin, thermoplastic resin for the wind blade manufacturing across some infusion of the two shells on the shear web, infusion and repair of the blade, and also a pultrusion process for the development of carbon spar cap by pultrusion that has been added in the second ZEBRAS blade. So overall, work package 1 demonstrates strong progress toward the deployable thermoplastic blade technology with key building blocks validated on clear pathways identified for final industrial optimization. So for the work package 2 and work package 3, managed by LM Wind Power, if I start to focus on the work package 2, so 2 LM Wind Power blade design was selected, 162.2 glass blade on 177.4 metal lengths, carbons per blade. So LM validate different blade 1 and blade 2 with quite a good success. And successful fabrication of these two blades. Though the key learning is, okay, infusion is more sensitive compared to epoxy, and we have to adapt the process parameter, but in terms of flow speed and mainly exotherm, we reduce cycle time, but unfortunately we have a little bit much higher exotherm that we have to control, but the resulting quality is very good. MMA bonding from a structural adhesive is feasible. We demonstrate that from these two blades. And post-processing is more demanding because it's a thermoplastic behavior. So we adapt the tool to complete the machining of the blade, and also we improve our helium formulation to be more robust in terms of post-processing. And also, I will show you later on during this presentation that we are able to carry out the recycling and to remanufacture some recycled helium resin again through our closed loop process. And we were able to use this recycled resin for the manufacturing of one of the shear web of this second carbon spar blade within Zebra. That means that it's a first industrial success using recycled helium, which has exactly the same end-use properties as the virgin one. And in terms of testing, so this two blade has been successfully tested on a bench at LM site. What we learn also that to use this new resin, it's compatible with existing LM blade design with only minor modification. We have improved mechanical performances. As we said, okay, in terms of static properties, we are comparable to epoxy. So the process is process of infusion is close to polyester, but the mechanical properties is close to epoxy. We have a potential for mass reduction for 13%, but not validated during this project. And as I said, we have much more higher toughness performances, so more damage tolerance that could be interesting to consider during the operation of the blade on the field, but also some higher structural damping due to this thermoplastic behavior, and we still need to validate these interesting properties just to assess if we could lightweight the blade because we reduce the load applied on the blade, or we increase the lifespan of the blade, and also could we also increase the lifespan of the other component of the turbine, engine and rotor, for instance, due to this higher structural damping of the blade. Now I will focus on the work package 5 led by Suez in terms of waste management and to consider also the end of life of this blade. So that's why we separate by two. We consider the post-industrial waste, so manufacturing waste from the infusion process. So you know as well that during infusion, unfortunately, okay, roughly around 10% of the weight of the infused part was linked to ancillaries and consumables. For instance, vacuum foil, pill ply, release film, infusion, tube, and whatever, and others. So fully thermoplastic. It was mainly based on polyethylene, polypropylene, polyamide, and so on. So all fully filled with the infused resin. Up to now, it was with the thermoset resin, so no way to consider the recycling for such a mixture. But now with helium resin, we are a full thermoplastic manufacturing waste for that. and roughly the average is 50% of the helium resin and 50% of the consumable. We also have some in a bucket some helium resin, some methacrylic adhesive, so same chemistry, some dust, some cutoff of the dry glass fiber, and the leading edge or trailing edge cutoff based on the composite. And for the post-consumer waste, that means the blade at the end of life. Definitely, well, now we have mainly composite material based on the glass fiber for the first blade, both glass fiber and carbon fiber for the second blade, so methacrylate adhesive, so structural adhesive, balsa wood, PET foam core material, and gel coat and paint at the surface of the blade. So now, with our approach of helium resin, we consider two ways for recycling. The first, because it's a thermoplastic material, the first route of recycling is what we name mechanical recycling, but it's an open loop, and with what we name a downcycling, but we could reuse the material. So we have two ways. The first thing, after shredding and grinding the composite part based on helium resin, we could manufacture some flat sheet by compression molding, but we also regrind thermoplastic composite particle in host thermoplastic matrices. So after a compounding step, then we have some new thermoplastic material, and so we could reuse this compound in a thermoplastic processes like injection molding or 3D printing. And we consider now, due again to the thermoplastic behavior, so we consider this waste as a reinforcement and not as a filler, as it has been demonstrated yesterday for thermoset material. More interesting, this is the chemical recycling in a closed loop process. So helium resin, it has been highlighted yesterday by Pascal Gallo from Composite Recycling. Helium resin has more or less the unique properties to be depolymerized through a thermolysis process. So depolymerize means I am able, through the purification of pyrolysis oil, to come back to the monomer. This is the raw material based on the helium formulation. We have a separation of the resin and the fiber. We collect the recycled monomer, and we are able to rebuild recycled helium resin in a closed-loop recycling process. And as we could show here, we are able to show that we divide by 3 the carbon footprint or recycled resin compared to pristine resin by adding up to 95% of recycled content in this formulation. So now we could deliver on the market some recycled helium resin which contain 95% of recycled unit monomer or material on it, and we have so lower carbon footprint for this approach. So now we intend to demonstrate at a full scale this closed loop for recyclability. So for one of the first glass blades, so Suez on Ronan, go on site and cut in small pieces having a length of 4 meter lengths. Cut this first ZBrass blade having a length of 62.2 meter lengths. So by a diamond saw, they cut in here. They cut in parts, and they Ronan shred this blade, collect this blade, or the weight of the blade was around 14 tons. Then we demonstrate at lab scale that unfortunately, we have to carry out the sorting of the different material. So we did that in like a kind of swimming pool by density differences. And indeed, if we soak this shredded particle in a water bath, let's say that the composite, which has a density higher than 1, will go down, and the floating material will be the balsa wood and the PET foam core material. So we are able to carry out the sorting of this material, and finally, after a grinding step, in order to reduce again the size, convenient for the process of recycling, then we collect the composite material, which is a glass on helium resin, which has a purity of around 95%. So we could accept 5% of cross-contamination coming from the remaining balsa wood, PET, foam core material, paint and adhesive and whatever. And then we developed the process of continuous thermolysis chemical recycling with a partner which is a Pirovac, and indeed in this pilot having a capacity of 50 kilogram per hour, we were able to manage the chemical recycling or thermolysis of a feedstock of glass fiber and helium resin. We separate, so Owens Corning recover the reclaimed glass fiber and consider the remelting of this glass fiber, and they are able to deliver the trade name is the Sustainaloop for this glass fiber, recycled glass fiber. And for us, we collect the thermolysis oil. We carry out the purification through a distillation process. We recover the monomer, and we were able, as I said, we were able to remanufacture recycled helium resin that has been used by LM in order to manufacture a shear web of the second carbon spar blade. Now, for the Work Package 6, it's a techno-economic and life cycle analysis of this blade. This analysis has been managed by ENGIE. So this study covers the life cycle stages, so raw materials, transport, manufacturing, waste treatment, dismantling and disposal of the blade, and we compare to a standard blade, standard LM blade. So the main environmental impact, and I'm quite sure that everyone is well aware is in this audience, is unfortunately the virgin materials. So most of the environmental footprint comes from using virgin resin and glass fibers, and now recycling makes a big difference. With this closed-loop recycling of both resin and fiber, we can reduce the CO2 emission by up to 30% per blade. That means the idea is not to manufacture a blade that will be recycled, but to manufacture some blade who already contain 95% of recycling content in the resin, 100% by a mass balance for the glass fabric, and then we could demonstrate that you produce a blade with 1/3 less of carbon footprint compared to a standard one. And in terms of economics, the gains are modest but real, and we have some partial recycling brings some cost saving through they remain limited. But indeed, from a theoretical standpoint, yes, we could have some interest in terms of economics to consider this closed-loop recycling, and we intend to validate with this partnership with composite recycling. So normally, Pascal already shown you during his presentation, and again, if you have some specific question, you could ask him. That we have a promising and circular business model, as mentioned by Pascal yesterday. So composite recycling will collect the recycling fees from different waste streams, and we consider mainly the waste stream for marine application with our charter customer, which is Beneteau, and also some waste stream from a wind blade. It was a Zebra at that time, and we consider also the recycling of post-industrial recycling for manufacturing waste, and also the part at the end of life. And okay, I will just go faster. So Pascal already mentioned this first pilot unit managed by composite recycling, having a capacity of 2 tons per day. And then at the outcome or output of this process, so composite recycling will sell the reclaimed glass fiber to Owens Corning for the management of Sustainaloop process, and will sell the thermolysis oil to Arkema in order for us to collect the recycled monomer. So as a conclusion, I hope that I was able to show you that helium resin, Sustainaloop circular glass on the Zebra project demonstrate that through closed loop recycling of both resin and fiber is now achievable. So the life cycle and techno-economic studies confirm significant benefits, including up to 30% of CO2 reduction per recycled blade, and the first industrial recycling solution, so a thermolysis unit managed by Composite Recycling, monomer recovery, circular glass mass balance are already deployed, proving industrial scalability. And the collaboration between Arkema and Owens Corning accelerates, so integration of high recycled content materials, so as I mentioned, up to 95% of recycled content in our helium resin, and up to 100% circular glass fibers through a mass balance approach certified by ISCC Plus for Sustainaloop, reduction of carbon footprint across the full blade life cycle, and establishment of a viable circular business model for the entire value chain. Thank you for your attention.
Thank you. Yes, good morning. Thank you for the very interesting presentation. You mentioned in one of the first slides that you do gravity separation, you put the shredded material into a water bath. Let me ask you, please, how do you dry this material again, which is soaking wet, especially if you had fillers that were balsa wood and all that would be soaked in water now? How do you dry the material before you further process? And then how you keep the water, you know, the pollutants out there?
So I forgot to mention that the recycling of what we collect of the floating materials, as I said, is balsa wood and PET foam core material. We do not consider the recycling of balsa wood and PET foam core material in the scope of this project, because we understand and we heard to know that we have there's other collaborative program who will deal how to carry out the recycling of balsa wood and PET foam core material from Decomblade program, for instance, and so on. So we do not consider that within the ZEBRAS program. What we consider is the recycling of composite material, glass fiber, and helium resin, which quite hydrophobic. So correct me if I'm wrong, Ronan, but we do not dry this ground composite particles. And helium is robust enough in order to accept a given level of water in the formulation.
Thank you.
Thank you very much. When will be standard blades available?
When some OEM will manufacture helium blade, and we could, okay, you know, situation. The idea, no one from LM is in the room, so the idea for MLM is, okay, to the next step is to manufacture at least 3 blades to install on turbine and to fly and to validate what I said.
Yep.
In terms of an end of life, it was only tested on the bench. Unfortunately, the situation last year for all the industry was quite tricky and complicated. The situation for wind market is complicated last year.
I know.
The situation for LM is also complicated. So unfortunately, they do not consider to the pursuit of this program. But now we have a partner who actually intend to produce numerous of helium blade that will be installed in North America in a specific turbine. And we could give you the right contact if you are interested. Yeah.
Thank you very much.
Yeah. My question would be, have you ever made a study on how to scale it and what it takes actually as an investment? Because what we see is that none of the Savolysis projects are being built because of the initial high investment cost. And we have been approached by the developers of the epoxy resin system who produce for the Siemens blades, if we can actually process those blades in the future, because they don't see that anybody is investing in actually building a big Savolysis.
Yes, very good question, and I completely share your point. Moreover, you mentioned solvolysis, and in our case, it's not a solvolysis process. So I confirm that, forget it, for solvolysis, from our standpoint, it will not be scalable at industrial scale. And unfortunately, we have unfortunately a lot of examples showing that okay, it could work at lab scale, but to manage solvolysis industrial scale, it doesn't make sense in terms of industrial standpoint. What we mentioned here, it's a thermolysis or pyrolysis process. So composite recycling is there in order to validate. They are the first unit. Is it profitable or not? We will learn from, I don't know if Pascal is there, we will learn from them, we will, and we will see, we will have the real number on that. But also for the pyrolysis of a wind blade, Genkraft, for instance, we mentioned, I don't know who mentioned Correc yesterday, also Acciona has built some plant facilities to consider the pyrolysis. But for thermoset materials, mainly epoxy, the only value is on the fiber. If you consider carbon for pyrolysis, yes. You couldn't valorize the oil for epoxy or the oil for polyester, for now. The main value that we bring is we share the industrial risk because we have some value on the fiber and value of the oil from the resin that we develop.
Yeah, Pierre. Thanks for the presentation. I have a question about the materials. If I understood it right, there's a little bit of thermoset material in it. For bonding, you're using MMA.
Yeah, but it's thermoplastic.
It's also thermoplastic, so okay. Yeah, oh yeah, correct.
It's MMA based,
Yeah.
same nature, same chemical nature.
Okay, is it also possible to weld
Yep.
the parts together?
Yes.
Because now you're using MMA as a bonding material. Was it also a topic in this project, or?
Not in this project, but we have other project in mind. And please discuss with Dirk, formerly working at Pontis.
Okay.
At Pontis, and you know, Pontis is our. We do not intend to develop the welding by ourselves. We need some specialists, and Pontis is one of them. And they were able to weld a helium beam. It's a demonstrator having a length of 4 meter length with resisting welding. So it's already done, and we have still development ongoing.
Yeah. What is the melting temperature?
It's not a melting temperature because helium fully polymerized, it's amorphous resin, but
Okay.
what we name a glass transition, it doesn't matter.
Yeah.
The glass transition is around 110, that means you have to heat at 150 up to 180 in order to fully melt the process.
Okay.
The main issue for wind blade is the bond line and the gap to consider, but for the spar cap, to weld that, this is what has been considered by Pontis, but with an OEM. So please contact them and discuss with them.
Okay. Thank you.
Thank you, Dr. Pierre. It's been oh, excuse me, one more question. Sorry.
Hello, Pierre. Thanks also for your presentation. It's funny that we are here together because you mentioned already Pontis. You mentioned LM. And to be more specific, Dirk-Jan and Pontis connected me at LM Wind Power. I was responsible for a CPO for all materials and new materials. So we did see this as a unique selling point. However, due to a cost increase, it's not easy to implement this. And it's all about shareholders' money and is the customer like RWE or where else willing to pay for the cost increase? So we said we're going to do this. It took some energy in the management to get this realized. That we said, yeah, we choose for your product because we didn't know as LM this is the future. That means we can recycle the blades. That was the main reason. But who's going to pay it was a different point because our blades were more expensive. Then you get an issue in the market because your blade's getting more expensive, you're getting less competitive. But in the end, we did it. And I think now we are at the phase, who is paying to make it possible to grind or to reuse all these blades. And that's the main question. Who's going to pay for it? Is it the price? Do we increase the price in the blade? Or do we say the owner of the park has to invest in granulates, paralyzers, etc.? And this is already since 8 years the question. Only nobody comes back with, yes, we understand it. We should make it possible to recycle blades on a large scale, but nobody is saying, yes, we will pay this.
No, I completely share your point, yes.
Yeah, so the next 5 or 10 years, we have the same situation.
I think RWE should pay. What? I think RWE should pay.
Yeah, so that, yeah, they are the ultimate owner of the park, so yeah, you can say that.
Saying that, but why it's important, and it was mentioned yesterday, we need to have some collaborative program for that.
Yes.
The idea is now we have enough data to establish the value chain from the building of the blade up to the end of the life, and to see where is the value chain on that, and is it at that time with this scale, is it profitable or not? To have a rough, right number on that. On how we have to go further if, unfortunately, if we collect all the value chain for the different actors, unfortunately, it will not be profitable in terms of business. Then we'll have to have some incentive from policymaker or whatever in order to force to use this approach. Or to be obliged, like automotive, to reincorporate in the blade a given amount of recycled material. This is what we discussed with John Carlo yesterday, but to be sure that we will be able to do that. Okay.
Thank you very much. This is a tremendous debate. There's a lot more to be discussed on that, and we need a lot more time, and I think we can go a long way with that. It's a great pleasure here now to bring on Reinhard Kessing, who is going to talk to us about the technologies and solution that his company, Kescon, has.
Yes, good morning, everybody. I hope everybody is awake, and I'm a little bit more old-fashioned. I'm not a good speaker, I must admit. As you can see with the many colors, it's a different generation, but some of you may have seen some of the samples out there. I have started back in, I need to go back here. Let's see how that works, back in 1990, some of you may have not even been born then, to recycle the non-recyclables. So it's really an interesting journey, I'd like to say. The other thing, before I forget, I want to thank Leadvent for organizing these events. That's a very good platform, I think. I want to thank Andrew for being our chair. Great job so far. So let me dive in. You may find some of these slides slightly provocative, and that's the idea. I want to make sure that we all recognize what can be done already, and we have living proof here. I will go to that into the details a little bit later. So the short introduction, as you can see, since 2003, it was really, focusing on recycling the, into high-value end products. Let's see. The next one goes to here. Maybe not. I think it's stuck. I went back. But no, I don't want to go back. I want to go forward now. The big one. But look. Sorry. Aha. All right. Thank you. So, we have recently formed a new alliance, and this is between Kescon and SimpleCamp. And I think some of you may know SimpleCamp. They are undisputed one of the world leaders in the composite panels industry. They're a machinery and equipment manufacturer, just like in their own capacity, Diefenbacher, who is also here. I'm honored to have both companies here. They wouldn't be here if I wouldn't be here. So if you have questions or doubts that, what I'm presenting here today is only talk and no substance, please do, consult with these people here. Let me get my glasses on here so I can. So, I'm not going to read everything, but please do, you get the idea of where we're coming from. First of all, it's super important that we understand that the technology is profitable, and it recycles 100% of all the plants, of all the blades. The plant sizes are capacity 50 to 120 tons per day. We're not talking kilos, we're talking tons. So this is something, and I want to make sure that we all let this sink in. The history, I'm not going to spend much time on it. We all know that there are no really sustainable solutions. It's something we all know. So the majority are still sent to landfill or co-processed in cement kilns. Whoever has been here yesterday, they know what I think about cement kiln processing. It's not the right way. We are delivering a solution that has the potential to significantly reduce CO2, because in our process, per ton, we are emitting between, and that depends on the energy source, between 150 to 300 kilos of CO2 compared to if you have a virgin material, it's like 3.5 tons per ton. So it is a very friendly process. Now, this was the theme, Tomorrow Has Arrived. Forgive me for this old-fashioned presentation, but I want to get your attention. The technology is proven industrial scale ready. It recycles all wind turbine blades, all contents, all brands, all vintages, and everything and all profitable. Now, let's make sure that it sinks in. So I'm going to be a little bit obnoxious. 4 more times. Our process and technology allows us to recycle all contents of the wind blades. Of course, we can also do industrial waste and many other things, but the theme of this forum is wind blades. So let's talk about wind blades. All contents ever made. The next one, all brands, all vintages. It doesn't matter. Our process is so forgiving that we can handle all the blades and all the vintages. The process is environmentally friendly. We have no stack, no air emissions, no CO2 produced in the factory. We have no dryer. That's, the steam, the whatever vapor coming out. We have no VOCs, no HAPs, no NOx. We have no combustion on site. There is no flame, no oil, no gas, no flame. The energy source, our preferred one, depending on the location, is of course 100% green electricity. And that's the one that determines our carbon footprint. Are we getting, a green electricity 100%, or is it a mixture? No dust emissions. We have all the machines from entering into the system are equipped with 100% encapsulated filtration systems, Class H. What does Class H mean? It's 0.5 milligrams per norm cubic meter of exhaust gas. That is the highest or the most stringent you can get. You can actually handle asbestos in these kind of filtration systems. We have no wastewater. All right. Our process and technology is profitable because we are transforming under one roof
the recovered recycled materials into valuable high-quality end products. You saw maybe some of the samples out there. Under one roof. We take in blades, transport length, whatever they are, and out comes a finished product, laminated, as you see out there, depending on what people want. Which other technology and process can do the same? Which technology can make check marks on all these things? Now, I know we need to cooperate and collaborate, but I just wanted to give you an idea that if somebody wanted to, we can do it today. We get into why haven't we been successful so far, but we fully recognize and appreciate very much many things that we have learned during this session already, the other technologies. However, that all these, we have learned that all other technologies have their shortcomings. None of them can tick off the 5 boxes that we mentioned simultaneously. And I think that's important. A to A will never happen. I think this is a pipe dream where people say, well, we need to take down an end-of-life wind blade, and from that material, we recycle and we make a new wind blade. It's never going to happen. Forget it. It's never going to happen. And the other thing is, as soon as you bring that blade down, you cut it into transport length, what I call it. Some people call them, 10 meters long, 8 meters, 4 meters. You lose your fiber length, and I don't care what process you have, you will not be able to make a new blade from that material. I think that's, but what happens to the blades that are already out there for 25, 30 years in some cases? We cannot ignore those volumes. I know people are working on so-called recyclable blades now, but what do we do with all the quantities that, I'd like to say almost millions of tons worldwide that are there? We cannot ignore them. Ignore them. So we need to do something with those. And this is where we come in, really, what we need to do. Now, our solution, in addition to our original OEM supplier, that was Diefenbacher. Like I said, I'm proud and happy they're here today. Thank you. We have teamed up with the SimpleCam Group, and there's a good reason for it. They're now our new preferred partner and supplier of the plant-wide machinery and equipment package. Why is it a very important milestone? Previously, we had been doing all these testings and, I should say sample panels, pre-production, on a laboratory scale, 400 by 600 millimeter or 40 by 60 centimeters, because of, there was no full-size, industrial-size press. And some of you may know the history of Continuum, which I co-founded many years ago. One of their investing groups, they said, Reinhard, this sounds great. Your samples look wonderful, but who guarantees that you can produce these on a full-scale basis? And this is the big step we were able to do with working with SimpleCam, because as you can see in that picture on the bottom right, they have a full-size press in there. I don't even want to call it a laboratory. This is such a huge laboratory. That press is 1.4 meters wide. The net product width is 4 feet or 1,250 millimeter. The heat platen alone is 16 point some meters long. And that press is capable of doing 50 cubic meters a day, which is equivalent to 62.5 tons. It's there. You can go there, you can touch it, you can feel it. That's what we're producing on now. So the argument, you're still in lab phase, that's no longer valid. We are industrial ready, thanks to SimpleCam. I have to give them credit for that. All right? So, next, it's basically a repetition. There's the press. That's me on the right there. You see my hair doesn't get any better, but so we're ready to go if somebody is ready to partner with that. So just a little bit of timeline, what happened when. I don't want to bore you with all these, like I said, in it actually started before this, but this is the rough timeline of what happened when. So I'm not doing this since yesterday, not since a year, but it's decades. I have, how should I say, contributed my life to this. It's been a vision. It's been a very costly venture. So obviously we are very much interested in getting this located, or I should say launched and off the ground. Again, just a little bit of history. That's me when I was young too, once. But I have started with recycling wood. It went to other materials. I mean, it's been a long journey. Back then, 25 years ago, people asked me, Reinhard, why are you in recycling? Who's interested in recycling? Who needs it? Well, I think things have changed, and I think we're on the right track, that's for sure. So, we have had our products tested independently, LCAs, of course, but also weathering tests. And one of our fiercest competitors really in the high-density panels is the so-called compact panel, which people use for flooring. They use it for building siding. Those are between 40 and 80 layers of impregnated paper, or I should say cardboard if you want, but thin. And they are phenolic resin impregnated, and they were fused together. It's a wonderful product. It's very stable. They put decorative forms on top and bottom. Our product, which is made from 100% recycled, outperforms that compact panel at less than half the cost in production. And I think, this is worth mentioning, and I'm very proud of that. Let's see. Yeah, the process of this plant, of course, I can't show you all the details, but like I said, this is ready to go, and I'm sure you understand that we cannot show you all the details, but the end products are there. You can touch them, feel them, smell them. That again is the press, just in very rough steps, what is happening, how do we do it, and it's a clean process, actually. The plant would employ about 70 people, 70, in a 3-shift rotating system. So we're ready to go. Now, end products. This is a hot topic. What are we using these for? The modern kitchen tables, they used to be in the old days, 30 millimeter, 35 millimeter wood-based panels, and if there was water seeping in somewhere, they would deteriorate. Now look at the top left. These are the modern kitchen tables. They're 16, 17 millimeters thick, high density and waterproof. Boom. Who does not need a kitchen table which is waterproof? Outdoor furniture. Who doesn't need it on their terrace, on their balcony? On the bottom left, this is actually Amsterdam Airport. These are furniture for flight passengers. I mean, indestructible. There's a steel frame underneath, but the surfaces are basically indestructible. Doors. Who doesn't need a door? In the United States, I made some tests with a 32 millimeter thick board. I had a guy who had a 9 millimeter Colt revolver. Boom, boom. Couldn't penetrate it. So this is really good material. This is tough. This is strong. It's amazing. And then, last but not least, the facade panels. We can do all of these. From there to there. Now, who doesn't need nowadays, unless you live in the desert, who doesn't need a flood-proof building material when you're home, when your basement floods? Later on, you go with a high-pressure washer and you wash it out, and boom, you're good to go again. Some of the mechanical properties, you'll have those, I'm sure. Some of you may be interested, take some photos, and it is incredible what this product can do, absolutely. So, commercial summary, return of investment, 100 cubic meters a day, that's 120 tons, more or less, approximately 4.5 years. That's not bad for industry. 4.5 years, return of investment. Yes, CapEx is high, but it doesn't matter. As long as you can do this ROI under 5 years, you're good. The smaller plant, because you need the same kind of manpower, but so your ratio goes out a little bit, is about 5 years. So you add 6 months to the return of investment. Opportunities for equity financing, venture capital investment are there. Technology licenses can be offered for a number of countries. So with this new, how should I say, partnership, we can offer plants in this range from 50 to 100 cubic meters a day, which equals 60 to 120 tons per day, right? Which other technology can process or claim the same? I'm sorry, I know I'm being obnoxious, but I think it's important that we talk about these things. You know, I appreciate so much. It's fantastic what people do. We've tried this and we tried this, and how many people say, oh no, we cannot recycle that part. No, we cannot. No, we don't touch that. That's not recycling. If you recycle, you better address the whole problem. Don't take only little bits and pieces. Take the whole thing. We sort out ferrous metals, non-ferrous metals. We separate carbon fiber because it's way too good for our process. We give that to people that are specializing in reprocessing carbon fibers. The rest stays in our material mix. This is interesting. So, do you have any questions? We have the answers. Yes. Thank you.
Eerst? Jij. Goedemorgen. Good morning. Thank you for this most interesting presentation. My name is Harold van der Meijer from TNO. I think I have to skip my presentation because this is the perfect solution. Just a question, because for the highest value out of the blade, you said that you sell the carbon fiber. I'm interested, how do you separate these spar caps? And you see now the latest blades have more complex combinations?
After the first, our process is going through a shredding, pre-shredding. Actually, we start with compressing. We're shredding in the first stage. And after every stage, we're separating out things. And the carbon fiber, they come out when the pieces are about, this size, okay? And with all the systems we have tested and tried, the optical one is the most sufficient one or effective one. We have tried many other things, but optical was the best one. So,
thanks.
Yeah.
You shred it, you don't keep it as...
Like I said, you know, we do not take the blade and then specifically cut out the spar or something. No. Absolutely not. We're taking the whole section, we put it into the first machine, and it starts, the first machine puts out pieces, they're about, I call them pizza size. Not the real big one, but pizza size. The next one, and then we're already, you know, there's some big magnets to get some big bulky ferrous metals out. And then it goes step by step by step by step. And after each step, there are separation processes. We do wind separation or, you know, gravity separation too. But there is ferrous metal removal. We have eddy current separators for the non-ferrous, like copper, aluminum, and so forth. And it goes on and on and on. Our material mix, as you can see on the bags that are hanging out there, we're accepting anything less than 1.5 millimeter. And it's so super clean, it is amazing. And please remember, in that mix, all the fillers, I don't care if it was balsa wood, if it was PUR foam, if it was anything else, is still in there. Yes.
Yes, next question. Thank you for your presentation, very nice. I've seen your factory once during the IJsengießerij. Very impressive. You mentioned the core point, we are profitable.
Yes.
How do you get profitable if you have to recycle blades only? Because the main cost is to get the blade out of the site to your facility.
No.
Unless you cut them up in parts and then transport them to your area.
Yeah.
But then still, it costs you money to recycle them.
Yeah, of course.
Unless your end product, what you're selling, is giving you the margins.
Yes, absolutely. So let me tell you this. Our business model starts at our gate. See, I don't care which route a decommissioned blade goes. Does it go to Solvolysis? Does it go to the cement kilns? It has to be brought down. It has to be cut to transport size, and it has to be brought to XYZ. In this case, to our gate. So we don't want to get involved in all the logistics, in all the cost, in all the headaches of transporting to our gate. Our business model starts at the gate. Very clean. The other thing I mentioned in the very first sentence, I hope I did, we're making from this waste material under one roof, not only we're doing the separation, the cleaning and everything, which is costly, no question, but we're creating such a high value end product that really return of investment, and I had this done by so many CPAs and different sources, and they said, Reinhard, you're really conservative, you know. So it's a combination of both, yet our end product is still very competitive to virgin. So it's a win-win, really, yeah.
That's really fantastic. That means
Yeah,
also, I work with RWE for having a pilot on such a project, making a factory in south and north of Europe for RWE. They had a fund to do this. In the end, I worked with Demac, but in fact, you are the better version of that company, I would say, having already a finished product into your recycling process.
Yes.
So I think this is the moment also for the developers, and luckily you have one in the room here, a very good one and a big one, to look at the possibility to take all blades of them into your machines and making an end product.
Yes.
The end product what you now have is maybe too small to get all the blades recycled and use these for new products. So you should look at a product what is consuming a lot of recycled material.
Yes.
If you have that one, you're the winner of this event, of the year, I would say.
That's right, yeah.
Thank you. Yeah?
I mean, we are new here with the recycling of the wind blades as Simplecamp, but we are very much in the wood-based panel industry. And RWE is IKEA for us in our world.
Yeah.
And IKEA is demanding, let's say, just to give a synonym here, as you're here, but IKEA is demanding from our customers who are board producers to have in a particle board we're sitting at, to have at least 50% share of recycling material. Otherwise, they don't take it. Meaning there's collection of your old furniture being brought to the factories. And this is what is, for us, a standard in our industry. And I just followed here. It was for me the first time. I just want to see who are these guys here and what is the industry about, to get a feeling. Is there anyone who takes the responsibility at the end of the day to make out of it a profitable business? And what we are doing here with Reinhard or with Kescon is, at the end of the day, to produce an engineered product. So we re-mill it, we bring it back to its, let's say, original, and then produce something which is scalable, which is repeatable. And I think this is important, and this is something to think about for you here in this room. And we would be there to deliver the machinery. I think, Reinhard, what you have seen, we call it R&D center, what we have there in Krefeld with this press, with this continuous one. But I think this is interesting. You have to scale it up, and you have to bring it to industrial scale to make it profitable at the end of the day. And for us, 50 cubic meter or 50 ton per day is basically nothing. We are talking about plants which do 1,000 cubic meter, 2,000 or 3,000 cubic meter. So I've built a plant now in Luxembourg, which is collecting in a radius of 200 kilometers, Luxembourg, our area, North Rhine-Westphalia, up to Paris, the waste material stream, converting it either to panels or converting it to electricity. And this is what we're doing. I think this is important for you to think in this way of scale.
Yeah.
My comment, what I learned here, at least in this one day and a little bit of today.
All right. One thing I'd like to mention too, the end product that we're producing that you see out there, we will take it back after end of life, and we can recycle that over and over and over again. Absolutely no question, no problem. I think that's worth something too.
Yeah.
More questions?
Yes.
Yeah, thanks for your story. I'm sold. And I would like to ask two things. First of all, what is the size of the pieces that you can feed into the machine? So you said you accept them at the gate at transport size, but is that also the size that goes in? And if you have an end product that you sell and you take in, is there sort of you are selling it to companies and actively taking it back?
Okay, the first question, the current in-feed, the first machine at the process is taking up to 8 meters long and 2.3, 2.4 meters wide, something in that range. But we have in the background a much larger machine. My ultimate goal is to have a machine that takes a full-size blade on a long conveyor. You put it there with a portal crane and then it continuously feeds into a slow rotating pre-shredder. Actually, it starts squishing the material first, let the air out, I call it. So that's my ultimate goal. But, you know, in order to justify that machine, we need to start with a smaller plant, and that was one of the things that Continuum did not do well. They wanted to start with a bigger plant, and it was like 100 and some millions, and it was too much. And the investor said, no. For a first plant, that's too much. So, but we have, the drawings are ready. We just need to, you know, say, yeah, we'll do it. So 8 meters by 2.4, that's the current transport length we can take without further cutting. We don't want to cut anything on our property. Not at all. Let others do that.
Yeah.
Transport it, bring it to our gate.
It's clear. And for the product, do you actively sell it yourself, or is there like a...
No. This would go through distributions. We're talking to the Nemo Trespass, to the Fundermaxes, to the guys that make these outdoor furnitures, to the kitchen manufacturers, and they're really eager to take that product into their product line and market it under their brand. No, we don't want to go into distribution. That's no. We have the technology. We can offer the plans. We need the investors that have the guts to say, oh boy, this is fine. And I'm sure we're ready to give industry standard guarantees for the whole process because it's been tested over and over and over and over again. You know, I made panels in North America, in Italy, in Germany, everywhere, and it's repeatable or repetible. You know.
Okay, great. Let's talk more in the break.
Yeah.
Very nice. Thanks. I would have a question. I mean, you know, I like very much your approach, and somehow we are working in the same area. You mentioned the distribution. My question would be today, what is the demand, realistic demand for this product? And what can we do to expand the demand? Because this is the key barrier today for closing the loop. And of course, the different big companies can be looking at supplying blades, but transforming a blade into a granulate and into a panel without a market is not meaningful.
Yeah.
So what is your perception of the demand?
First of all, unfortunately, there are many different models about blade availability. I mean, yesterday I saw one where Wind Europe said there's only 3,650 tons available. I think that number is way too low. I have other models which show 12,000 tons already. Remember, on an annual basis, this small plant that we're offering, the smallest, will do 18,000 tons per annum. The bigger one, twice, 36,000, right? What was the second part of the question?
Demand side, how to activate the demand more sustainably, constantly, and...
The interesting part was that, for instance, the building facade manufacturers, both I mentioned, Fundermax and also the Nemo Trespa here from the Netherlands, they said, why is your plant so small? I mean, we put this product in our product line and it's not even making 5% of our total turnover. So they want bigger plants. Why do we limit the plants to the size we're offering right now? If you go smaller, and I had people from Portugal, they wanted 10 tons a day. I cannot make a business model work with a smaller capacity than 50. Just doesn't work. Sorry, we've done models back and forth. Why don't we go over 100 tons a day? Now logistics come in, because although I'm not, like I said, we don't care about everything that happens to our front gate, but if you have a plant that is producing 500 tons a day, you need to ship that material over distances, and it makes it not feasible. So it's much better to have smaller plants and strategically put one in northern, or in Denmark, one in middle of Germany, and one in the Netherlands. That makes a whole lot of sense. And all the models, and we have a lot of them. We're working with Wind Europe and many others, in the UK, in Ireland, Scotland, everywhere. Their models show much higher numbers. So right now, if somebody says, yep, we want to build a plant, we fire a purchase order to the supplier, they need 12 months to build the machinery and equipment, because I can't, unfortunately, I tried already to say, can I not have that press that we're already operating? They said, no, that's not for sale. So 12 months is the lead time. In the meantime, you prepare the property, the construction of the buildings and whatnot, or put it into an existing building. So in another year from today, which would be the earliest, I think we have enough capacity. Of course, then we have a ramp-up curve. We are in the business model very realistic. We're not saying, okay, plant is installed, and 2 months later we're at 100% production output. Not a chance. No. We have a very realistic ramp-up curve, which takes about 6 months to go from first panel inside the plant to full production, because there's a lot of things that have to be, synchronized and coordinated and so forth. But the plant itself is based on technology-wise and control, and the quality control measures inside the plant are enormous. I mean, we measure real-time density, weights, everything, as far as keeping and maintaining a constant quality of the end product. That's where our wood-based panel background kicks in, which is now industry standard. We're putting the same type of technology in this type of production plant. Yep.
Reinhard, I think there's one more question now. We're running quite beyond time now. Yes, yep. Just a brief question
thank
here,
you.
please.
You mentioned 100% recycled product, but if I look at your product, there's a binder that's keeping the shredded material together. What binder do you use, and how is it?
PMDI.
And that's also recycled?
No. Okay. But we are recycling, I'm recycling 100% of the blade.
Okay.
Okay?
Clear.
Yeah, I need, but only 8%. Yesterday I heard somebody said, we need 60% resin or something. So 8% now, for those that work with PMDI or isocyanate, they say, geez, that's a high percentage. But yeah, we have made panels with less, but to get these bulletproof mechanical properties, 8% is perfect.
Yeah. And then a follow-up question on that. You mentioned that your energy source is the main sort of driver of your CO2 footprint. In my opinion, it's usually the sort of oil-derived binder, actually, the PMDI that you're using. That's the main driver of the CO2 or the LCA. How is that?
Yeah, that's part of it. That's part of it. I mean, we have we're working with BASF on a green, or more sustainable PMDI. Huntsman is working on it. So there are several things in the process, but that's out of our control, I must admit. At the moment, our LCA, the CO2, is based on the standard PMDIs readily available today, not in the future. Okay?
Thank you.
You're welcome.
Reinhard, thank you very much.
You're very welcome.
A big hand, please. Now, it's absolutely my pleasure to introduce Casper Glenning from Stena. Casper's working very hard. He's dedicated to bring about a tremendous process in collaboration with Vestas. And I'll let him explain everything and show the great progress they've made there.
Thank you for the kind words. My name is Casper Bull. I work at Stena Recycling as a project manager. And today I will introduce the blade circularity solution for you that we have been working on in collaboration with Vestas. And my job in this project is to to ensure the partnerships with the outbound customers and the recyclers of the materials that we get out of our separation process. So this is just a quick agenda. I'll do a quick introduction to Stena Recycling, but I won't bore you too much with that. So we started as a local scrap dealer in the area close to Gothenburg in Sweden. And since then, we've been trying to become a circularity partner for businesses, helping them do circularity and a more sustainable production by handling their waste and recycling their waste. As you can see, we are in 7 different countries in Europe, and we are a total waste management company. So we do all kinds of different waste, and composites are another area that we want to get into. This is a little overview of how the branches are spread out over the different countries. And this is a slide that we often like to bring because it shows where we were and what we are striving to become. So from that scrap dealer in Gothenburg, we have been transitioning towards this circularity partner that can help in innovation projects, try to find solutions for different complex production wastes. And I think especially this project here is a great example of exactly that, and exactly our willingness to go into innovation projects and to invest in solutions that can help the circularity agenda. So just a quick introduction to the project as well. The purpose of the project is to create a solution that allows circularity for epoxy-based turbine blades. And the way we do this is in collaboration with Vestas. So what we want to do and how we want to do it is to utilize each of our different experiences and knowledge within these 2 different industries, combine them together to find a solution that can, through a solvent-based recycling, provide a circular solution for the blades. In terms of the project, back in September 2023, we signed a joint development agreement with Vestas, and Henrik Tede and Leise Marud are the project managers of the project. They strive to ensure progress of the project and do the administrative parts of it, make sure that the work package leaders provide the right progress and also ensure that we have good communication between the steering group that makes all of the decisions and us work package leaders that provides the work. This is kind of the way we view the setup. So we start at the decommissioning side. Then we receive the material at our facility, where we will do some cutting of the material. And then we envision different routes for the recycled material. Some of it we hope to be able to close-loop recycle, so it can go back into new blades. But we are also very aware that some of the materials will not be able to be closed-loop. Here we're looking at, for example, the carbon fibers and the glass fibers. However, it is very important for us that these materials are as high up in the recycling hierarchy as possible, because utilizing the material qualities is important for us, and we would like to try to avoid as much downcycling as possible. And this is kind of the way we view it. So we have seen the 10 R's a few times during this conference, and we've tried to hone in on the recycling part of it, where we see that there are also different levels of recycling. So what we would like to do, of course, is to reach the highest level, as we see it, of course, which is a full circularity of the material, where we have close to zero loss of the material properties. And as I mentioned, it's not possible for all of the materials. Some of the materials will have to go into another process or another industry, and cannot go back to the same high-performing product that is a turbine blade. Just for some background information, we have been working at our facility in Halmstad, which is our biggest recycling plant. It's the place where we have our research and development lab as well, and this is where we have done all of the tests to evaluate the technology and scale up the process. So at this point we are at what we call a test bed, and we view that as a medium step between the lab scale and a pilot plant, and I'll get back to that. This doesn't mean that the pilot plant or an industrial facility will be placed in Halmstad or in Sweden. There will be many different variables that can strategically determine where we will put the plant. For example, it could be decommissioning strategies from different energy companies. It could be close proximity to recycling partners, and so on and so forth. And just to give you a bit of a timeline perspective, we have made this high level draft. It's as you know, it's difficult to really scope when you will be ready with different parts of the project in such a development project. But this is what we envision, and this is what we hope that we will be able to stick to. So in 2026, we believe that we are able to validate the business case, and then also in 2026 kick off with the pilot phase, and then within 1 to 2 years we will have the pilot plant ready, and get even more information about our OPEX and our processes, and optimize those processes so that we can follow the market and try to handle the materials that will be ready in the market at that point. So it's also a question of following the demand of the market and seeing when will the materials be available for the process as well. And then in another 2 to 3 years, we hope that the industrial scale facility will be available. And from that point on, it's a question of looking at where the material is. Can we put up another facility to handle it, and thereby upscale it? So the project status at this point in time, and some of the achievements that we have realized in the project, is that we've produced quite a few different tests. We've tested the technology vigorously in the lab, and at this point we have reached the test bed where we have the process established, and I'll show you some pictures afterwards. We are also at a point where we are talking to many different off-takers of the different materials that will come out of the test bed, and we are in an iterative process of finding solutions for each of these materials. But we are super happy with this first upscale in volumes, and we are very happy with the quality of the material as well, because we are actually exceeding the expectations in terms of contamination and so on. So the next steps will be to further work on these partnerships, to further do the iterative steps of trying to find recycling solutions and work on contamination and so on and so forth. And this right here is our test bed in Halmstad, so it kind of gives you a visual of the scale. This is what it is now, We are not talking tons as you are, Reinhard, but we are talking tens of kilos in this process. So the next step would be the pilot plant, where we are going to hundreds of kilos, and then so on to tons. So there's still a bit of progress, and as you saw in my timeline, it is also 4 or 5 years into the future. But we are very happy with our process so far, and we think that we can really get some good recycled materials out of this. Just to give you an idea of the process steps, then we will have a pre-treatment step before receiving the material, where we will cut the blades into manageable composite blocks. We will cut out the carbon fiber, because that will go to another recycler. And then we will put these composite blocks into our chemical step, where it will be treated and where the solvent will selectively break down the resin and causing this delamination, where we will then have some materials, or the materials that are within the composite, and we will have an epoxy powder. Both parts we will of course recycle. And then the chemicals that are used for this will then be recycled back and used back into a new batch. After this, we will have a separation step, where we will mechanically separate foam or core material. We will separate glass fiber mats and, in some cases, aluminum mesh that is within the blade. And just to reiterate, we've gone from the lab scale of grams to tens of kilos now in the batch production that we are running. And now I just want to show you a short video of the delamination process. And what you see here is a very, very small piece of the blade in a lab scale, and you can see the delamination and each of the layers of glass fiber being available afterwards. This is not from our project, but it's from the CTEC project, which was the predecessor to this project. So we've scaled it up and further developed on this exact technology. And the materials that we get out of it is the ones that you see up here. And what we've then done is, and this is more or less where my job starts, is to look at the different markets for each of these materials. What is the maturity of the markets? Are there any recyclers that can work with these materials when they're coming out of our process? And for the metals, it's easy peasy. We've done that a million times. For the other parts, it's a bit more questionable. And for us, it was very important to make a prioritized list for these materials to see what's most important for us. Of course, we want to recycle all of it, but what are we focusing on? And to do that, we have two measures. One, which is material circularity index, and that's just a nice word for how much or how big a percentage of the blade is being recycled, if you can handle that material. And then the global warming potential, which is how big a reduction in CO2 emissions can you get from recycling this material rather than using virgin materials. And by this, we of course have identified that carbon fiber and glass fiber are very important in terms of it's a big part of the blade, and it's a high energy process to produce the carbon fibers. So looking at the carbon fiber, as I mentioned, we would like to cut it out from the blade before our process. And we have been in discussion with multiple different recyclers at this point. We haven't decided on any specific recycling route because there are many options. But what is important for us and what is a priority is that the recycling solution keeps the material at a high level so that we can use the properties of the carbon fiber. And that is one of the things that we prioritize when we're looking for partners. For the glass fiber, we have also looked at many different options, and we also haven't decided a specific route. There are remelting, there are mechanical recycling where you use it into a new composite material. And one of the problems is that we have some contamination from the epoxy powder in these glass fiber mats. But this is something that we are trying to find solutions for. How can we, oh, I made a mistake there. How can we open the mats and get in between the fibers and get the epoxy powder out? Because that can be a contamination in different recycling solutions. And there are multiple different ways to do this, and I don't want to go into this because I think that's also a secret for the different recyclers. But we have looked at many different options, and it's an iterative process, and it is so for all of the materials. But we are very happy with the partnerships that we are already forming, and we hope to keep forming other partnerships. For the epoxy resin, we have looked at both mechanical recycling, but also chemical and thermal recycling. And again, we have some problems with contaminations. There are a little bit of glass fiber in these epoxy powder, and we also have a fairly high moisture level. But we believe that through the conversations with recyclers that we actually can solve these problems. Of course, adding process steps to these parts will increase the cost, but we are still fairly certain that this is a good way of returning the materials to a high level and to products that can perform at a high level. Regarding the PET core, or the core material, we have actually only focused on the PET foam for now. Of course, there are other core materials like the balsa wood. There are also PVC foams and PU foams, but from our understanding, most of the core material is PET, and therefore that has been our priority in this recycling journey. And for this specific part or product, we have some problems with those lines, so you can see. So these lines here are cured epoxy that our process has difficulties getting to because it's lines that are cut in the PET foam so that it can form to the form of the blade, and it's difficult to get to these. So we're looking at a mechanical separation for this, and yeah, as you can hear, there are many things that still needs to be worked on, but the information that we get from the recyclers that we are working with is that we believe that there is a route for this to become a new product. So to end off with, I just want to mention that we are still looking for partners. We are still looking for off-takers. If you can point anyone in our direction, or if you have any ideas, you are very welcome to talk to me. We believe that it can be a win-win solution. And as a final statement, I just want to say that success starts with collaboration and with these partnerships. And this is something that we see in all of the different innovative projects that we are running in Stena Recycling across the different countries. There are many examples of using the entire value stream together, combining all of the information from the different parts of the industry really helps in the circularity process. So that was it from me.
Thanks a lot. Interesting collaboration. I was wondering, do you only take Vestas blades in the process right now, or other OEMs also acceptable? And what is the size of the pieces that you can feed into the machine once it's developed?
Yeah, so we are still at the test bed. So our capacity is fairly low, which means we don't really need that many blades. So for now, we've worked on Vestas blades, but this can also be applicable to other types of epoxy-based blades. So it's not specific to Vestas in any way. However, the capacity at this point is so that we have only used Vestas material at this point, but it has been tested on other.
But it's not a requirement from the collaboration with Vestas that it is only for them.
It's an industry-wide project, but the partnership project, of course, is with Vestas. And for now, the sizes you can say are kind of like this, so an A4 page more or less. And well, it really depends on the recycling route, whether we go in one direction or another. So depending on what recyclers want in terms of the form factor, we can shred it, we can keep the fiber length, at least at this point, to this length, but in the future, who's to say that the machines won't be bigger and the batch will be able to handle bigger sizes.
What is your ambition for the machine you would like to develop? Is it like 1 by 1 meter pieces or 10 by 10 meter pieces?
Yeah, so I don't really think we have a specific vision for it. It will be a collaboration and an iterative process with recyclers. So it's still up to interpretation, I would say.
Okay, great. Thanks.
Kasper, thank you very much. Excellent presentation, courageous approach, and we would definitely like to partner up because we expect to have granulate over which needs a home, which we can use in our process. My question to you is, when you say epoxy powder, now it's actually a thermoset. You don't break bonds between the epoxy and amine hardeners, so it's a polymer. Where do you try to do you talk to chemical companies? What do they want to do with that thermoset? Where could you possibly use it? Because it doesn't depolymerize like Arkema's Ilium.
Exactly, it doesn't depolymerize, but we are talking to chemical recyclers, and they have, at least it seems like, options for depolymerizing the epoxy powder afterwards. So that's what we're looking to.
The two chemists in the audience would be skeptical. You can't depolymerize. You destroy it. You can pyrolyze it. You can get some monomers back, but that would be the route, and you need scale for that as well. So I think that's a very difficult part of it.
I can't get too much into it because, first of all, I don't know what I'm talking about, and second of all, it's also confidential for the partners that we're working with. So the only thing I can say is that it seems like there's a recycling route for the epoxy powder.
Okay, great, thanks.
Yes. Well, if there are no more questions, thank you for...
Kasper, thank you very much indeed. Incidentally, I will say Kasper's a prime example of what's happened with regards to collaboration, how important it is, and how important it is to have a long vision for what you want to achieve. Thank you very much.
Thank you.
Unfortunately, we were going to be joined today by Cristina Fernandez Alonso from GE Verona. She's messaging to say, due to unforeseen circumstances, she will not be able to be here today, and that's with big regrets. So we move forward now, and I'm pleased to invite to the stage Claudia Martins from Jewel Mine, who's going to present the generational recycling solutions she can offer where every element is considered, solving the challenge for good in this generation. She's got 100% material health of recycling of resources.
Yes, hi. So probably a few of you guys remember me from last year. Do I have to move closer? Yeah, okay. It's a little bit tough when you're taller. So, okay. Yeah, of course, I'm going to introduce you to our approach, and also I want to bring back a little bit also of the thought process, because I think we have seen a lot of good approaches, and in the end, we believe there is not the one approach, but it will be a combination of approaches, because it will also be, it depends, not every not every business model works in every country. So there will probably also be a mix and match of, what works and what doesn't work. Who we are. So we have been founded in 22, end of 22, out of basically with our co-investor and a small consulting company. Yes, so we have set a couple of ambitious targets. So we wanted to do a full material recovery. We wanted to have zero emissions, and we wanted to be completely renewable powered. And obviously, looking from an investor's perspective, we had to be scalable and economically viable, right? So with that, we basically set out, and we also had a lot of ambitious goals and said, like, okay, why does it actually matter? So, obviously, I've been in the wind industry since 2000. So, we want to make it, 100% renewable. And we also believe that it has to do with a lot of responsibility. So if you do a job, do it right? So, and not halfway through, and I think we, here in the room, we are kind of the good guys, let's put it that way, because we are trying, genuinely all finding a good solution. But there's also a dark side in the recycling market, which we cannot really ignore. Nobody has touched upon it. And, but in the end, we still have to solve that things don't go, into the wrong channels. So, hearing about the last, yesterday and today, so I'm sure that as an industry, we are on a good way, and we will find a good solution so that, the other routes are dying out at some point. So, and I think we owe it to the next generation. So we should solve it in this generation and not just push it into the next one. So, because the best thing that we can do is to preserve resources now, right? So, I just give you some of the highlights up front, and then I talk about why we actually choose that way. So we are also building a capacity which will have a 35,000 ton blade capacity per year. So that's, I think, about 120, 140 tons per day, I think. Yeah, Umar is nodding. That's good. He's the engineer. So or one of them. So so that's roughly 140 tons per day as a maximum capacity. And the route that we have chosen for that site is up to 400 tons of clean hydrogen, fuel cell ready. We will also retrieve 23,000 tons of glass, and we will have a syngas, which will be sold to the chemical industry. And the interesting thing is, we have a very high recycling rate. Obviously, we take out all the metals. We take out all the metals, and they will be processed by obviously a metal recycler. But we take it out. So that's basically the minus what you see here, and a couple of other things. When you do product carbon footprint for hydrogen, we have an extremely low product carbon footprint for the hydrogen, which is about 4.8. 10 is the limit for green hydrogen. Unfortunately, we don't have a color because nobody has thought about us when they put in regulations that we exist or could exist. So, so that is something that we are working on. And roughly we will employ around like 35 people. And we are working on the commissioning date in Q4 27. So what do we do? Yeah, it's a bit generic because we cannot, for IP reasons, we cannot go into too many details. But basically, what we also do is we do a mechanical conditioning, and I think here it is where scale is coming in. And we have seen the project of Kescon or Signal Technology. So if you want to have a continuous process, you have to make the material, feedable, and that's a big issue for a lot of the projects, or why things are getting stuck. And so to make it feedable is a key. So because only if you have a continuous process in the end, you can scale it. And what we have also seen in the past is you can try lab scale. We worked with a lot of universities. I can tell you we plugged up a lot of stuff. So sometimes we traveled for 8 hours just to clog everything up in 3 minutes. So we have also found out that basically when you test on a small scale, the loads, everything, it just does not scale very well. So you really have to. So that's when we started to test on real life machines. So. And that works. So then we go and we have tested all kinds of pyrolysis units, different temperature levels, and what we found out in the end is if we go with a low temperature pyrolysis, we have to deal with a lot of clogging, condensation, and in the end, you always need an off-taker for your product. So talking to BASF and a couple of others, they basically, it's too polluted, so they really don't want that. So we went into a different route and we said we are gonna go high temperature. That high temperature has a couple of benefits. First of all, it breaks up almost everything into a syngas. Also, all the toxins. Syngas cleaning has been around for 80, 90 years. We don't need to invent anything. It's already scalable. It's there. So you can apply it. And with the syngas, because everybody thinks the glass is the most valuable thing, but that's not correct. Nobody pays very much for the glass. So the syngas preserves also the C molecules, right? And I mean, why do we take out actually, oils out of the earth from natural gas or oil? It's because we need the C in it, right? And then we process it, put it in a cement kiln, and blow it in the air. That doesn't make much sense to us. So we want to preserve all the C molecules in our process. And that's where the flexibility comes in. So up to the thermolysis unit, everything is the same. And then it depends where in the world you would be. You could actually produce hydrogen and the precursor for the industrial industry. That's what we will do in the site in Germany. You can increase the hydrogen and produce liquid CO2 for example, greenhouses. Then you produce tomatoes, peppers, whatsoever. Or you could also go a third route, that's methanol. Methanol is super interesting, actually, but it's very early stage for the off-taker market. So we can take all types of blades because that's a beauty. We can even take PVC because, we can clean up everything, for the in the process. So why did we choose for that, right? I mean, that's a valid question because everybody has a good reason, to go for this way or that way, right? So we actually had an investor's perspective. So, it was a mixture of our own values and the industry needs. So we made that assessment. We have we also think about resource management also on a higher level. You know, Europe, especially Germany, is not a resource rich country. So we import all of the resources from outside. So it actually makes sense to keep the resources inside and to reuse them over and over again, right? And then also from an economically standpoint. So, you know, price offtake agreements definitely make a difference. So if we talk about value chain, then so the question for us is what will move the needle, right? We have the OEMs, we have the asset owners, we have decommissioning, we have recyclers, and in the end, you know, out of that comes a couple of products, sorry. And the question is always what drives it. So we all are asking, you know, the asset owners are asking, okay, who's going to invest? Well, if we want investments, it needs to be attractive and the investments need to be paid for. It doesn't come for free, right, to build a large facility. So I don't know what's your investment volume, but ours is around 60, 65 million. Somebody needs to pay for that. It's not for free, right? So, and the question, the OEMs, they don't have the margin, you know, they're pretty thin. Asset owners, yes, they have the biggest margin. The decommissioning companies, they're a bit squeezed out. They literally don't care. I mean, let's say 99% of them. We have met, like, I think 3 decommissioning companies who actually do care, but it's an exception. So most of them, they simply just go by price. There's no other evaluation. So that's why, you know, the question is who's taking actually the decisions, and the investments decision have to be taken on the, you know, recycling side. But you need to have the support from, you know, that's where the joint effort comes in. You need to have the support also from the asset owners or on the off-taker side. You know, it just doesn't work as a standalone perspective. So that is why we have teamed up with a couple of asset owners who are deliberately taking the decisions to recycle in the future with us, because they want to cut out that decision part at the decommissioning companies. Because they don't want to be in the press. You know, there have been a couple of scandals in the past. And yeah, so I basically want to touch a little bit on it. So, because, you know, as I said, I believe we are the good guys here in the room. But, you know, it is always a little bit like, what do I want? You know, what do we want as an industry? So, you know, a lot of prices or cost levels were thrown around yesterday. Well, that's also a standalone solution, right? It depends always where does the value chain start. So, yeah, you have visible cost. You have process efficiencies, you know, that's kind of like managing the top of the iceberg. But we also have to deal with a lot of other things that have not been addressed yet. So if you take, you know, how it's done today, you know, let's say status quo, how it's done today, when people do mechanical recycling, they still landfill, for example, the blade root because it's difficult to tear up, right? So that's common practice, definitely in Germany. So don't know how it's done in other countries. So there's a variety of like non-visible cost to it. And it is extremely hard if you need full traceability for example, an asset owner to actually really be sure what happened to your blade. Yeah, so just want to touch upon that. So we are very passionate in that sense, also about the responsibility we are taking. We are not saying, you know, we are the only solution, but we believe we are, according to our value set, you know, we have a good solution. And we are what we are basically measuring everything against is also what is the material health that's, you know, put out there? Can I safely use the products that come out? And do I have a very high material reutilization rate, right? There's different solution to that. But we know that, I mean, all industrial products, they come with some kind of toxicity here and there. It's just in the nature of industrial products. And we believe if you put out, you know, new products, they should be safe to use. So that is something that needs to be kept in mind, and that is where we think, you know, our responsibility comes in, and it can be done also, you know, economically viable. To give also customers a bit more of a traceability and certainty, that is in the pipeline of development. So basically a blade tracker app. It's blockchain based, similar to Plicewire, probably, I don't know. But the beauty is that, you know, as soon as you change information, you change the block. So it's pretty much fraud proof. And that's the reason or the benefit of that technology. But yeah, basically to give, you know, that, yeah, that certainty. And then, yeah, as I think also a couple of other people already mentioned that, you know, it takes a child, it takes a, no, what is it? It takes a village to raise a child. That way around there. So I'm sorry. So yeah, I think everybody in the supply chain or in the value chain needs to take the responsibility. It's, you know, if you point to each other and say like, well, the other guy will do it, the other guy, yeah, nothing is going to happen, right? So our partners is, and we are very grateful for that, we have a great supporter in WPD. We are developing products with the Svane Group in Denmark. And we have also worked with the University in Freiberg for the gasification part and others, TÜV Rheinland and the Fraunhofer IFAM also for the product development side. The product that we are getting out is basically at our site, well, it's a syngas that goes to, you know, a very large chemical company called Dow. They are basically making mattresses or sneakers out of that. It's a precursor. And we have the fibers that are also coming out. Yes, they have seen a high temperature, and the biggest question is always, okay, Claudia, then there's no sizing on it. Yeah, that's true, there's no sizing on it, but there's another effect, and that's why we have a Fraunhofer project right now. It still sticks together because the residual carbon is kind of, let's say, burned in. It almost diffused into the glass. So we are targeting with that, you know, the small fiber market, and you can simply use that as in various ways for building material, for 3D printing. So there's a lot of applications for that. Yes. So then the question is always, how far are you? So, well, we are getting that is the targeted site. We are currently in the process of putting the material together for the building permit and the emissions permit that you need in Germany. So that is planned for end of March, April. And we are currently also in the debt financing process. That goes quite well. We are still looking for a small equity partner, primarily out of the value chain. That's a smaller ticket, maybe 10% ticket, roughly like that. Yes, so once we have actually financial closure, it takes about a year to build. Well, that's the same thing as I think for other projects. So that means if everything goes well, yeah, we can basically be operational by the end of 27. That's kind of the goal. Yes. Thank you very much.
Thank you Thank you, Claudia. Very interesting presentation. So I have some question. First, I'm not fully clear on the current capacity. And second question is if you can share the residual carbon level on the fiberglass.
Sorry, I didn't really understand.
So I am not fully clear on the current capacity of the process.
Current capacity.
Yes,
Okay.
current
sorry.
capacity.
Yeah. Okay.
And then also future capacity. You talk about this industrial plant that is expected to be ready by end of 2027.
Yeah.
What will be the capacity? And the last question is around the residual carbon level on the carbon fiber. I would like to understand if it's something feasible for remelting to make circularity on the fiberglass as well.
Oh, you mean on the glasses? If you could remelt it? Yeah, the residual carbon is about 3 to 5%, roughly. Yeah, we tried with the, for example, glass foam industry. That didn't work out so well, I would say so. But that's a different type of product. The part is also, how much value is in remelting. I mean, if it would be interesting to have that discussion. Yes. So currently, when we are testing our material, we are testing it on basically. So this capacity that we are building will have 4 thermolysis units, right? Because you cannot scale rotary kilns to, there's a limit to where you can scale it because of the heat transfer, right? So we need 4 units, and that's kind of the optimum. We can build smaller. Yeah, you could also build larger, but then you need to kind of double your mechanical separation line so that, it just makes the things more costly. So this is, this is roughly about like 25 to 35,000 tons. This is where the optimum is. And currently we are working on a unit. Normally one of the units has like a roughly 5-ton capacity per hour. And we're using a that has like 1/5 of the capacity. So, yeah, so it's a scaled, or it's a smaller model, it's a prototype model. Yeah.
Okay.
Yes. Yeah. But we are not in a day-to-day operation, yes.
Yeah, I'll give it back. Claudia, first of all, thank you for a very interesting presentation. I think that's really, really interesting. You mentioned in your CapEx investment about 65 million, I wrote down. What is the return of investment?
Depends on the shareholder, but that's financial engineering.
You have operating costs, you have an end product sales, your various. You must have business models which say,
of course.
I mean, if you go to financing, that's what the investors want to know. So
absolutely.
Is that proprietary, or are you going to share?
Yeah, it is proprietary. So because in the end, it's financial engineering. It depends who wants to be paid first, when. So, but it's attractive. So yeah.
Okay. So in our case, if I may, you said you didn't know what our investment starts at. The smaller plant starts at 45 million.
Yeah.
And it goes almost proportionally, in size. So, and return of investment in any plant size is less than 5 years. I think that's worth mentioning.
Yeah. Okay. I mean, that's basically depends like how, but that's where financial engineering comes in, right? With the banks and the
I've learned the hard way that you don't go to investors if you don't have an ironclad business plan.
Yeah, but we have that.
Okay.
So that's why our first investor actually pledged 50 million. So he didn't do that for nothing.
Okay.
So
Thank you.
My question was very similar on the capex side, but then let me go deeper and say, can you give a ballpark of euro per tons processed material? What are the sort of total costs? So for someone to consider, shall I buy recycled or the recovered glass fiber and all the materials which you recover? Can you give a ballpark number on euro per ton?
That would be proprietary. Sorry, but so in the end, you know, we know there will be a competition out there. You know, currently, at least in Germany, the gate fee is very attractive. So, but we believe if you only live off the gate fee, then you know that doesn't work out. So, so of course the capex has to be paid for. So that means in the beginning, yes, we definitely need to have also a gate fee, but we also have products, and the product markets will also develop. So in the end, I think if you only a robust business model, considering like both sides and with a good product base, will have a chance to survive, right? If you have no product to sell, then and you live off the gate fee, then you're almost basically dead right now, no? Yeah.
Thank you, Claudia. Very aspiring presentation. I'm a little bit confused. You mentioned that on the input side, you are pretty flexible. You can deal with PVC, among others.
Yeah.
But you also mentioned that a product passport is a prerequisite. How does that?
No, it's not a prerequisite. It's not good to know, you know, because if you can so we have we can handle flexible feedstock, for example, especially when it comes to blades. So we are preparing for all the blades. We could also do packs, but so we have a range of what we can take in. And because that is simply limited by the cleaning capacity. You can clean almost anything. But that's where investment gets really expensive. So so if we, for example, know beforehand what type of blades are coming in, that actually helps us to, you know, pick the right mixture, because you don't want to run only PVC, you don't only want to run PET and so on. So you want to have a good mixture that you don't have like a system overload on that side. And I think it's a good practice to have you know, passports for the material, because otherwise you don't, at least roughly, no? I mean, nobody knows really what's really in the glass recipe. Other than the manufacturers, but how much carbon is in there, you know, PVC, PET, and so on. So the big data needs to be, it will be helpful. Let's put it that way.
So it's not a showstopper, but it will be helpful.
Yeah, it's helpful.
Being a recycler, I can tell
yeah.
we never get the detailed content. Never.
Yeah, but I think I think we should push for that. I mean, that was also part of the Decom Blades project. And I think it will help also to run efficiencies, you know, to be more efficient in your planning and so on. So, yeah, it's not a showstopper, but it will help, you know.
Okay, thanks.
Yeah.
Claudia, thank you very much indeed. We'll take a break now for coffee. Coffee is served through in the usual place. And if we could come back within 30 minutes, we can progress forward. Thank you.
Everybody, we're pleased to continue now. I hope you've enjoyed your coffee and perked up. Not that anybody was lacking any energy today, and we'll move forward. I'm very pleased to present now Johannes Engels, who's going to present about the energy efficiency recycling for end-of-life thermoset into new composites.
Thank you, everyone. Let me introduce to you Koyos Titan, a company that can recycle any thermoset into new, fully circular products again. Koyos Titan started about the early 2000s when the founders were actually looking for a way to recycle bakelite in Europe. A lot of the electricity companies were taking down all the old meters made of bakelite and were looking for ways to recycle those. So they developed the process of grinding that, coating it with a binder, and making new products out of that. That was very successful, so successful actually that within a few years all the bakelite supply in Europe had been used up. So they're looking then at new ways of actually using this process and looking at other thermoset material. And then it turned out that recycling other thermoset materials were a little bit more difficult in the process. That process has now been fine-tuned, and we're here to present ourselves. And I'd like to thank Reinhard actually about your provocation and your challenge, and I'd like to sort of bite and take up the gauntlet. Who else can claim this? We can claim this. But let me first take you a little bit back. And we've seen that, right? Each year, hundreds of wind blades are reaching end of life, but it's not only wind blades. It's a lot of other thermoset waste as well. It's glass fiber reinforced pipes that are coming out of the ground after being in there for a couple of decades. It's boat hulls, but all other thermoset products as well. For instance, if you are decommissioning offshore platforms, there's a lot of glass fiber reinforced piping and materials in there as well. We've also seen production waste, also a big one. So where we're focusing here on the wind blades, and then the very visible sort of thing also to the lay public, there's a lot of other thermoset waste that we can recycle as well. And of course, what we want to avoid is that they end up in landfill, or even worse, being burned. So what you also have, on the other hand, is that in traditional building materials, there are a lot of products made out of tropical hardwood, out of concrete, out of cast iron, and that's also not a very desirable situation. Tropical hardwood is less and less available in larger sizes. Unfortunately, those big trees, they just don't grow that big anymore. And cast iron, concrete, they have quite a heavy CO2 footprint. So that's where we come in. With our patented and innovative technology, we can actually avoid that any blade, boat, or pipe needs to end up in landfill. And we can turn these into new products made out of composite, which is what we call our material. So what we do, similar to some others that have presented already, is we grind, we shred, we granulate our material. We do this in-house ourselves. There's a couple of reasons for that. One, we can actually control the quality of that. We can also use all the fractions that are coming from the blade, so not only the fibers, but also the dust and everything in between. And actually, that's what we want and what we need, because that allows us to fine-tune our recipe to what the customer wants in the end product. And it also reduces vastly the amount of binder that you need, because that's the next step, coating it with a binder. Because imagine if you have a glass jar, and you put that glass jar full of tennis balls. There's a lot of cavities in between. If you then put them in some marbles, you shake it, those marbles fill up those cavities. If you then fill up some sand, they start filling that as well. So you want to actually have all kinds of different fractions to fill out the matrix and use less and less binder actually to coat it. We then mix that. We have our composite mixture, and we put that into molds. We press it into molds. That's all. You need some pressure, takes a little bit of energy, but for the rest, it's an exothermic reaction. It's the setting of the binder, and there's no other energy that goes into it, the moles I just called. What we make from that are, on the one hand, standard products for building industry, for road infrastructure, for water infrastructure, and those are planks, beams, and poles, for instance. And we make more custom-made products out of that. For instance, hydrant wells. So if you walk across the pavement, you see that cast iron lid sitting there. There's a whole infrastructure underneath that, which is a big ring, often made out of cast iron, and we make that out of our composite as well. And I have some with me here, so in the break you can actually come by and feel it. It's quite heavy, and therefore also quite durable and can take a lot of stress and strain. So those products are currently being produced for end customers. They're water companies, harbors, contractors, even animal enclosures. So you're talking about water companies and harbors where you have mainly replacing hardwood being used at the interface of air and water, where wood rots, where you can actually have a lot more longevity. So you're talking about revetment on the left or jetties on the right. For contractors, we're talking about crane mats, where you have big hardwood poles now that are connected together with rods that the cranes roll over. We produce those made out of composite. The hydrant wells, like I said, the more bespoke product. But even sometimes you find little niches, because this material is so hard. We're asked by an animal enclosure who are building new enclosures for monkeys to have something that they couldn't destroy. And actually, that then is a great story if you then go to a local municipality who's looking for something for outdoor furniture, which the local youths cannot destroy. Well, if the monkeys can't, then good luck to a 15-year-old. These products made from composite have great characteristics. They're very durable, very low CO2 footprint, high strength, both compression strength, but also tensile strength and bending strength. They're flame retardant. I won't say they won't burn, but they form some kind of coating on the outside, which then doesn't really burn further. They have very low thermal expansion. They stay in their shape. Also for the water safety, we've talked about that yesterday as well. There's no leaching into water, no microplastics coming out of it, and also not affected by any organisms or even larger animals, canal-free. And all of that turns into that one at the bottom, low maintenance, because that's something that I think we've also seen here, is that when is the business case actually feasible? Is it feasible if you provide a new molecule that's then competing with all the other virgin molecules on the market? We've seen the case with thermoplastic recyclers who are all going out of business because those virgin pellets from China are just too cheap. So in the end, you have to add something to the value of your chain. So we're not only recycling it, we're making new products out of that, but those products also are competitive in their own right. They are very durable, they last very long, they are very low maintenance. So all of those things make that they have claimed their own place without needing a green premium, for instance, to get into the market. And it goes further than just us having a business case to sell our products. It goes into, I think, creating an industry, and that's what we all do here together with all these recyclers, creating an industry that avoids landfilling waste, but also looks at energy efficiency. So what is the most energy efficient way to recycle certain products? And I think what we've seen in the last 2 days is that every type of recycling methodology has its place. If you can reclaim really high value materials, like carbon, for instance, of course you would want to do that. But if you want to retain the fiber strength and use that in products that can be used in the market again, then that's also a great way of doing that. And in that way, we can approach this from all sides. And what we actually doing is creating a new stockpile of new raw materials. So these planks, beams, poles that are being used in the infrastructure, yes, they last a very long time, but we can take them back again. We could put them at the beginning of our process, we grind them down again, etc. And I think you've heard it before with other mechanical recyclers. So where are we? We're currently in the south of the Netherlands. We have a factory that currently has a capacity of 1,500 tons a year. And we are actually right now building a bigger production facility of 10,000 tons a year. That facility sort of services that circle that you see there in the middle. It's not because it's not scalable from a production point of view, but at a certain point it doesn't make sense to start dragging this thermoset waste across half the world. And we found that sort of a circle with a radius of about 200, 300 kilometers is rather optimal. Then you reach a certain critical mass in your production facility, and it's then actually easier to take that whole thing and put it somewhere else. So in our expansion plans, we're looking for sort of the middle of France, Limoges area, and we've been talking to northern Denmark, Esbjerg, where they have their recycling city, for instance, that they're looking at. So those are the locations that we are looking at. So, like I said, it's great that we are in this together, that we're all focusing on sort of solving this problem. And I think what I'd really like to is that in all these reports, all these presentations, we stop saying thermoset is hard to recycle. It's not. There's a lot of solutions out there. There's a lot of economically viable solutions out there. We just need to start doing it. So, thank you very much.
Johannes, thank you for your presentation. Most interesting. Maybe a question towards the customer base. You're building products that end up in a construction industry that is traditionally focused on steel and concrete.
Yeah.
That means that the hurdle for using different materials is pretty high. How do you deal with that?
And that's correct. It's quite a traditional conservative industry. So we're first focusing on the non-constructive elements. So you're looking at paneling, for instance, where the durability is a very good component. And also, like I said, at the water interface, for instance. So water companies, the Dutch water authorities, for instance, which there are 20 of, those are the ones that are actually using this right now in the first projects.
Thank you.
Yeah, thank you. Also from my side, Johannes, for the very interesting presentation to use the material in other products. What I'm wondering myself is, after 50 to 100 years, what we do then with your products? It's a mix from thermoset and thermoplastic with some other ingredients. Do you have experience what you can do with the old products, what you deliver then?
Yeah, well, it's not a mix of thermoplastic and thermoset. So our binder also is a thermoset. We use polyurethane. And there might be small elements of thermoplastic in it. That can be in our process. That's not a problem. That's why we don't have to be that diligent in sorting out the material that we get in. But in the end, you just shred it again. So we've not taken a 50-year-old product of ours, they're not out there, but we've taken a 1-year-old product of ours and we've shredded it again and used it again.
And you do this already?
Yes. And not because it's needed, but because we tested it. And there again, because we determine our own recipes, we can add some extra fibers if that's needed, but also for some applications it's not needed. So for instance, that hydrogen well doesn't need any tensile strength or bending strength. It only needs to withstand the pressure of the wheel of a truck standing on it. And that's perfectly fine with just granulating it again and using it again with a binder. If you were to make I don't know, a load-carrying beam out of it, of course, you would want more fiber in it, and that's maybe not what you could do out of, or what you would want to do out of the, after 50 years again, recycled.
And maybe another question is there an idea to know where the products are? Because after 50 years, nobody knows what's in the ground, what pallets is there or something else. Is there some idea to get it back to really...
Yeah, it's something that we're working on. We haven't figured that part out completely yet. It's also what we're working on with our first launching customers, what they want. But we're experimenting with putting RFID chips in there, or putting some aluminium sticker barcodes on there, or QR codes on there. It's all the question of how much does that actually still work in 50 years' time. But I would love to be there in 50 years' time and have that problem, actually.
Okay, thank you.
Hello. Very interesting, thanks. I mean, I remember your presentation from the last year as well.
Thank you.
My question would be again on the demand side. So how do you see the role of municipalities and public entities in boosting the demand for this kind of products? I see a big potential market there. Public procurement should really support these products more. And then I have a curiosity on how you handle fire resistance specifications, because that is pretty complex in with high fraction of recyclates in the product.
No, clear. That first one is, so we're working with some of the water municipalities, for instance, who are putting this into their first projects. And the way actually that we're approaching our first go-to-market is actually looking for customers where we can have a cradle-to-cradle approach. So they actually have a thermoset waste problem. We're taking their waste and we're giving it back in certain products. So for instance, these water municipalities, they take these GFR pipes out of the ground. We grind them and make these planks and poles out of them that they can put back in. And you're right, those are the types of customers that just from being a public service also need to show some kind of environmental consciousness. Those are great launching customers that then can show to the rest of the more traditional conservative building industry that these kind of things work. And it starts with showing that it's safe in the water, for instance. That's why I chipped in yesterday about my comment about the microplastics, because we've been asked that, yes. And in the end, so there's no one study that shows that it's safe, but if you put the whole body of evidence out there, it's safe to use it. Your other question was around the fire retardancy. So we don't have any claims on that. So we're not proposing it right now to be used as some kind of, if you would build a structure with a steel beam and clad that beam with our product, that's not what we are proposing to do. We've done some testing ourselves. This is where we see that it has very promising properties. But if we were to use this in those settings, we would have to do those tests.
Thank you.
I do have a question.
Yeah.
One is very interesting, and I believe it's a fantastic product. Allow me to ask a few things. Since you're using virgin thermoset resins, what's the CO2 footprint on the product? Then, how competitive is your pricing compared to the standard, whatever cast iron, whatever units you're replacing right now? And thirdly, if you can share, what's the return of investment of your operation as far as capex and
So the CO2 is favorable if you compare, the LCA is favorable if you compare it with hardwood, with cast iron, and with concrete. It takes into account the longer lifespan of the product. If you just have it kilo versus kilo, then it doesn't. And I must also say, and I think all of us looking at LCAs, it all depends almost, right? What do you take as your boundaries? And there's also, I think, for concrete, some very unfair comparisons out there from very old approaches to LCAs for concrete. But also concrete is the least of the products that we're trying to replace because it's so cheap. it could only be in applications where you need to be lighter, like roof tiles for roof terraces, for instance, where it could be an application, but otherwise, concrete is very cheap.
But roof tiles, there you get into the fire retardancy issue,
Yeah.
big time. I would not recommend that.
Okay, great. Thanks very much
Tell
for
you
that,
from
for that warning.
experience,
Yeah, okay. On the pricing, we are very competitive in pricing if you look at the larger sizes of hardwood that we're replacing, so larger sizes of beams and planks, for instance. If you look at the smaller ones, the ones that you buy at your local DIY store, so a 2-meter plank, for instance, that's not very competitive because we put it in molds, and the work of actually putting it in the mold and taking it out is almost the same for a 6-meter beam, which is 40 by 40 centimeters, versus a 2-meter plank, which is 10 millimeters thick, for instance. We are working with ways of actually cutting a beam into smaller ones so that we actually have the one production run and then making it into smaller sections. Also, it's a great way of actually handling your inventory because you have sort of a half fabricate as inventory, and then depending on the demand, you can actually cut it in different sizes afterwards. But that's the way we approach it. For cast iron, those are more the sort of bespoke products, the custom products, and there you can actually ask a lot more price per kilo because it's a very specific product. It's also where we have commercial agreements with our customers of how you actually recuperate the investment in the specific mold, for instance.
Yeah. Thank you. Very interesting.
Okay. Sorry, and the return on investment question is, I can't answer that. I don't know if it was you that said it or someone else, but by actually having these end products in your business case, the investors are saying, this can't be true, this is too good to be true. They've been looking at thermoplastic recycling business cases and saying, how can this have such a short return? How can you actually get these kind of turnover in such a short time? That's by actually having an end product that you're getting to the market and selling that.
If it's so good, you should put it on the table.
No. Yeah.
I think this is good enough.
Yeah.
All right, good. Thank you.
Johannes, thank you very much indeed.
Thank you.
Efficient recycling and process methods. So we welcome Niels Ludwig onto the stage now. He's a senior engineer at the Fraunhofer Institute for Wind Energy Systems.
Yeah, hello everybody. I talking a little bit about the recycling of rotor blades, what we dealing as Fraunhofer, and especially my cases there. I will show you a lot of things what you've seen yesterday and today, but we have to focus more from the research side. So we are not a producer or something. We can only help the industry to bring us forward. Okay, what I want give you a short introduction about Fraunhofer and the EWIS. May you know, may you not know what we do, and then coming in the question, how much separation is needed? We are not discussed this point, and we have a very special meaning on this. And as we are discussing about separation on the rotor blade, come later on this, then how we do it. And how we do it in a matter of cost efficiency. And yeah, then some different methods there. And then some experience what we have about rotor blade recycling or what we see in the market. And I want to introduce some new products made by old rotor blades. We hear this also from other presenters, but maybe only for discussion what happened then with these products. This is why I have such questions about someone present a new material or a new product of it, what's happened there after this life. Yeah, and then a small outlook and discussion with you. Okay, who is Fraunhofer? Fraunhofer is a research institute what is connected very deep to the industry. Fraunhofer is quite big. We have 75 institutes, over 30,000 employees all over Germany. And we as Fraunhofer IWES are one of the institute. And we are the institute who is dealing about wind turbine, and especially wind turbine blades. We are located in Bremerhaven. It's our main stuff, and we are starting with rotor blade testing. A little bit difficult today. You see our test halls here, our big test halls. This is what the industry knows us. We are the test institute, but we made more than testing rotor blades. We are starting very early in the beginning with some investigation about wind conditions over the sea, some investigation about soil for the offshore turbines. Means that we've tried to find out is there some soils on the ground where the wind turbine not can stand. Also, we had a laboratory which can support structures. Find out. And one important thing for myself, we have nearby the test facility, also a test facility where we can produce rotor blades. Clearly not the 100-meter blade, it's a little smaller, but we had test facilities for simulate production issues. And we also can simulate recycling issues, especially the dismantling and the cutting there. Yeah, and nearby there's a large bearing hub there, and hydrogen, and in the 1 year, 2 years afterwards, a big rotor blade test stand because the rotor blades are getting bigger and bigger. Yeah. Okay, as we are thinking about how to separate the rotor blade, we have to know what is in a rotor blade, which parts are in. I think that sometimes it's not quite clear what ingredients have the rotor blade and in which percentage. And I will give you also an overview about the annual end of life for rotor blades, especially Germany. Why Germany? Because we are here much more and more that it's a local business. Not interesting about worldwide rotor blade dismantling. It's more the question in which region will comes the end of life rotor blades. And then coming the separation, but separation concerning its future use. We will see why I point this out. And some maybe alternative to separation. But we're starting, how is a rotor blade designed? Okay, I have here a cut of a rotor blade, means like a part of bread, and the main part of a rotor blade is the spar caps and the shear webs. Spar caps means the bending element. It's like a T-joint. Okay, in bigger blades it's a double T-joint, but in the end it's a massive spar cap on the suction side and the pressure side, hold it together in distance on a shear web. And the spar cap on a smaller blade is in glass, and in bigger blades, offshore blades, it's in carbon. But it's this only thing ingredient, the carbon things. That means even a very, very long blade, 120 meter or so on, they have only the spar caps in carbon. And the most of the area is a sandwich laminate. Here we see it here. It's made in PET, PVC, or balsa wood. This is why we have to handle the sandwich material. It's not from the, it's also from the weight, the most of it, especially of the surface. And as we are looking, especially for old blades, what will come in the next 10 years, we are looking about which material in percentage by weight is in. And you see that's roughly 60% glass and 30% resin. This is the most of the material is glass and resin. And so we have to handle these materials there. But not forget the balsa wood and the foam. This is why is it so interesting? Because from balsa wood and foam, we can very easy make other products as we separate it from the blade. How does it go? I will show it later. So it's always thinking about the ingredients of the blade. Only shredding and burn it makes not really sense. And as we are now looking about annual end-of-life masses on onshore, we made a data diagram, or make the datas from a recycling project names. What was the name of it? Recycle Wind, sorry, Recycle Wind. And from Recycle Wind, we take the data and annually updated these data. And the interesting thing is that separated not only the whole mass, it's also the ingredients, what you see. And not wondering that the most, it's green, it's glass fiber and resin, it's in orange, and a little bit of foam and balsa, because that's in volume a high amount, but in weight very less. And you see also here in 2028, 29, 24, it's going down. This is why the installation in Germany 20 years before was quite less. And as we look about offshore, we have also a data from the offshore. There we have a peak on it, and then goes down. And here, 41 is zero, because there was no installation on onshore in Germany. And so that's clear. Then come 20 years later, no blades there. And we, as a consumption then, I showed later, then we come to a maximum of 80 megatons about material, what we have to deal. Come later on this. Okay, as we see separation of material. I have an end-of-life blade there. They have a thick root laminate. What I think Claudia recommended, that this is landfill, even because it's not shreddable. If you're looking about 100 millimeter, and this is also from the thickness of the flange on quite old blades, it goes not through the shredder. And so the question mark, can we do it? Yeah, you can handle it. We can also handle it. You get the pyrolysis. Why not? Cut it out, cut the flange on, give the pyrolysis and not shredded. And then you have the glass fiber and the resin. The question mark is what we do with the resin. But for the glass fiber, yes, we have the new action from Owens Corning to remelt it, but it could also to take it for filling material, for adhesive, or we can make foam glass on it. And so there seems a way for this pure glass without sandwich material. Then we have the sandwich material. There we made some trials with the sandwich material. We shredded in the case that we can quite easily separate the sandwich material from each other. Means the foam and the balsa wood. The balsa wood is very fine to make isolation mats on it. And the foam could be also used as a PVC to isolation mats, and the PET they made starting to make recycled PET. From the PVC, we have to know that the quite old blades, what's now coming, mostly ingredients PVC. There was not PET, it was PVC there, and we have to handle this point there. And PVC is not so easy recycled to new PVC as we have it to do now. But we have to know, is it in or not in? But there is maybe a solution for this. Okay, this is the way what we heard more than once, what we do at the moment. We decommission it, cut it in pieces, then bring this to a shredder and then burn it. And the question mark is, would we, this 83,000 tons in incineration, or we want to solve these problems? As we do it, we can do it, by burning, then we have a problem. We have the problem that burning the carbon fiber and by clogging the filtration, and also for the glass fiber. And so burning is not the solution anymore in this. And then would take a little bit how we handle such a big blade. If you're thinking about this is an 83-meter blade, what we're cutting by hand at our yard. There's a guy, it was two guys, worked roughly 1 week and cut it in 10-meter pieces, separated here the carbon fiber out. I can show this picture because the company doesn't anymore exist. Maybe some of you know this blade, but they're not existed, so it's easy. Here you see the carbon material here underneath, and the crazy thing is that from the outside, even the blade has no paint, you cannot see it, because in the production they had the idea to produce the shell in glass and glue then the carbon on the shell. So from the outside you cannot see it. But there is a trick to how to detect it, but you have to detect it. Today's, if they cutted blades, they're cutting, oh, it's black. Oh, now it have to be carbon. But this is not the way to do it in the end. We are separated these panels from balsa wood and foam and carbon, and then bring it to different separation solutions. Okay, let's try the next. Okay, yeah, cutting semi-automated, not by hand. Semi-automated means I have a gantry. Clearly, that such a gantry, what in the industry used, is not like this. This is our gantry for producing rotor blades. This is why there is a mold. But you can imagine that if there's a blade underneath, we can semi-automated cutting the rotor blade either by milling or also with water jet. But this is one of the point. The next is separation of sandwich and FRP. We make some trials. It's quite easy. You have the shredded material, give it to a water bath, and take away the light material. Here, it's maybe the balsa wood, and with this sorted material, we can reuse it as another thing. Not in a rotor blade, clearly, because the balsa wood itself has not the same effect because it's not have the right direction, but for an isolation mat it's function, and in the future maybe we make an balsa foam on it and can use it in the rotor blade instead of foam. But this is really future. And separation by machine or by a plant. We try this also. It's quite easy. You give it there, the machine learning how is the design of the different materials. You can say, okay, we take it with augmented reality, no, but it's only a little bit learning. And then it's a very nice separation. We do it on a machine, a bigger scale. This is PET foam and glass flakes on it. And with this separation, then you can really recycle the PET and then give the glass flakes for the next issue because it's separated there. As we compare a little bit the separation method, cutting by hand, clearly it's with water jet and or a saw quite easy. For a low amount of rotor blades is profitable, low investment costs, and yeah, it's dangerous for operation. You see the guy standing there by a big blade what's laying on the ground. If the panel's falling down and you have to hold it, it's not easy on this. And we have the semi-automated by a machine. Clearly, we need a high investment on it, but it could be very exactly and repeatable and possible as we are having a higher amount of blades and we are getting really in industry. The floating sink method is after mechanical grinding, clearly also low investment, easy method, but the sandwiches the principal parts are wet and have to be dried. It means I have another process afterwards to can use the material again. And industrial separation, clearly we need a plant, a very big plant. It's a high investment to do this. Standard machines or standard plants can do it, but it have to separate to other waste. And the pros are we have a lot of amount of material what can separate it, and yeah, against the high investment cost. Okay. Come to several solvolysis and pyrolysis. This showed also from my other speakers. We have the chemical is solvolysis, the thermal is the pyrolysis and co-processing, mechanical grinding and shredding, and electrical, we named the pulse fragmentations. There are some others, clearly, but it's only for getting an overview what has happened and what can be done. Okay, if we compare this, the solvolysis, the chemical bonds are broken by the solvent. I can have a refiber, used fiber, a fluent fraction, and the fibers are relatively intact and can be recovered. As we are thinking about carbon and say, okay, we want to recover the carbon through other products, that is a product. The pyrolysis, thermal, quite easy, have also recycled fiber, pyrolysis, oil and gas. Depends on the temperature, is the gas and the oil different, and the fiber size is destroyed, absolutely destroyed, and the strength of the fiber is reduced according to pyrolysis, and the question mark, what I do with the fibers. By the co-processing, mechanical grinding, give it in a cement clinker, it's well established, we do it commercial, available, but there's nothing in the end left. No recovery of fiber or resin. It's away. If we do only the mechanical grinding, yeah, clearly shredding and crushing, then I have a fiber and rich resin, have some remaining waste. Clearly, we heard it's efficient, very efficient, it's scalable, nice product what we learned from Johannes, but I think that the material itself, the fiber and the resin, is a way. I have a product where I can maybe shred it again and can use it again, but I have no chance to bring back the resin or no chance to bring back the fiber to remelting or to bring it in the process to producing in the end. It is the wish a new blade. Yeah, pulse fragmentation, I split this. Okay, different method to separation due to part of the rotor blade. What we discussed yesterday, it's quite easy. Unknown blades, what is in? I show you some words on this. Then the dismantling of rotor blades. This is not a really modern system. We do this with our hand separation, then the separation, foam and balsa, and the batch pyrolysis. Going a little bit more in detail. What means the incoming control? Incoming control means maybe how to know where is the sandwich parts, the spar caps, the full laminate. We do it by our own research blade. We're blowing hot air in with a thermo camera. You can quite fast see. You see here the red parts is balsa wood, the green parts is PVC foam, the blue parts are the spar cap with the glue and also the full laminate on the nose. If you do this and several times, you can really nice know which part is where. For this blade it was quite easy because it was not painted. But even with painted blade, it's function. And with these thermal images over some software codes, we can detect it which material is in, can this visualized, and also what is more important, we can cut it out on it. Clearly, not by hand, by semi-automated. And in the next, as you have it in such a semi-automated environment, as we are scanned the surface, then we have the really nice shape information, and then if someone want to have from this blade a roof or a part for shelters or something else, then we can cut it out in this time and really know what is the shape what you get. And as a next step, clearly cutting the blade in this row by a robot. Clearly we can do it with the cutting saw or a band saw. This is a trial what we made, and also with the water jet to separate it afterwards. Yeah, this we seen also before, that we made some terrace bondings there, or panels for solar parts, and all the shredding the pure glass. As we're looking about the most ingredients of the blade, what we learned before, then we have to discussing what we do with the fibers, the pros and cons to remelting. Clear, remelting is circular. I have a new glass fiber on it, but the glass fiber have to be separated by the type. Means that's not the type in technical data, it's the type in the melting point. This is the point what we always discussed. The glass suppliers who want to remelt it say, yes, that's nice, but I have one glass 1030 degrees, the other glass has 1060 degrees. If you put this in the oven, then I have a problem to separate this, and they need the melting point. But I cannot see which glass have which melting point. This is one of the point that we have to know which is the melting point to give them really in recycling on it. The post for this is just shredded there as filling materials, reinforcements, circularity, downcycling. And aggregates in cement, we know this clearly, burn it, and then it's the ash, and the ash what used then in the cement clinkers. What we can do also, we see some of the pictures, and we discussed this yesterday, and it's very interesting. As I use such blades, okay, the nice walls, what we see yesterday is not there, but anyhow, if I have this in the community, I have enough time to find out what is in these parts. Also on bridges, what is in the bridge there. And if I get it back and really to the recycling, I exactly know which resin is in. I can think about where is my balsa wood and foam, and have to take there. We also make some furniture of it, only to look how does it function. But if this furniture goes then in the community, in the private sector, it will be hard to get it back. Here's also from the shelters. Is there also, after several years, I can find out and get it back how to use it, and especially what is the ingredients, what today is not made. But this is one of the point where we are want to bring projects in to say how we can make an incoming control for rotor blades which be separated. Okay. To the last slide. Yeah, question mark of what I want to also discuss today, now, or also then in the part-time, what we can do else with the fibers instead only to bring it in cement, to bring it in a melting or something else. And what's about the private use of the planks? You see some terrace bond planks. Can we do it circularity, or what happens then if it goes away? This is why I ask, are we be sure that in the end of the life we can really recycle it? And yeah, who should pay for the waste? At the moment, the wind turbine owner, Bettina, have to pay. Yeah, she we say in Germany, she have the black Peter. She had the black card about this. She have to pay it. Not the producer, not we as material supplier, nobody. But is it fair or is it not fair? And we say, yeah, they earn money, yes. But I heard that it's anymore not so much that they have so much money. Yeah, clearly, this is the question mark. And if you have this point that the owner of the turbine have to pay for the bill, then they do always with the lowest cost. Clear. Who else should there? And this is a thing what we should discuss. Who pays the bill? And yeah, the commercial issues against proper way of recycling is also is that controversial or not? We can discuss about this and bring this in the community. Okay. Yeah. At first, from my side, thank you. I have used the time.
Yes, thanks for the interesting presentation and the nice overview. I was wondering if robot cutting becomes commercially available. Of course, it's very interesting for us as well, and I've been dreaming of that for a long time. But what would be the upfront cost of bringing something like that outside of a research facility into the practical field?
Yeah, that's the question of the amount of the blades and the question how you program the robot. It's maybe not for the whole blade. Clearly, it will be handwork and maybe a mix of it. But we see that if your robot really operated 24 hours, 7 years, 24 hours, then it's very valuable. Okay, the question mark is how complex is the robot?
Well, in my opinion, it could be fairly simple, but I would always try to operate it on a full blade, where you can put the full blade somewhere the robot can drive or move around.
Yeah, move around and getting to the edges there.
Yeah.
And what I not discussed is coming a full blade to the cutting, or is the blade more cutting in sections, maybe 13.5 meter because it's transport length, and width of 22.5 meter, and these parts are cutting there, and then it's easier handleable. Anymore in the flange area, it's quite big.
Okay, thanks.
Yeah.
Thank you, Niels. Very interesting presentation. I have a question about you showed a picture of a thermographic image. Did you, I mean, this is interesting for us because many of the old blades it's completely unknown, and
absolutely.
Yesterday there are no design data.
Yeah.
So I think that is very valuable. Was it just like an infrared?
Yeah, it's quite easy.
Or did you have light from the inside?
It's quite easy. We take it because I cannot also believe how does it function. You take a blower, blow in the temperature, shut off the blower, and wait the moment that's cooling down, and then you see it. Clearly, you have to make some trials to see and interpret the infrared. Teach it, like the augmented reality.
That was excellent.
It's excellent and very, very easy. And then you have a database for all of the blades, for the next blades. Especially
when we take blades from a wind park, you know, we may try to avoid to cut through the carbon.
Yeah. This is the point. Yeah,
this is good.
This is the point. And if you make it in some blades, then you have a good database for do this. This is why I presented it. It's so easy, quite easy.
Thank you very much.
Yeah.
Thank you very much. Can I just add in here? There's been Probertine has been attacked and attacked and attacked. Who pays? Ultimately, if the tender's put out correctly, the consumer of the electricity pays.
Yeah, this is
and that's how that should be.
This how it should be. You're absolutely right.
Yeah.
We all who use electricity have to pay for it if we want to do it as a community. And if we accept that we shred it and burn it, then we'll not change. But I have good hope because you see the last 2 days, yesterday and today, there are some solutions what really industrial side come to this. We will never operate a recycling center. We can, as an institute, only can help to do it and give a meaning there. And this is the point. We have a new mindset about this topic, all of us. And with a new mindset, then we can, starting such activities.
So. Yeah, it's all good news really for RVE.
Yeah.
Thank you very much, Niels. Yeah.
Okay, thank you.
Yeah, we did discuss afterwards.
Processing for recovery of materials during rotor blade decommissioning is what we finished with Niels. That is a discussion that's going to continue today. And we follow through now with microwave-assisted recycling. And there's challenges to that, prospects and process scaling. So we invite here Ignacio Barillo to present on behalf of the Circ Technology Center.
Thank you very much. Thank you very much, Mr. Chairman, for the nice introduction. It's a real pleasure for me to be in front of you talking about the challenges and the developments in the framework of the microwave-assisted chemical recycling, because taking into account the audience here, which is very business-oriented, the technologies with lower TRLs are being somehow overestimated in this overall conference talks. Just in the case of Derek yesterday, he was mentioning microwave pyrolysis as a potential technology in terms of CO2 footprint reduction, etc. But nobody else has talked about the details, what is inside this technology. But before going into the topic, let me present briefly what is CIRSE. CIRSE is a technology center based in Spain, which helps industrial partners to increase their competitiveness in the fields of energy and sustainability. We are based in Zaragoza, in Spain, with more than 300 professionals and more than 50 PhD researchers, but we have also locations in Madrid and Brussels. And our aim is to fill the gap between the research and the needs of the business sector. So, which is our strategy? First, we identified lines for research and development and innovation. Then we obtained competitive public funding as the project that is funding this development that I will show later. We accompany the industrial partners to assess the viability and profitability of that technologies, and we transfer the results to the company. So we license the technologies that we develop to the end users. We enhance the competitiveness of our partners, generating private income, and during the lifetime of the technology progress, we anticipate the future challenges, keep informed our customers, and we reinvest the income improving current lines or creating new ones. We are a self-sustained organization. We don't get any public funding. And our income overall one in last year, for example, was 20 million euros, 60% based on research activities, 40% related to transfer and services. We are very active in European projects, both leading them and accompanying the end users. These are the lines that we cover in our technological center, but my department is focused on industrial technologies, efficiency and decarbonization, plus recycling and circular economy. And this brings me into the topic. Of course, if you are here, you are prone to this renewable wind energy, you are fond of it. And I don't want to go into details on the figures of the up right and down left plots, because they were fully discussed yesterday by our colleague from Wind Europe. But I want to stress out that besides dismantling due to the age of our end of lifetime of the turbines, they are being also dismantled due to repowering purposes. So if 2 windmills can bring the same energy that 10 windmills that are in this wind farm, then the business has to replace those windmills. So, which are the options for the end of life? They have been commented alongside the previous talks. Blades repurposing, as you can see there, picnic tables, which is an action made by the Refresh project that is found in our research, but also parking for bikes and urban furniture of different types. But then we have also the mechanical recycling and thermal recycling. You all know about this. Mechanical recycling is the most mature technology, and that's why almost all of you were talking about this technology and how construction panels and other kind of products can be made out of it. But regarding thermal recycling, I've heard at least 3 times along yesterday and today that the fibers have low value and the oils cannot be directly sent to anyone else, none the petrochemical industries or not other use in the chemical industry. I will I will comment on this because in my opinion and based on the results that I will show, there is a possibility to get value out of the oils. We focus on microwave pyrolysis and microwave solvolysis. And since the TRL is low, as mentioned yesterday, around 4 to 5, we wanted to validate at lab scale level how the technologies can improve the overall energy efficiency and products characteristics, both in glass, fibers, and oils. And this is what we did. But microwaves, I believe you are not familiar with them, but microwaves are electromagnetic waves that interacting with a matter, they change the polarity of the matter, provoking the release of energy in the form of heat. How fast are they changing the polarity? Well, imagine your microwave oven at home working at 2.45 gigahertz frequency. That means the polarity is changing 2.55 million times per second. This impacts in the molecular level release of heat by friction of molecules, and that leads to a sudden increase of temperature of the heated material. So, in terms of depolymerization of resins from wind blades, we can get drastically reduced heating and full depolymerization times. As you can see here, the heating times to reach pyrolysis temperature, well, not in that case, but it's up to 10 times lower in heating time with respect to conventional heating. In respect to the depolymerization times, they are up to 10 times lower than those under conventional solvolysis. That gives great advantage, but the key advantage is that we can generate a temperature gradient between the solid sample that is heated and the surrounding atmosphere. Why is this important? Because if you think of resins, the heat transfer in resins is very poor. So a large temperature gradients along the heated medium can be achieved under conventional heating from the walls that are hot to the resins that in the center of the vessel. And gas phase cracking in the hot reaction system atmosphere limits the oil product distribution controllability. So once the chemical molecule starts to break, you cannot control anymore which kind of products will you get out of it. I will come to this later. In contrast, microwave heating advantages are fast, selective, and volumetric heating, enhanced control over the pyrolysis process and oil product distribution, as well as a lowered apparent processing temperature. And this is important because if you are able to reduce the temperature of the pyrolysis by 15, 18 degrees Celsius, you preserve more the mechanical strength and properties of the recovered fiber. So, what happens at chemical level? Here, for example, you have a molecule of an unsaturated polyester that has several bonds, carbon to oxygen, carbon to hydrogen, etc. Well, some bonds are weaker than others, so they can be easily activated or broken with temperature. And this is what happens along pyrolysis. So, if the environment is at the same temperature of the sample, this chain reaction keeps playing, so the final molecules that, here the pointer is, the final molecules that you are getting may be randomly have a random distribution, so you cannot get value out of them. But on the contrary, if your sample is hot and you have a colder environment, you are somehow inhibiting this chain reaction that takes place. So you can keep, So you can keep the production of the products of interest, what we call the chemical building blocks. And they have a real value, a market value. So, experimental tests were performed in these two equipment. The setup for microwave pyrolysis is on the left-hand side. The setup for solvolysis is on the right-hand side. In all cases, what we use is just threaded blade parts, composite parts, from wind turbine blades from different wind farms. And what we get and analyze and characterize are the fibers and oils out of them. The pyrolysis unit has a 3 kilowatt roughly microwave power, while the solvolysis one is 1.5 kilowatt power. And they can process in a batch mode up to 1 liter of sample. This allows us to have a comparison on the performance in both electrical consumption and quality of the products to see which of the technologies is more promising. So first thing we do is to characterize the input, the feedstock, because the blade parts that come to us, we don't have any clue on the resin content. So neither the amount nor the material, either polyester or epoxy. So we calcinate them, we evaluate the amount of glass fiber versus resin in the sample, and then we shred down the piece. We separate the lighter fractions, so the balsa and others, and we perform the thermochemical test. And this is what we get. We were analyzing the operating temperature, the residence time, the ratio between susceptor particles and the blade parts to be assessed. And we found that in case of microwave pyrolysis, for both epoxy and polyester resins, we were able to get clean fibers. If the temperature is too low, some resin rests remain. If the temperature is too high, the glass fiber start to be damaged, as you can see here. Let me just here. They are completely damaged. By the way, if you see it visually, they are crystal clear. They are white, and their appearance is nice. But if you go to the microscope, they are completely destroyed. So we were able to get the optimum temperatures for this process, both for epoxy and for polyester. And what about the oils? The oil compositions in case of epoxy are made of benthofurans, pyridines, styrenes, and phenols. Phenols representing more than 80% of the overall weight of the sample. In case of polyester resins, we were able to obtain phthalates and phthalate acid derivatives at the level of 70%. This is important because I don't know if Pascal is here, but he was showing yesterday that they were obtaining BTX styrenes that have a certain market value. But if you are able to control this temperature gradient in the gas phase, and you're able to keep the building blocks as phthalic acid, then the price in the market is much higher in this case. Regarding solvolysis, results were not so encouraging. In terms of glass fibers, they were also visually clean and white. But once you go into the microscope, since we need to use catalytic salts to provide the 100% degradation of the fibers at low temperature in order not to decrease their mechanical strength, some deposits of salts remain there that may impact the final use of the fibers. And in terms of oils, since we use solvolysis media, so liquids that are quite aggressive to the resins, the resulting molecules are less useful or have a lower market value. But still, they could be used as fuels. Because here I'm showing you a Van Crevelen diagram showing the atomic ratio between hydrogen and carbon on the vertical axis, and oxygen versus carbon. So if you look at jet fuels, naphtha, diesel, biodiesel, they have a very low amount of oxygen and roughly 1.5 to 2 H to C ratio. And our oils are quite close to them. So after proper upgrading of the oils in order to remove mainly the nitrogen that needs to be taken at the ppm level and a slight reduction of oxygen content, these liquids can be reused as oils by the petrochemical industry. This would be the final destination for solvolysis oils, because from pyrolysis oils, one can get these building blocks that I was mentioning, phenols in the case of epoxy, phthalic acid in the case of polyester. With all of this, we wanted to evaluate the electricity consumption and the OPEX and CAPEX of the technologies at lab scale. And what we found is that both the energy consumption and OPEX and CAPEX of solvolysis was at least twice as high as that of microwave pyrolysis. So the results were not encouraging in terms of energy consumption, because as you can see there are kilowatts per hour per kilogram of FRP, not per ton. So still very high, because the lab scale units were suboptimum. That means these units were designed for the recycling of other sort of solids like plastics, textile, etc. And we wanted to adapt this proof of concept to these wind blade materials. But still was enough encouraging to go forward with the technology. And this is the first time I'm showing in a conference our new pilot plan for microwave-assisted pyrolysis, which is able to treat up to 30 kilograms per hour of wind turbine blades, shredded parts. The power consumption is, the maximum one is 9 kilowatts, plus 6 kilowatts of cooling power to condense the organic vapors into pyrolysis oils that we get, finally. By testing this scaled-up technology, you want to take a picture? Yeah, you look upset. Anyway, you will have the presentation afterwards. So. Yeah. So, which were the results with this pilot plan? We were able to decrease the normalized, that means per kilogram of sample, energy reduction by 120 times, and we were able to reduce the OPEX, the overall OPEX of the plant, by 58 times. On the contrary, the CAPEX of this new plant is just 5 times higher than the small microwave oven that I was showing at the very beginning of my talk. So we wanted to elucidate how this technology will shine in the market, or which are the return of investments and payback periods for this technology. It's a pity that Reinhold is not here, because I'm the only one that is showing the return of investment. Anyway. So basically, we need to take into account the selling price of the outputs of our system, that are the glass fibers and the oils. If the glass fiber price is in the vicinity of 200 euros per ton, 250, our business case would be negative, as you can see here. This would be the curve of payback period against the production capacity for 200 euros per ton of selling price. But of course, if we can get value out of the oils, and this would be the case, the oils can reach up to 500, 700 euros per ton. And this would make the technology fully profitable, both in terms of payback periods below 5 years and returns of investment, of course, beyond 20% yearly. So this brings me to the conclusion. So microwave heating boosts the energy efficiency of wind turbine blade recycling, so down to 3 times lower consumption per kilogram against conventional heating. Increased process controllability to get the oils, the molecules that we want to preserve, and requiring fibers quality, keeping up to 80% of the original mechanical performance. We evaluated both pyrolysis and solvolysis at experimental level, and both may provide clean glass fibers plus complex oils. The techno-economic assessment revealed that the overall cost in CapEx and OpEx of pyrolysis is roughly 2 times lower than that of solvolysis, and the quality of the fibers are comparable. But pyrolysis oils seem more interesting from the end-use point of view. And finally, this microwave pyrolysis is being validated through a pilot unit that we have at our labs to assess the process scalability and energy efficiency at larger scale. And this plant will be available for bench trials for potential investors that maybe are you. So in order to get a deeper detail on the results that we got and the real numbers, conversion, selectivity, yields to different oils, you can have a look at these 2 recently published papers. And that's all from my side. Thank you very much for your attention, and I'm pleased to answer questions.
Hi, hello. Very interesting presentation and excellent work. I just have a question. Well, compared to the CFRP, I think for using the microwave pyrolysis for the GFRP is more challenging, as we all know the cured thermoset matrix and also the glass fiber, they have the low dielectrical properties. So how can you make sure that you have relatively high absorption microwave efficiency for the GFRP?
Yeah, in our technology, we have developed a complete mixture of these parts with susceptor particles. The susceptor particles are the ones that receive the irradiation and release the heat into the shredded parts that are mixed in a whole fluid aspect.
So it's the solid particles?
Solid particles.
And after the microwave pyrolysis, do you have to separate them from the
Indeed. Yeah, but the size of these particles is completely different to the size of the glass fibers that remain in the bed.
So
we can sieve them.
Or bigger?
Basically, the geometry is different. The 2D dimensions of the fibers can easily be filtered out through a sieve, while the rounded shape particles that we use, basically they are silicon carbide particles, can be easily separated, also by density. So it's straightforward.
Yeah, and for your economic assessment, do you also including the cost for using these particles and also like the separation process?
Yes. What it is not included is, for example, the permitting or the installation of new buildings. But for one that has already a mechanical treatment and has a shredded material, then the rest is incorporated in this analysis.
Okay, thank you.
You're welcome.
Thank you very much. I think your technology has potential, especially if you think of a continuous reactor, because the microwave are heating up things so fast. So once you go from batch to a continuous, it really looks promising. My question is, probably you're using 2.45 gigahertz, so the standard. Now that may not totally fit to the absorption spectrum of the organics. You want to heat up the organics. We had a similar experience. We tried to de-ice wind turbine blades, and we used a carbon nanotube coating which absorbs all microwaves, actually from Arkema. So you want absorber. Maybe if you tune the microwave frequency to the organic molecules, those you want to heat. But then it looks very promising. I don't think the absorption spectrum matches the organics. That's my question or point.
Our approach is rather different. We don't want to hit the organics, the vapors that are being generated, because we don't want the chemical reaction to evolve towards molecules out of our control. We want to get the building blocks. So we want to get the first molecules that are generated out of the initial breakage of the resin matrix. So in this case, we are working on the continuous operation. What is fixed, what is inside all the time is the susceptor that gets hot, and the material, the FRP, is flowing.
Thanks.
Yeah, me again. Sorry. But Ignacio, thank you, because we are also working on salvolysis and pyrolysis and also with the microwave. What I'm interested is by the solvolysis and pyrolysis, especially more the solvolysis, which temperature you are working?
Depends on the resin, but it can go from 180 to 250.
Yeah, okay.
Degrees Celsius.
Yeah, thanks.
So it works under pressure.
Yeah, it's clear. Yeah, otherwise.
By vapor pressure of the solvent that is.
Yeah, after solvent.
Yeah.
Do you have experience with the carbon fiber?
Carbon fiber, yeah.
Yeah, yeah, because this is completely other behavior, especially by the pyrolysis.
Indeed.
What the colleagues also ask for, which frequency, microwave frequency you are working on, and then you heat up the carbon fiber instead of the resin.
Indeed, indeed. You have there a better control, even better control on the oil products distribution, but the risk is that the tips of the carbon fiber can accumulate electromagnetic field, and they become even fused. So they can reach temperatures of 1200 degrees Celsius or even more.
And then it's not.
Then you are kind of destroying the carbon fibers.
You destroyed your carbon fiber.
Yeah, indeed.
Okay. Yeah. Thank you.
Welcome.
Thank you so much for the presentation. I just have curiosity. Like, did you perform other assessment, like other technique to verify if there was some residue on the fibers apart from like optical microscopy or ACM? I don't know which one.
SEM with EDX. So we can determine exactly the metals present there.
Yeah, and maybe
amounts.
like thermal, any thermal, like TGA.
Yeah.
Okay, that's good, because sometimes with ACM it seems clean, the fibers, but it is not. There's also. Okay.
Yeah, you can check it out in the papers.
Okay.
I want it to be the least scientific possible, given the audience here, but you can check that. Yeah.
Thank you.
Thank you very much indeed. Yep. You made it very understandable for everybody, even ignorant people like myself, shall we say. Just before lunch, we welcome here Harold van der Meyer, who a lot of you know already. He's presenting about Beyond Design, End of Life and Decommissioning for the Future.
Thank you, Andrew, for the introduction. We just heard just before lunch, but I'm sure that Andrew keeps the time to it. My presentation is about a project which exactly kicked off 1 year ago. It was a project called Circle for Wind. It's a Dutch national funded project with a complete supply chain, and it's a 3-year project. But first, short about TNO. We are the largest research institute in the Netherlands. We work on a lot of different topics. I'm from the group from Energy and Materials Transition, and 4,500 colleagues But more important, I think the TNO strategy of the mission is that we provide innovation for strengthening the market position. And for the program where I'm in the lead for circular wind farms, we have a focus on different things. First is the design for circularity. Second is the advanced recycling technologies, like for instance, not only the blades, but also for the magnets. And we also have often an orchestrating role, because especially for this end of life, now we heard a lot of presentations that we said we need a hub, a consortium to make things happen. And we also support the government, for instance, for tender requirements and for the roadmap on circularity. Okay, the project. Project is focusing on thermolysis. Yeah, thermolysis, it's for us a combination of pyrolysis and combustion, because the focus is on recovering a clean glass fiber to use it as feedstock for new glass fibers. And we have to make it feasible and commercial attractive, we need to reduce the cost for the pre-processing and the logistics, because that's the majority of the cost at the moment. The focus for us, for the Netherlands, is now on the offshore. Of course, we have a lot of bulk of used blades, but for the offshore, there's high cost and also some uncertainties. And for us, if you see the supply chain, the process starts with smart cutting of the blades to do it as localized as much as possible. Secondly is the thermolysis. We have our own facility at TNO where we can optimize the process together with Renewi, that's the large recycling company, and they will implement this in the future demo plant. The recovered fibers will be processed by Sibelco, and Sibelco gives the stamp on it from now it's applicable as feedstock for glass fiber. And Envalior will produce glass fiber of it, mix it with virgin fiber, and at the end we look for different applications. Suzlon is also on board and for the expertise on the materials, and also look for future solutions to make it happen. Today I will present the decommissioning cost and emission and the LCA. My colleague Chen is in the audience, he's the specialist on the LCA. But the short impression, I will explain later about the tools. The picture in the middle is an example of the cutting of the blade. We started with a very old blade because that's the biggest challenge with the pyrolysis, because there's PVC in it. So the smart cutting already focuses on excluding the PVC. First challenge. And second challenge is the shredding. We use different shredding options, different size of feedstock. And on the right, you see our pyrolysis facility, small batches, lab scale, and we produce now the first batches which will be tested at Sibelco if it's according to the requirements. For the decommissioning, we developed within TNO a tool to optimize the planning and the cost of offshore operations. So this tool involves the input is MetOcean data. We have a large database of all types of vessels, work orders, and so on. And we implement this in installation, operation, and decommissioning. And for this project, we use the decommissioning tool, and we include different aspects and also the different seasons in the year. So we'll give some examples later on, but for the project itself, we are focusing on the first generation wind farms. For us, it's the Princess Amalia wind farm. It's a wind farm. It's at the end of life now. It's V80 turbines, 60 V80 turbines. And the present, that's the granted by Vattenfall, is the Zeevonk wind farm. It's a bit further away from the coast, 2 gigawatt. And yeah, the exact type of the turbine is not decided yet, so we use the NREL 15 megawatt reference turbine. The facility of Renewi for the recycling is in Moerdijk. I'm not that good at the pointer, but you can reach it with inland vessels or trucks. And in this case, we optimize. We say it's best to transfer it, the blades in the harbor of Rotterdam, and bring it by inland vessel to Moerdijk. This is the scenario we used. So for offshore, we used for the Zeevonk, so not for the Amalia, for the Zeevonk, the largest jack-up vessel at the moment, because it's needed to lift these 15 megawatt turbines. And this is a reversed installation. A reversed installation means that we use also the jack-up vessel to transfer the whole turbines to the port. When it's reached the port of Rotterdam, the blades, 120 meters, are too large to bring it in an inland vessel, so we have to cut it. We decided to cut it once or twice for transport. Then the transport by inland vessel, a large Rhine vessel, will bring it to Moerdijk. They have their own harbor, but also with a certain capacity, so that's why the size of the segment is limited. Over there it will be pre-processed and shredded, and on the same site is also the pyrolysis facility. Then, after the thermolysis, the reclaimed glass fiber will be brought by trucks to the Sibelco and then to Envalior in Antwerp, so this is the full schedule. For the offshore cost, we limit until the thermolysis process. For the LCA, we look for the complete process. We have also a creative solution, because we have the reversed installation solution, but we also looked for the option to pre-process blades offshore. For the smaller turbines, for the nearland, it was not interesting, because it's no use to do these expensive operations offshore. But for the large turbines, and I will show you in the first simulations, that it's useful to segmentize, to cut the blades already offshore. Because then you can use a smaller crane jack-up vessel, much more expensive, less expensive than the large vessel for the turbines. The cutting tool is an implemented gripping, lifting tool and a cutting tool. So it's patented. So the next step is to see if it's feasible to commercialize. What does it mean for the whole process? Is that we can skip the onshore processing in the harbor. So it means that we can directly transfer it from the jack-up vessel to the inland vessel. So we don't need storage and facilities in the harbor. That's a big cost reduction. This is the first simulation of the reversed installation. This is only the removal of the turbine. And it's interesting to see that there is a large difference in cost in the different seasons. It means for the Princess Amalia wind farm, there's a lot of turbines, so there's a lot of transit. So it means that the campaign is relatively long. So it means that in the months that there's more wind and more sea states, and it means that it's more expensive. So it's very useful to plan your session to campaign in time. And if you see for the cost, if I compare it later on with the larger wind farm, that they are relatively high for the small turbines. So it's quite difficult to find a contractor at the moment, because it's not always so commercially attractive to remove a small wind farm. And the cost is majority the jack-up vessel and the uncertainties of the weather conditions. That's the orange pie. Okay. No, yeah. You have to believe it. But it's important for this is that we use for the onshore, it's only a very small part of the whole decommissioning. So it's different from onshore, that for the offshore, it's included in the whole business case. So it means that we have only 1% of the cost, and also 1% of the emissions is the onshore operations. And onshore is the inland vessel or trucks, but in this case it's an inland vessel, and the shredders and the cutting facilities. If you go for the next one, and that's the Zeevonk, and you've seen that the costs are much lower now per megawatt, and also it's more stable over the full. And it means that this campaign takes also quite long. So it means that especially for the reversed installation, that these large, very expensive jack-up vessels, they use it also for transporting it to the harbor. And that's the discussion we should have now with contractors. Is it useful to invest in this? Because it also reserves your jack-up vessel for a long time. And there's a lot of uncertainty. That's the green of the orange pie on weather conditions, because it's further offshore. The jack-up vessel has certain limitations, and also the emissions are comparable. Now, it's interesting, we see for the same large wind farm that we use this offshore cutting solution, that we've seen that the cost can drop in some periods of the year, and it means that you can use two campaigns simultaneously. You have the blade decommissioning campaign with the smaller vessel. The smaller vessel will lift it to a barge and bring it directly to the harbor, and the large jack-up vessel it keeps in the wind farm. So that's more attractive. The costs are lower, and also the emissions are a bit lower because a large vessel consumes a lot. For the emissions, by the way, we used the normal diesel, and you've seen in the environmental impact assessment that we used only the situation for this consortium. So we asked all the consortium partners. We have a partner who do the cutting, we have a partner who do the transport, the thermolysis. So we have exactly the data we need. And the focus is on the different scenarios. Now I present only 3 scenarios, but we have more scenarios within the project. And the focus is on the CO2 equivalent for giving the greenhouse gas potential. We use the standard database and also standard methods, and the output is the global warming potential. And I've heard before saying that there's a lot of variety in LCA results. Keep it in mind, there's also an IEA Wind Task 60, and that's focusing on normalizing this LCA specifically for the wind. It's interesting also for the decommissioning, because then it's easier to compare, and we try to implement this also in future tenders. Interesting, the results we used as benchmark the Vestas V80 blades from because they were used in the Princess Amalia wind farm. And you see that it's already 1/3 of reduction by using this recycled fiber. For this, I have to mention that the recycled content is 17%. It's quite a challenge. We learned also from the decom blades that it's the volumes for these glass manufacturers are really large. So 100% recycled glass fiber is not feasible. So, but you see that's quite a lot of impact. And if I go for the next slide, then you see more detailed breakdown of the actual cost. This is, by the way, only the glass fiber production. That especially for the production, you see there's a large amount of the electricity. For this case, in this case, we use the electricity mix right at this moment. I think it's 25% of renewables. And for the future study, we also look for in 40 years, because the Nederwiek wind farm will be granted for 35, 40 years. And then the energy mix will change, and also the fuel. So we look now also in the future for what's the effect on the LCA. Now you see also a very large contribution of the decommissioning. So it means also if you focus on optimization of your offshore operations, focus on other drivetrains, more clean fuels, that it also has a large impact. And the pre-processing and the onshore logistics, the inland logistics, it's not that high in cost and compared to it. So in the future you will see that the owner of the wind farm will tender, write a tender for decommissioning, and then it's important that we find a consortium we can cover this on. Final conclusions. First conclusion is about the decom cost. An interesting outcome is that the first generation wind farm is relatively expensive to decommission. And you see that for this wind farm it's only 120 megawatt. It's about 26 million, but there's a lot of variety in the different seasons. If you compare it to the larger wind farm, like the Nederwiek, then you see that it's quite a reduction per megawatt. And it's also, we discussed this a lot with contractors, and they say that nowadays vessels, they have a large capacity. It's not useful to use them also for these small turbines. When I started with this wind farm, when I started my career, it was a very large turbine. Secondly, it's the blade cutting option. Now it's positive, but a lot of assumptions. That's my remark, because we have to do quite a lot of work to be very specific. And the emission is predominantly the jack-up vessel. So not the inland vessels, but the jack-up vessel. And conclusions about the LCA, and that's my last slide. And you see that the electricity is key. So it means that we also focus, of course, on the energy transition, but it's also very important for the overall SCA that we focus on the electrification to change this energy mix. That's more a push for the government. And the production of the recycled glass fiber, if you use this in a new blade, it has about 30% of a lower impact. So that's quite significant. That's the benchmark for the V80 blade. We also look for the larger blades for them. And the pre-processing, the thermolysis, the transport, that's relatively minor compared to the other, but it's still very relevant to optimize it, but to optimize it more from a cost perspective. So the next step within the project is that we look for other scenarios, also the onshore transport, and look for the future scenarios for the different energy mixes. Okay, thank you for your attention.
Thank you, Harold. Over here. A very innovative way of cutting them offshore. Is there a way to actually capture the sawdust that's coming from the cutting there, or do you just let it blow away?
No, that's a very good one, because it's not allowed, because we never can sell this if there's microplastics or debris or powder coming from. So we look for now already for different cutting techniques. So we look for water jet, for wire cutting, but every system needs this capture system, filtering system. So it's still nice idea, but a lot of work to do to make it possible to do this offshore. But there's already interest, because you save a lot of cost in crane capacity, and especially for the offshore turbines, we expect worn out. So the dismantling by debolting, it's you can save a lot of cost if you can cut it. But like you said, the powder, and there needs to be a system under development.
Yeah, Harald. Many thanks for the presentation. Again, I have a question about your cutting on the turbine. It's quite interesting, but even you cut it in 3 pieces, it's very large pieces, especially the middle part. And I know that from Germany it's quite difficult to transport such big parts. Is there the idea to cut it again then on the harbor, or you can transport in Netherlands such big and such wide parts, especially?
That's a good question, because in the beginning we wanted to cut it in 12-meter pieces to transport it easily by truck. But for this, we checked the harbor in Moerdijk, and the harbor quay is quite long. And then a barge or an inland vessel can also transport. But you're right, if you save costs in cranes and onshore logistics, it's better to cut it in smaller parts. But in this case, we wanted to have the operations offshore as limited as possible. So
Yeah,
that's
clear.
why we cut it in two parts. But yeah, there's still a lot of optimization to be done.
Thank you.
Yeah.
Any more questions? Harold, thank you again, yes. A big hand for Harold, yeah. Everybody, it's a busy morning. I'm sure you've got grumbling stomachs and so forth. There was great catering yesterday, and Teresa tells me the catering is no less today. It'll be very good. So if you'd like to go down at your leisure down to the restaurant, and the food is ready there for you.
Am I audible? Yeah, I'm audible, right? Great. So, yeah, this room I've got to move. Change the battery from you.
Good afternoon, everybody. Welcome back. I hope you haven't overindulged with your food and make you sleepy. I'm sure you haven't done that, no. So we start this afternoon with a presentation from Blades to Build. This is a joint presentation, and we welcome onto the stage Duc Thanh Duo, Natalia, and Anna. Thank you.
Good afternoon. I'm Natalia Lushnikova. I'm a postdoc of Technical University of Eindhoven. And with my colleague, Dr. Tao, the researcher of Holcim Innovation Center, we present our project Blades to Build. It's working, but I don't hear myself. Recycle, repurpose, and reuse end-of-life wind turbine blades composites. A couple pre- and co-processing demonstration plant. Our colleague, the project manager, Anna Teresa Lima, could not, unfortunately, join our presentation. But she presented our project 1 year ago, more than 1 year ago, at this forum. And we will shortly outline the updates, because our project lasted 3 years and it's almost close to the end. The key ambition of this project, I will not focus on all the work packages, but the key ambition is implementing a demonstration plant for circular use of end-of-life wind turbine blade waste, based on 3 options of circularity. There is repairing with blades with minimum refurbishment and processing. There is also repurpose of waste of the materials in new construction materials, like concrete, asphalt mixtures, and other composites. And set is recycling blades, waste, and glass fiber, textile scrap from the wind blades manufacturing in cement and clinker co-processing. So we focus now mostly on recycling. Our part as Technical University of Eindhoven was basically coordinating of work package on development new circular building materials. But we have a big consortium which consists of 13 partners. There are 4 universities. You see here the Technical University of Denmark, Technical University of Athens, Greens, and Aachen University, and industrial partners from wind turbine blades industry and construction industry. And also Global Consultants Sustainability, which basically promotes our project. So the concept of the project is definitely avoiding landfilling, which you heard a lot, that landfills are banned in Netherlands, new landfills, and repair the blades or reuse them for other purposes, as well as repurpose for new construction materials and recycle and use as alternative fuel for clinker. So briefly, what we did during our mostly last project here, we worked a lot on characterization of different waste. We mostly worked with mechanically shredded waste from wind turbine blades, but also chemically treated and thermally treated waste by solvolysis and pyrolysis. They were developed circular building materials. I will not outline all the mixed designs and all materials we developed in the consortium, but the key ones, and there was built a construction demonstration plant to recycle end-of-wind turbine blades. And there were implemented pilots, industrial pilots on concrete pavements. There's demonstrators. So regarding this plant, we, in 2 weeks, in less than 2 weeks, with all consortium, we meet in Madrid for annual meeting, and we will have first visit to this plant. So we all really excited with that. I will talk a bit about our academic part, and my colleague Tung will more out like lab scale materials, and my colleague Tung will focus on industrial scale outcomes of our project. We worked a lot on cement-based materials because according to marketing analysis, which was done in first year, one of the most promising application area for the waste is cement-based composites like mortars and concrete. So this is the results of a test of mortars reinforced with wind turbine blades waste. There was developed microstructure analysis and X-ray computed tomography to see the distribution of the particles, wind turbine blade waste, the pores in this composite, and unreacted clinker. They were tested different materials, like different waste of different size, from 0.063 millimeters to 8 millimeters. And you can see in this graph, like with increasing the particle size, we have change also in unreacted clinker and change in porosity, reduction, for instance, porosity. There was also prepared a paper and published. You can go to this link and read it, on effect of wind turbine blade waste on cement hydration and gel structure. It related to powder waste, which were grinded, mechanically shredded and grinded, for polyester and glass fiber based. So basically it's a kind of competing interaction, positive with glass and fiber and negative with polyester resin. So our colleagues model it and describe basically this chemical process from DTU. In TUE, we focused on developing like two directions: the cement-based composites and mostly concrete, and polymer-based composites. So here you can see basically on the left side the images of the waste we used. So as you saw many pictures today and yesterday, that definitely these wastes are heterogeneous. We received them from our partner PreZero, which prepared and shredded it with different sizes, and we just did sieving. So we have fiber-like particles, we have flakes, we have powder. And basically we worked on replacing partial replacing in natural aggregate, fine aggregate, coarse aggregate, at different sizes of the particles, and partial replacement of cement with powder particles from this waste and also fibrous-like particles were used as reinforcement. So we have this hybrid effect of reinforcement and a replacement of the components. And we used standard methods for mixed design of concrete, and also method of optimized particle packing, because we understand that these wastes have lower density. They are heterogeneous, so it's very challenging to get optimum, like higher density, higher packing in this mixture. And here you can see results of mechanical tests, testing splitting tensile strengths, compressive strengths at 7 and 28 days. They are also compared to different dosage of waste. So from control is 0 and up to 5% by total weight of the concrete. and the results of elastic modulus at the bottom part of the right. So definitely because the density of the waste, they're heterogeneous, is lower. So we observe the reduction of elastic modulus of this concrete. We also worked on other materials like lightweight aggregates based on this waste. And there's another big direction from our side. This is polymer-based composites with polypropylene and coupling agents. So we here see the results of mechanical properties of 3 cycles, basically, of recycling these composites. There we're comparing of these mixed designs, like with recycled wind turbine blades, shredded wind turbine blades, and virgin fiber, which we receive from our industrial partners. So we can see on this same image, we can see that definitely if we use coupling agent, we improve adhesion of waste with polymer matrix. And we have similar properties of recycled composites. They have similar properties, mechanical properties, compared to virgin composites, even after 3 reprocessing cycles. So, and 10-15% of virgin glass fiber can be replaced by 25, even 50% of this recycled shredded material. Our partners in Aachen University, they also worked on different mortars, cement-based mortars and concrete with different shredded waste. And here they limited their dosage with 1% by volume of waste. The most promising result, for instance, for CMOD test is for residual fractional strength for 0.3 dosage. And they basically replace the aggregate with this waste. We didn't work, so what I now described, it's only related to wastes mechanically treated, but our partners also work on thermally and chemically shredded, chemically treated fiber. For instance, they developed like pilots set up for supercritical solvolysis of waste with acetone and water. So now it's definitely only on the lab scale, and we can get comparatively very clear glass fiber from that. With this chemically treated fiber, our industrial partner Acciona make lab trials of asphalt mixtures and see really good results when we add 1% of fiber content. So here we see different properties, water absorption density with control sample, and the second bar is with 1% of fiber. So you see that they are really similar or even higher. And there also was set like powder grounded materials, waste were tested for pozzolanic activity, and here is describes of made Frattini test for this testing, defining this pozzolanic activity, and comparison of hydration products. So mostly there is comparing with treated and untreated, heat-treated materials. So mostly untreated, just mechanically grounded material showed higher CSHGL and carbonate formation. And a heat treatment sample with heat treatment waste, it has reduced portlandite and carbonate phases. For industrial trials from PreZero and Holcim and Acciona, I give floor to Dunk.
Thank you, Natalia. Good afternoon, everyone. So I take the charge to present to you now is upscale, meaning that after 2 years screening on the opportunity to figure out where we can recycle or recycle the end-of-life wind turbine blade waste in construction materials. We decide that only in ready mix, so in the concrete, that we can scale up. In order to scale up this, so this is a typical process to strip and then to grind, to obtain from very, very big piece until the aggregate size that can be integrated in our concrete. And then in our innovation center of Holcim, based in Lyon, France, we try to use our two branded technologies, EcoCycle, where we try to use the CDM, so construction and demolition materials, with the use of EcoPlanet, so with the low carbon cement to make our concrete. Why EcoCycle and EcoPlanet? Because we have already branded solutions that are now on the market for more than 40 countries for EcoCycle and 34 countries now, with a very, very ambitious objective. Like in 2030, we want to recycle 20 million tons. So to keep an image to compare it to the volume of the wind turbine blade waste in 2030 is around 300,000 tons. So meaning that with these technologies, if we can put it in our EcoCycle, we can absorb easily the total volume of the end-of-life wind turbine blades right now, 2026, and can be much more in 2030. And integration of wind turbine blade waste in our concrete, it was not easy because a lot of trouble in the workability, in the degradation of type of mechanical behaviors. That's why you can see in the picture we limited at 1.5% in terms of volume in our concrete. And it doesn't matter because with this we can absorb easily 300,000 tons of wind turbine blade in our concrete. So we don't need to go higher than 1.5%, and we can be sure that we can absorb completely this waste. So this is the first trial that we deployed our EcoCycle wind. So either for my colleague Francisco is for the Lakis repowering plant in Europe, where they want to build an industrial platform to store all the emission piece, so blade as well. We supplied around around 8 cubic meter of concrete, so 44 square meter of slab made of EcoCycle with a wind turbine blade waste inside. And we can say that it's the first wind farm in Europe that we can reuse our structural waste to build the new infrastructures. Thomas, could you? So we have prepared a small video that you can take a look about the top side, the challenges. It's in Spanish, but I think that with the subtitle we can.
En las cuales pues, esa trituración se mete dentro de la masa del hormigón, sustituyendo parte del árido. Para desarrollar conjuntamente la dosificación hemos contado con la colaboración de nuestro laboratorio central situado en Lyon, el Holcim Innovation Center, el cual pues, bueno, hemos desarrollado una fórmula para que el hormigón fuera capaz de mantener una trabajabilidad y una durabilidad conforme a la normativa vigente de aplicación. El hormigón es un material circular, se puede reciclar 100% y tantas veces como queramos.
Para Holcim España, la sostenibilidad y por tanto la circularidad no es solo un objetivo, es un valor. Prueba de ello es nuestra plataforma de materiales de construcción Ecocicle, que incluye todos los materiales que fabricamos, que incluyen en su composición al menos un 10% de materiales procedentes de demolición y construcción. Por eso estamos encantados de participar en el proyecto Blaze to Build, que supone un claro ejemplo de circularidad.
El gran objetivo de este consorcio, que está formado por 14 empresas y universidades, es buscar una solución circular a las palas eólicas, que ahora mismo es un problema que hacer con ellos. En el 2024 reciclamos ya a nivel mundial 6.5 millones de toneladas de material de construcción que volvimos a usar en nuestros productos. Nuestro gran objetivo es hacer 20 millones de toneladas de material de construcción y demolición en el 2030. Y este proyecto contribuirá a ese objetivo, ya que las palas eólicas están consideradas material de construcción y demolición.
Los parques eólicos llegan a su vida útil en torno a los 25 o 30 años y de las turbinas eólicas se pueden reciclar hasta el 94% de ellas, salvo por una circunstancia, una excepción muy llamativa, que son las palas eólicas. Las palas eólicas son materiales compuestos y son difícilmente reutilizables, salvo que sean reusables en otros parques. Endesa, preocupada por este tema, pues se introdujo en el consorcio Blaze to Build, que dentro de la convocatoria Horizon de la Unión Europea tiene una financiación de más de 12 millones de euros y en el que están incluidos diferentes líderes de la industria como Endesa o como Holcim, la mayor cementera del mundo, y universidades y organismos de investigación de toda Europa, Países Bajos, Dinamarca, Alemania, Grecia. El consorcio Blaze to Build, además de dar una solución viable técnica y económicamente al tratamiento de las palas de los generadores que iban a ir a vertedero como residuo, también lo va a hacer viable a través de una planta que se va a construir en Castilla y León y que va a ser la primera planta que además va a tener financiación europea para el tratamiento de estas palas de aerogeneradores.
Thank you, Thomas. I'm running out of time, so very briefly for the latest slides. So in the next slide, you see that we have another Triton pilot made with Acciona. And then with these two Tritons, we got the prize for the Outstanding Innovation Award from European Concrete Pavement Association. And we are also on the finalist for the EDI award. It's some kind of sustainable economy award given by association in UK. This is a big picture, say that just what is today and what is tomorrow. So we have Prezero, who is ready to street and to supply to us around 6,000 tons of treated aggregate wind to be built waste per year. It started, I think, at end of this end of January and beginning of this month. And then for the boat job site, we conducted the life cycle assessment with University Aachen, so it can be used to for the future trials if we need any CO2 evaluation at the end. This is some this QR code to follow our project, and then the activities in terms of communication. Yeah. I think this is the end. Thank you for your attention. We are happy to answer to your questions if you have.
Hi, hello, thank you for the nice presentation. Actually, during my PhD, I also doing in cooperation shredded the GFRP with the inorganic polymer, which is recycled from industry waste. Well, for your project, I have two questions. So first, is the pure GFRP shredded material used for this project, or it will contain some wooden part?
No, we used only mostly glass fiber, reinforced plastic. So no, there's no wood, almost no wood. So it's already like sorted and shredded by our industrial partner Prezero, which you saw on this. Yeah.
I asked this because I know for the wood part, sometimes it contains the lignin and also cellulose. This will hinder the hydration of the cement. And my second question is, have you ever done some long-term durability study? Because for the cement, during the curing of the cement, the water in the pores has a very high pH value, which will cause some alkaline degradations on the glass fiber.
No, like we do leaching test, for instance. We do alkali silica reaction test. We did shrinkage for concrete. So we don't see basically these problems because basically we don't work with like pure virgin fiber for concrete, you see. So it's basically glass fiber coated still with polymer. So we didn't have these issues with this concrete. Probably you can add something to it.
Yeah, we did also test on the aggregate scan, and we didn't observe any SAR trouble. So that's Natalia's explained that maybe the reason that cover the fibers helps to avoid this phenomenon. Yes.
Okay, so there is no corrosion issues for using.
And you can see that with the very low percentage inside, it cannot create the linked weak points that can damage the performance of your concrete, even in the long term, yes.
This gives a promising sign for using this technology in the construction field. Thank you.
Thank you.
Yes, thanks for your presentation. Hi. I'm going to be a bit critical because I'm shocked that there's a study that's funded with 12 million euros on European money. And you're talking about repair, repurposing, and recycling, and I only see recycling. So are the other two parts not presented, or are they still under research? Because I'm quite interested in that part.
They are not presented here because of we don't have enough time, because there are a lot of big study on repairing also. And other parts you probably can add on that. Well,
Yeah, I think this part is carried out by Leon Lasky. He's very well-known researcher from DTU Wien. He did a great job. He released so impactful papers on this. We cannot include in this, and we want to show just from the initial side what is the most scalable solution for tomorrow or today, because tomorrow is already late. So for today, we can see that is in the ready mix from our studies. Yeah.
Okay, and can you share those results also with us?
For sure, yeah,
okay.
for sure.
And one other question I had is looking at the asphalt that you produce, where you add 1% of glass fiber to the asphalt mix. What is the end of life for the asphalt, and can you still retract the glass fiber from that, or is it lost forever?
Well, the asphalt, the bitumen is some kind like, we can say, I'm not expert in the polymer, but can say that it's thermoplastic. So when you hit up 150, you can recover aggregates, fibers, and the bitumen. And it is the way that people now today, they do with the recycling of the asphalt roads. So they remove it, they reheat at 150, they add just 1 or 2% of bitumen to make the new asphalt concrete. So we can think that in this case, we can, if we go to the higher scale, because up to date it's just in laboratory scale, if we go to higher, it will work like you add the fibers in the asphalt. And in the asphalt, we have also some experience on the single recycling. Single recycling, you have the glass fiber inside for the roofing. And then in Canada, I know that they use to recycle the singles in the asphalt, and after that, they recycle many times that they can, because the only limit is 150 degrees Celsius.
Okay, well, looking forward to see the paper.
Thank you.
I had a question. I don't want to be as critical as yours, because at least you're recycling. It's much better than burning. So I understand, lifting it up the value chain is fine. My question here is, Natalia, you mentioned the aspect ratio, or the morphology and size distribution of the aggregate. If you use this wind turbine waste, is the sort of strength increase, elasticity decrease, is that, if you compare it with stone aggregate, is there really a striking difference because of this aspect ratio and the sort of length to diameter ratio? Does it justify sort of kicking out stone aggregate, which you normally would use? And then the next question is, how much more expensive is this eco cement?
Well, we have, it's a good question because we see definitely the impact basically of the length of the fiber. So for instance, if there is actually higher length and you see this reinforcing effect. So for instance, for tensile splitting test for flexural strength, we see this bridging gap effect when we are testing it. So probably the value of the strength itself is not significantly a bit higher, but still you can see the cracks, for instance, the smaller because of this bridging, as well as for fine powder at the partial replacement of cement. We see some positive effect for several percent, like up to 5%, for instance. So it's more definitely not physical, but chemical, but probably physical because it can be more compacted. So basically what we see now. So for flexural strengths, mostly for deformations, we see this effect. Thank you.
I had a question as well. Thank you very much for the presentation. There was one slide where you mentioned CO2 reduction in comparison to regular concrete, or at least something like a reference. But it was also, no, I think it was a different slide, but it's okay. It was also mentioned that it was in combination with another technique, something with eco cement. So how much of the recycling of the fibers and replacing the aggregate, how much of that number of that CO2 reduction is because of that, and how much is just because it's a more sustainable concrete altogether?
Well, we can see that during the pre-processing or on the treatment that you added to treated waste, you release the CO2, right? And you increase the cost. And the only way that we can keep it similar to the ordinary concrete or even lower, like we have to add the low carbon cement that we call EcoPlanet. So EcoPlanet is a new cement that can have less than 30% of CO2 emission during the production of the clinker of the cement, because to be honest, at the end of the day, it's a grinded cement that we mix with other SCM, so supplementary cementitious materials. So with this secondary cementitious materials, we will not hit the limestone and the gypsum until 1,450 degrees Celsius. We just bring them, we grind them, so that's why we keep lower CO2 emission compared to the ordinary cement. And we use this, we put it in the mixture with winter blade waste that have a positive CO2.
So you use the eco cement technique to compensate for the glass fiber.
Exactly, and this is a big difference because in our mixtures we have many levels to play with the CO2. I saw yesterday and today through different presentations, if you have the only one product, unique product, without any possibility to play with the other components that you can earn in terms of CO2 credit, at the end of the day, you will have positive CO2.
So isn't it then just, why not just use the eco? What are we gaining by mixing the fibers into it? Why do we do that?
We have this because in EcoCycle, we used to use the CDM, so we crush the concrete here, all concrete, turn it in aggregate, put it in the But when wind industry comes to us saying that I have blade, have you any solution to recycle it? So we have this, so this we have to answer to the customer, yeah.
Thank you.
Just to add very shortly, regarding carbon footprint and other parameters, we have separate part on LCA. So they were we just received the report, so they were analyzed 5 different scenarios compared to the classical concrete with natural aggregate. So definitely still the largest hotspot is still cement. And for waste, it's basically the transporting. So if you need to transport very far, like, so it's also increases carbon footprint. So we need also to consider that.
Thank you for a question. Yeah, please go ahead.
Thank you very much. The quality of the eco-cycle, is it also to carry dynamic loads or just simple concrete?
EcoCycle and EcoPlanet, they are commercialized now, today, so we have to respect all the standards in terms of Euro code, for example, Eco 2 for the structural materials. We don't want to compromise the performance with the circularity. We want to go both. So, for example, EcoCycle, we are working now in the parent, a new way to process the recycled aggregates that is called some kind like the advanced crushing process or smart crusher, if you have heard about this before.
Yeah, so my question would be, has that product the quality to be filled into my foundation or not?
Yes, you can call, for example, if you are based in Germany, you can search on the Google and maybe in 50 kilometers around from your house, you can find our company to supply you these materials, yes. Even for the EcoPlanet, so for the cement, yeah. It's commercialized, yeah.
I have a curiosity. You are an expert in construction demolition waste. Do you find composite material, I guess so, in this stream? And do you see any opportunity to find synergies between the composite present in the construction demolition waste and coming from blades?
Yeah, well, basically here, yeah, there's also like 10% of recycled material. It means like 1% only waste, shredded waste, wind turbine blades waste, and the rest is basically recycled concrete. So this is a combination of different construction demolition waste.
I was referring to the composite in construction. Glass fibers used in construction, if you find the stream.
You mean that repurpose, like you use like the element in the structure, right?
No, you need virgin fibers in the concrete instead of the reused fibers. You can also put virgin fibers in the concrete.
Well, virgin fiber is on concrete is traditional way. So all people, yeah. The most difficult is the recycled fiber because even with the cleanest and the most advanced technology, you weaken the fibers and say that reinforces fiber concrete. You have to use a premium fibers to reach it on the area. So sorry to say about that, but recycled fibers in the concrete to improve the quality concrete, I think is still a big dream. So it's from my point of view. Yeah.
Thank you very much indeed. Fascinating to see this is happening like this, and it's a different way of thinking and so forth, and well done. Thank you very much. Big hand. We welcome forward Anurag Bansal. He's the head of strategy and innovations at Acciona. He's the driving force in that company, to say the least, and he's adding to what a lot of us already know regarding challenges and strategies for using recycled wind turbine blades in construction.
Thank you, Andrew. Am I audible? Yes. Great. Good afternoon, and thank you everyone for giving me this opportunity to share some of the challenges and strategies in using recycled wind turbine blades in construction. But it is not only limited to construction. Those can be used in other industries as well. So at Acciona, our philosophy is business as unusual. We believe that being a leader in energy transition, it is our responsibility to take care of the end of life of our infrastructure. We are a global company present in more than 42 countries. What makes us unique is our presence in the entire value chain of and infrastructure industry, from energy and water to construction and social infrastructure. With a team of more than 66,000 people and a turnover of 19 billion euros, we believe that we have the scale to make a real impact. So these are some of the figures. Now, if we see the scale of our company, even for us, when we talk about like transition from linear economy to a circular economy, it is not easy. It presents a lot of challenges. And today I'm going to present one such challenge. Now this is a real world example. In this, on your left hand side, you can see a wind farm that was constructed by us in early 1990s. Now in that time, we used 98 turbines to produce 78.4 megawatt. But then with time, the technology evolved and we have to repower. Now on the right hand side, you can see like after repowering, we are generating 84.4 megawatt, but with only 13 turbines, 13 modern turbines. So technically, that's a massive achievement. But when it comes to environment, now it creates a question. Now the question is, what to do with 294 turbines that are decommissioned and lying on the ground? And it is only from one wind farm. We are having lot many wind farms around the globe. So what to do? Because those are also coming to their end of life. So what to do? So answering this question is not easy. There are lot many challenges. So let me like take you through to some of the challenges. For renewable energy industry, some of the challenges are like normally they try to do landfill or they try to go for energy recovery through incineration. But those are not sustainable solutions. The second challenge is cost and logistics. Imagine you have got a huge blade, 40 meters, 50 meters, like the first generation blades, and you have to transport it to a recycling facility. Who is going to bear the cost? Who is going to take care of the logistics, whether you have got permissions or not? The third challenge is, like everybody knows, the composites blade, they are difficult to recycle. Other challenges, the technologies for recycling the blades are not having a technology readiness level of 9, like they are not at an industrial scale. They are still in pilot or in development stage. Then the end markets for the use of those recycled materials are even not developed. That is also one of the challenge. And then the regulations, these are also the challenge. And then these challenges are giving more challenges to the end users. So on the right-hand side, you can see the challenges for construction industry, and these challenges are coming from other industries also when they want to adopt a recycled material. The first thing is performance uncertainty. We don't know what material we are recycling, let's say. The blade, we don't have the passports, we don't have the materials. So how can we assure that the product we are going to make will meet the performance criteria? The second one is regulatory compliance. In construction industry, we don't have building codes. We don't have codes which help us to use recyclable materials. The third one is traceability and quality assurance. Again, as I mentioned, we don't have all the history of the blade, what materials were used, what process was used, how many times the blade was repaired, how it was decommissioned, and how it was recycled. We don't have those data. We don't have traceability. So how can we ensure a quality in a product? Then it comes to integration compatibility. Now, if you see, construction is a huge industry, but very conservative. When you try to use a new material, then it is not only the end user who has to use, it is the entire ecosystem who has to adopt. For example, the kind of jigs and fixtures you are going to use, the kind of machineries you are going to use, whether they are in a position to handle these kind of materials, a real experience is no. And the last one is like cost value perception. At the end of the day, everybody see what is the cost and what is the value that it brings. Now, some of the strategies which yesterday our colleague Gianmarco also showed, these are the typical strategies like which are to handle the retired wind turbine blades. So today in my talk, I'm going to focus only on repurposing and recycling. So when the company, the energy division, had this problem, so internally we were thinking, okay, how can we repurpose or how can we recycle? So they, instead of going outside the home, they found inside the solution. And for that, they contacted the Technology and Innovation Division of the Construction Business Unit. Now, this division has got more than 20 years working with composites. Some of the structures that this Innovation Development Department has done are like a bridge making use with carbon fiber. You can see a lighthouse that was made using carbon and glass fiber structure. We have got maritime structures. So we have got the experience of how to handle these materials, how to design a product with these materials. Because even the materials are good, if you don't know how to design, then the product will never be cost competitive. So now I will be taking you to some of the cases where we are demonstrating how we can get the value. So the first one is this surfboard that we have developed. It was made using a wind blade from a wind turbine farm which is in Australia. So what we did was we took the root section which has got the maximum fiber and we cut it in rectangular strips. Those strips were used as the main structural element of this surfboard, and then the skin, they were used from the part of the wing, like where we have got balsa, where we have got other kind of cores. So utilizing those, we developed this, this surfboard. Another example of mechanical recycling. Like in 2 days, I have listened a lot, like people were talking about what to do with the dust, right? So this is a perfect example of what to do with the dust. Now in mechanical recycling, whenever, like once you decommission a blade, the first thing is you cut the blade. A lot of dust is emitted. What to do with it? Once the part or the blade is cut, then it is further shredded. Now, during shredding, also dust is generated. Apart from that, there are particles which are less than 2 or 3 millimeters. What to do with them? So in this example, in this thing, what we are doing, all those dust and the particles which does not make sense for recycling, we take and we produce the beams using pultrusion process. And then these beams are used in our solar farm to replace galvanized iron beams. So here in this, you can see on the left-hand side, your right-hand side, this is a galvanized beam, and on the left-hand side is the beam that was made by us in polymers. And this beam is really, if you see, this is a torsion beam because the panels, they move with the sun. So there is a constant torsion load going on the beam. And with our development, we saw that adding those materials in a pultruded beam increases interlaminar shear strength. Like normally you can do pultrusion with conventional material, but that was not the goal. The goal was how can we reduce the use of virgin raw materials. So in this case, through this demonstration project, we demonstrated to our management and to the industry that those are not waste. If you design the product in a good way, you can get the value. And this is not theory. Right now, in this picture, you can see the beams that are installed. And this is the solar farm finished. And right now we are monitoring. Because something is what you design on paper, something is what you get once when you do a destructive testing, but the other thing is how does it perform in real life. So right now we are monitoring. Those data will help us to optimize the design. In this case, so I want to go back. How can I go? Oh, my present. Back, please. Can you back? 2 more slides. Yeah, the next one. Yeah. So in this case, you can see, as I was mentioning, one of the limitation is compatibility. When this wind farm, solar farm started, we had already purchased all the jigs and fixtures, and they were for the size of a GI beam. Now the beauty of composite is, if you know the material, if you know how to design with it, so you can make it of any size. Since we were not allowed to change the jigs and fixtures because they were already purchased, so in this you can see we match the outer dimension of the protruded beam. So in this way, we also demonstrated that when you use these kind of materials, you don't need to have special machines or equipments on site. You can do whatever is available. But that is not the limit. Now we have also developed another technology, which is value. It is the acronym for waste to value. So here what we are doing is, we have got the waste, which could be a blade or it could be any kind of composite waste. It is cut, shredded, and then it goes through a thermal degradation or thermal pyrolysis, and then we obtain fiber and pyrolytic oil, and then those are transformed to be used in some of the industries. I will show you some results of what we have obtained. Before that, I will show you a video of our value technology.
Acciona, a world leader in infrastructure and renewable energy, has developed the Wallu technology, a revolutionary process dedicated to the recycling of composite materials. Wallu sets a new benchmark in environmental protection, underscoring our commitment to the circular economy. The Wallu technology was conceived to reincorporate different components from end-of-life stage of composite materials, along with production waste from different sectors, into the production chain as raw materials. In the initial phase of this innovative recycling system, the polymer matrix of the composite material undergoes controlled heat treatment to separate the fibers from the matrix. Unlike other methods, this technology aims to retain the quality of these fibers while promoting the reuse of all their components. This is accomplished by maintaining a temperature below 600 degrees Celsius, avoiding combustion, and replacing it with heat treatment in an inert atmosphere. To ensure uniform heat exchange and a continuous material feed, Wallu technology incorporates a rotary system. Thanks to an opening in the center, the gases produced during the process can be evacuated, with most of them then condensed and collected for reuse as raw materials. The second stage of the process focuses on transferring the material to a rotating system, which rotates at a lower speed compared to the first stage. Here, the material undergoes heat treatment under a second controlled atmosphere. This results in clean fibers, free from organic remnants of the polymer matrix. The rotation of the equipment ensures homogeneity in the temperature distribution over the material, and consequently, the quality of the fibers obtained. At the end of this stage, both the reinforcing fibers and the condensed organic fractions are ready to be used as new raw materials, thus ensuring circularity in the composites industry. To minimize the carbon footprint and the environmental impact of recycling, Acciona has electrified the entire process and procured certified green energy for the supply. This complements the production of clean energy generated by the solar panels installed on the plant roof. The Wallu technology can be used to recycle composite materials from various industries, ranging from wind turbine blades, automobiles components such as car bodies, to aerospace and shipbuilding components. Through advancements like Wallu, Acciona is actively promoting circularity and the efficient use of resources, giving a second life to materials that have reached the end of their useful life. In this way, the company contributes to global well-being and steadfastly progresses towards a more prosperous and sustainable world.
So this is our pilot plant. It is working right now. Last year it was having a capacity of 1,000 tons, but because the demand was increasing, so we increased the capacity to 1,800 tons. And right now we are in construction of another facility which is 10,000 tons per year. So here you can see the different like sections of our technology, and then finally the clean fibers are coming. So some of you have already visited our plant. So since I don't know whether I'm allowed to show their picture or not. Yeah, yes. So Alessandro, yes, you were there. Few others were also there. You have seen the plant running. And in this you can see the fibers obtained were later transformed in the form of non-woven fabric. Before transforming, they were sized. And then we use those fabrics in manufacturing of profiles that could be used not only in construction, but in other industries. Now I will show you one more example. Now here you can see on the top is the non-woven that was developed from the recycled fiber obtained after recycling. And then, can you please start the video? So here you can see that non-woven is being used in pultrusion for manufacturing of profiles. Y Mónica, ¿sabes? Este non-woven es de retales. Yeah. So this is the non-woven that was used to produce pultruded profile. On the right hand side you can see a plank. This is of the same dimension as a plank that is used in a wind blade. But right now our objective is not going into the plank for a wind blade. These are the flats that will be used in cable trays, and those cable trays will be used back in the infrastructure for solar and wind energy. Yep, some other kind of profiles also we have manufactured using this technology. So the limit, there is no limit, like it is only imagination. Apart from these demos, we are also participating in projects. For example, before Natalia, she was presenting Blades to Build, so we are a partner in that project. We are a partner in Redol. In this, like we are talking about construction and demolition waste. Right now we don't have towers from first generation which were made in concrete, but we know that they will be also coming. So we are tackling those problems in this project. We are a part of Refresh. So my colleague Daniel is going to speak afterwards, so I'm not going to say more on it. Daniel, you are going to talk on it. And finally, before I end my presentation, I would like to say that circular economy is not always round. We have seen that sometimes it is flat, it is straight, it could be in the form of sandwich, or even it could be in the form of Snickers I am wearing. So in these Snickers, actually, it was the sole in which we use all those powders which are generated when you cut a blade, or all those 2 millimeter, 1 millimeter fractions of composites which nobody wants, but they are generated during shredding. So this is also a perfect example of 100% of the material that we get from a blade could be used. It is not a waste, it is a valuable material. Thank you.
I think you've answered all the questions in your presentation. That's tremendous, Anurag. Thank you very much indeed, yes.
When we buy the Snickers.
I bought them before, while I was coming to Amsterdam. 2 days back, El Ganso has an outlet in Madrid airport. There you go. So there you can, or you can go to city center. Yeah. So they have the outlet, you can buy them. All right. Thank you.
I'm very pleased to bring forward Daniel Crescenti. Daniel's been working hard over the years on the Refresh project, and he'll bring us up to speed on the progress that's been made there, scaling up sustainable end-of-life solutions for blades. Daniel.
Thank you. So, I will give the overview on the Refresh project I'm coordinating, in which also Acciona and Thirse are involved. So a brief overview on the project, but it's something I have already presented last year, at least the overview. So for the ones who doesn't know about the project, it's a consortium composed by 11 partners from different countries. So we count waste recycling and remanufacturing companies, engineering companies, and we are the coordinators located in Italy. So just to give the timeline, the project started in January 2023, and the first phase was like a design phase. Then we went to the goal milestone, and then, sorry. Okay. Oh, wrong button, sorry. And now we are in the deployment phase. So, and in the last year of the project, actually. So, yeah, pretty important result to show now. Okay. Briefly, the concept. So, the concept is to recycle the dismissed wind blades from the decommissioning till the end product. So, we cover the whole value chain. And we use different recycling processes, and everything is governed by the decision-making tool, which will be an AI smart tool for the traceability of the information of the wind blades that are decommissioned and then transferred to the recycling processes. The goal is to provide an accurate set of information and to improve the quality control of the recycled products. So we can have like a digital passport for those products. This is the slide Anurag showed before. I will navigate through this refresh value chain, explaining all the actors and partners involved. So we start from the first one, so the first phase, the actual decommissioning. So this first phase is performed by our partner Etat Neuf, which is from France. And the idea is that we have to cut the wind blades to improve the logistic aspects, because it's difficult to transport actually the big wind blades. So we have to cut them, but in a smart way, because those wind blades are the feedstock for the recycling processes. So without a smart cutting technique and idea, it's all useless. So what's smart cutting? With precise shapes, panels, and the idea is to cut the wind blades in order to use them for their reuse, the repurposing, their use, or the recycle. So that's why we speak about the smart cutting, and you'll see in a minute also why this is very, very important. So this is also other part of this process, because we generate a lot of dust, but there is this has been taken into account for the management of the dust, and also the process filtration of the water used in the cutting to recirculate the water and not waste it. So we go to the next step, which is the shredding and sorting. So this was the pre-shredding equipment which was installed in 2024, and a lot of tests has been run. So what we got? We got that we have a pretty much different families of materials in the wind blades actually. So that's why the pre-shredding results show us that it's difficult to separate the materials after the shredding because they are too well mixed. So that's why the smart cutting comes to help us, because you select the channels you want to pursue later, because you separate before the shredding the glass fiber from the carbon fiber, which are the most difficult part to separate after the shredding. So that's why the smart cutting phase it's important. So the results basically confirm that the balsa wood can be successfully separated, which is good, but the mechanical sorting of glass fibers from carbon fibers is still difficult. That's why it's important to separate them before the shredding. That's the conclusion we got for now, because a lot of separation methods have been tested but are not useful. So we jump to the part, the recycling part of the value chain, so after the pretreatment. So we start from the mechanical recycling. So the main challenge here is that by volume, the presence of core material in blades is huge. And this makes less appealing the using cement and the production output is reduced. So in the thermochemical processes, because those material is not suited for these processes. So what's the idea here? Use the least valuable part of the blades, which are less suitable for the other recycling processes. So if we transform those in panels, we left the best and suitable materials for the other recycling processes, and we still remain competitive because we use the least valuable parts for panel production, which can have various densities or thickness, regardless of what we want to obtain. So these are some examples. For example, in the building components, or either panels that could be used for to isolate thermically some parts in the cold chain or freezer components, for example. And this is an example of formwork, fully recycled, which can be modular also. And now we move to the part of the value chain in which we start to explore the thermal recycling processes. So we have here the Gencraft process, which is an electrical pyrolysis, which started from a batch process, and then now it's in the project being converted to the continuous process. And this allows us to recover oils from pyrolysis, clean fibers, foam, and new materials. We can product some products like skis, for example, or also non-woven mats, and so on. So this is the idea of the technologies. So it starts from the downsizing. So we have the elements that are reduced, ready for the process. And then there is the thermal depolymerization and depurification phase, in which the clean fibers are obtained, meeting so the expectation, because everyone wants the blank fibers, not the dark ones. So now we are up to the last phase, in which the continued phase of the process it's being explored and constructed. Because, as I said before, we are also in the last year of the project. So now the goal is also to upscale the production to nearly 3,000 tons per year. So next steps will be to scale up further also the capacity of the plant and the continuous optimization for the parameters of the thermal purification processes. So last in the recycling bracket. Okay, so as I mentioned before, every step generates dust. you have to deal with those, and that's the problem because it's a loss of material, and also you have to deal with them because you cannot let them go. As you might imagine, every step produce dust and fines. So it's as I said, it cannot be ignored. So in this phase, the Ecolab Technologies goes for the recycling of the dust and fines by gasification of them to produce the syngas, which is an energy carrier, and the residual solid that are basically inorganic inerts compounds. Here you have some data. So as you can see, we have a pretty good percentage of methane, hydrogen, and CO, which is useful for the synthesis and also as an energy carrier. And also here you have the comparison from the data we have tested in the lab scale and the industrial scale, because the industrial scale is obviously the goal of the whole process. We have here the data and parameters we have obtained. Lastly, last step, we close the loop of the project value chain with the eco-design phase, in which we go for the end products, actually. So, in the reverse pyramid, we are located in the repurpose and the recycling zone, basically. And here's some examples. The repurposing approach, we have explored the picnic table, which was already in literature by Gel Giustra in 2021. We proposed this last year in the JSC in Paris. And then, as I said before, for more panels, we are exploring also the 3D printing and the non-woven insulation mats from the thermally recycled materials. To validate everything and demonstrate everything is sustainable, we are also performing the LCA, the sustainability analysis, in our project. We have gone through the preliminary LCA phase in the design phase, and now we are validating and redoing the LCA with the real environment results. So, we can notice that this graph shows the relative climate impact of waste management options against our recycling options. So we treat 100% for the landfilling or incineration, and here we have the relative climate impact of our processes. You might think, so the mechanical recycling process is not good, seems like. But you have to consider also another thing, that every process leads us to avoid to use virgin raw material. So this produces an impact, and in the end, the general impact translated in tons of equivalent CO2 avoided show us that the mechanical recycling actually is delivering the largest net reduction. But also, the thermal processes are doing quite well if you consider the tons or kilos of CO2 equivalent avoided per ton of material used. So, this was all from my side.
Thank you. Very interesting presentation. So I have a question because I was surprised by the amount of powders. There are different players in the room that discuss about mechanical recycling, and they didn't mention it. So I'm wondering, can this be reduced, and what was the process step, if it was cutting or shredding, causing this high amount of powders material?
Okay, so if we start from the shredding phase, this is the normal process you use for reduce the volume basically of the wind turbines and the fibers to get them in the process in the machine that then it's fitted with the resin and then you make the panels, but you have to basically reduce them too much because you have to press them. So that's why you generate a lot of dust, because in the mechanical recycling, when you are going for panels, the dimension of the feedstock has to be more like in the same granulometry, and it has not to be too high. Sorry. Okay. So that's why we generate a lot of dust. Because you have to imagine if you are making panels, you have to, if you look at the panels, you see the dimension of the grains and particles. They have to be quite small, not too small, but this is why also it's quite energy consuming, but in the end you obtain the panels that substitute a lot of virgin raw materials, so that's why it's still convenient, but you have to deal with dust and fines. I don't think there's a real way to avoid this when you are treating composite materials. It's inevitable.
Hi, super simple question here. On slide 19, you were saying the least valuable part of the blade, it's on your challenges part. Was that the root section you were referring to?
Okay, let me go back then. So I will
Side with the
answer.
blade with
this one.
Yeah. You said something about you don't use or you referred to the least valuable part of the blade.
Yeah, the least valuable for the next recycling processes, because you cannot use the core material basically for the thermochemical processes.
Which section? Is it the root section you're talking about?
Yeah.
Yeah, okay, there, that's all I was.
Okay. No, it's okay. But you see the composition, basically, of where it is located.
So you don't want to recycle the root section, or you can't recycle the root section, is that right?
It's not so appealing.
Perfect.
Okay.
Yeah, I was also wondering about the fines. Or the dust, because especially in combination with with gasification. So as we also do gasification, our dust content is in the lower 1%, lower, lower than 5% basically, and you have almost 50%. So did you do that on purpose, or is that just a coincidence because you just smashed it?
No, those are data that we found out experimentally by processing. So it's, you are meaning about the weight of dust.
Yeah, exactly. So because if you just take a hammer mill or whatever, it depends on what you. Depending on the question is, did you design it that way? Because that's an incredible high amount of dust. So, we are like basically 10% of your dust.
No, this is the amount of dust is not controlled. It's something we measured after. But the idea also is that we use the dust and fines for this process, which can be combined well also with the mechanical recycling process. So we accept this basically.
I think what we're saying here, for various people here, it seems a high volume of dust for what you're doing. So maybe that's a reflection of the processes you're using and so forth.
No, I mean, there is this loss of dust, but it's fully recovered, so, I mean, it's not a loss in the material balance in the end, because we are able to recover it.
Hello, Daniel. I have a question for the LCA result. I see for comparing the mechanical recycling with the thermal recycling, the process impact is higher for the mechanical recycling. I'm just wondering why. What's the hotspots for that? Because we all know that for the pyrolysis or the thermal recycling, you need the initial pre-cutting, so which means part of the mechanical recycling is included in the thermal recycling. And can you explain why here the thermal recovering has the lower impact?
Because here you are... Can you use the microphone? It's working? Okay, it's working. Perfect. Because in the thermal recycling parts, you are also recovering you recover the chemicals and you recover energy also with the dust. In the mechanical recycling process, there is a larger amount of energy involved because you have to, we have to use the press and so on. So it shows like a higher climate impact.
So this is the lead result. I mean, the process with the benefits, right?
Yeah, here you are just considering the relative impact of the process. But if you want to consider the whole impact, you have also to consider how many virgin raw materials are you avoiding. And this is a contribute that it's translated in the tons of CO2 equivalent which is avoided. But if you are analyzing the whole picture, you have to also take in consideration those further steps, not just the process itself that makes more or less emissions.
Yeah, it's clear for me now. Thank you.
Okay, thank you.
Hi, and thank you for your presentation. I have a question related to the dust content. Can you please go to that slide? Yeah, so 50%, it looks very unrealistic to me also. We have done a lot of tests with different machines, but 50% is too much. So what are you considering here as a dust? Like you have mentioned dust and fines. So to what size limit you are considering it like dust and fines? I mean, below which size?
It's written here. We consider dust and fines with the granulometry from 0 to 5 millimeters.
So less than 5 millimeters, you have 50% of material.
Yeah, that's what we got.
Okay. That seems really unrealistic to me.
If I may comment on this. Sorry. Just to say that in order to get the 0.5 mm that we can put in our concrete, we have to pass through the additional pre-processing process. So I'm curious to have your process, and maybe by this way we can absorb all of the waste with a lower cost.
I mean, this one, it's still on the, we are putting this towards the industrial scale currently. But we can for sure align also on the results, and why not?
Okay, one last quick question, please.
One last quick one. Actually, it's not only you, but even the previous speaker. I'm not sure what the fuzz is, if I may call it that way, with the dust, because in our case, we want the dust because it gives us a fine surface. We do a 3-layer panel. So, you know, I really, and I think 0 to 5, if people paid attention earlier, I said our granular is all smaller than 1.5. So dust is, depending on your process, can be good, can be bad. But apparently in your case, it's bad.
Yeah, it's bad because we want to obtain also longer fibers. So if you want to obtain longer fibers,
Yeah, we do that in the core of the panel. But we use the finer layer on top, so we get smooth surfaces. When you laminate the panel, it's like a mirror finish.
yeah, but
It's a matter of the process.
But you're speaking about the panels now, or what?
No, fiber length, fiber geometry. You're talking
okay,
about
general.
dust, and like I said, we have perfect use. I want to repeat myself. Everything that's in there, even the dust, even what we recover from our dust extraction system to keep things clean in the building, we're reusing that in the panel.
Yeah. Reinhard, we're really talking about Daniel's project here, yeah? Yeah. Okay.
I understand, but you know, it's worth mentioning.
Thank you very much, everybody. Daniel, that was a great presentation there. You put a lot of work into that. And there's coffee outside now, and then if we can assemble back reasonably quickly, there's one more presentation and then a panel session. Thank you, everybody. Hello, everybody. We've had a break for our coffee now, and we'll start the second part of this afternoon with a presentation by Dr. Angie Nagel. She's the Chief Executive of Blade Bridge, which she's built up as a pretty smart company operating out of Cork for repurposing wind blades.
How you doing? So I'm Angie Nagel. I'm CEO and co-founder of Blade Bridge, and I'm going to present to you today about Blade Bridge first, and then a case study of a shelter that we built for a local authority in Dublin. And then I'm going to do just a brief whip around of our cost model. It's going to look probably quite different to what the recycling discussion on cost is, and plans and capacity, which again will also look a bit different, and then into the Q&A. So about Blade Bridge first. So we're all here to talk about the end-of-life wind turbine blade problem for the wind sector, right? But I first came across this with the ReWind project, which was a research project out of Cork that looked at repurposing of wind turbine blades. It was multidisciplinary. There were sociologists, structural engineers, environmental engineers, et cetera, that worked on this project. And we looked specifically at repurposing, not recycling and not reusing, but just repurposing. And from our research, we saw that even after 25 years of use as a wind blade, the wind blades still have a lot of life left in them. So they're stronger than steel and aluminum. They're extremely durable, and they're capable of replacing steel and concrete when they're structurally repurposed. So this is what Blade Bridge is based on. So it's not a spin out, but it's based on the research from the ReWind group. And we repurpose the retired wind blades into durable products. So we're a two-sided business. We're offering waste management for the wind sector, and then we're offering durable products for other sectors. So for wind farms and material handlers, we aim to be cost competitive to recycling, and we want to really show the wind farms and the end users of the products, or the end procurers of the products, engagement in the circular economy. So when you look at our products, you see clearly that they're made out of wind turbine blade. So as we said, we're offering waste management for the wind sector, but this is just half the story. So local authorities and contractors need to source infrastructure that's affordable, that's durable, that looks good, and that it meets green procurement requirements. And Blade Bridge is aiming to do this. So far, we're working as kind of one-off projects that we're aiming to scale up. I'll talk through this. But this here that you're looking at is our Greenway furniture collection, basically. Ireland is building 3,000 kilometers of greenways. The Greens were in government there during COVID. They pledged €1 million a day to try to catch up with the rest of Europe with their cycling infrastructure. So a lot of our initial products were for cycleways and greenways, so they all have bike parking incorporated into them. So far, we've made greenway shelters for county councils. This is up in Achill, and these shelters were photographed the day after they saw 160 kilometer-an-hour winds after a storm that was on about a year ago. And for Mayo County Council, cost and durability were top priority. These two shelters were made from the entirety of a B39 blade that we got from Scottish Power. We used the root sections as the uprights. We used the middle sections as the roofing. And then the tip sections, which aren't that great for structural applications, we use as the bench legs. So we called this also our parts of the cow too. You referred to parts of the cow, and this is kind of our way of trying to use the whole wind turbine blade. We've made pedestrian bridges where 80% of the steel is replaced with blades. We're effectively storing this material for another 60 years till the recyclers can, figure out what to do with it. We've built street furniture. This is also up in Mayo. That's really attracting extra visitors. So we have people who are going around and tagging themselves and saying, I've seen another Blade Bridge installation. So this is all the way up north in Achill. And it's a stunning part of the country. If you want to do a Blade Bridge tour yourself, you can start in Achill. We've built electric bike charging hubs for the National Electrical Utility, ESB, that are super durable and beautifully shaped. And this was after they searched around Europe to try to find durable boxes for rolling out electric bikes across the country, and couldn't find anything that they thought looked good and didn't rust. And finally, we're making bespoke creations for wind farms, like this installation we did for Energia, in which we fully repurposed a V52 blade into a memorial for a man who basically had built that wind farm 20 years ago. So I'm going to go into the Rathfarnham case study. I'm going to show you from start to finish how we built one of our products. So we were contacted by Dublin County Council in April of 2024 for their Rosemount District Improvement Scheme. And they had a fairly simple design brief. They wanted covered outdoor seating and bike parking. They wanted it to be extremely durable. They wanted a centerpiece, basically, right? They wanted it durable. They already had a budget with a contractor, so they needed it to meet the budget. And then they really wanted to demonstrate their engagement in the circular economy. So they wanted it to hit you in the face that these are made out of repurposed blades. So this is the render that we came up with for them. We had a couple of design iterations. We ended up with this that really featured the blades, and they were happy with this. So then the next step is to source blades. So far, we've worked with LM13 blades and B39 blades, and Scottish Power paid us to repurpose 6 blades that were badly burnt within 24 months. So in designing this or choosing the blades that we'd use, we really prioritized the B39 blades over the LM13s, which we got as just test blades. So we had done extensive structural testing on the LM13 previously. Paul talked about that a bit yesterday. So we did sort of a go, no-go comparison or structural comparison of the B39s against the LM13s to qualify them for use in our shelter. Then we did the engineering drawings, selecting each of the blade sections. And again, we used the parts of the cow approach, where we took the larger blade sections as our uprights, the middle sections as the main roofing material. We ran out of B39s for the roofing material. So there's one roof section that's made out of an LM13 and one that's made out of a B39. And it formed a frame for polycarbonate. And then the tip sections were the bench legs there. The blade preparation and fabrication, so blade geometry is clearly the biggest obstacle to repurposing, right? But it's also an opportunity. So we love the blade geometry. We love using it. We're inspired by the geometry for the design. So it's more of it's an opportunity as much as a challenge. So we did several things like, yep, all right, that does work. So not good enough, okay. So if you look at the far right-hand image, we've positioned the blade so that the trailing edge slightly curves upwards. And so this serves as a gutter for the water. So the water is actually directed down off that lip and down the far edge of the shelter. So that was one way where we capitalized on the blade geometry. We created universal steel brackets to fit multiple blade models and multiple blade sections. And we used recycled plastic for the end caps. And that's why I'm really interested in talking to everybody's recyclers here who can create material that we can use for, say, end capping or for the bench tops as well. But we also received a grant. We were talking yesterday about public and private partnerships. So we received a grant from the Department of the Environment, Circular Economy Innovation Grant. And that allowed us to take our time building this, and it supplemented some of the cost of the design. And now we have a shelter fabrication process that's repeatable and commercially viable for public procurement. And that was enabled by a small bit of extra public funding. We worked really closely with our transport company because we needed to be able to drop this shelter in place and have it installed in 4 hours or less. So we created these removable brackets, which are up there, and that allowed us to lash the shelter down to the truck and then to lift it and place it into place when we got there. And we really consulted with our transport company from early on. So this was installation day, dropping the shelter into place. This is right in the middle of Dublin city centre, so it's quite busy. We didn't want to close the road for very long. And basically the road was closed for only maybe about 2 hours as we dropped this into place and then secured the back wall section. And then the benches were, sorry. There we are. So then this is the finished product with the benches in place. And there's bike parking around the backside. I have another picture here in a minute. And then we always put a sign on our products that say what the provenance of the blade. So this says, I'm made from a retired wind blade. I can't actually read it from here. There we go. We came from Barnesmore Wind Farm in Donegal after generating electricity for 20 years, and we're each 20 meters long and weighed over 1 ton. And we're substituting new materials as furniture. That's pretty obvious to all of us here, but it's not like if you're somebody that's never seen a wind turbine before, that's pretty special to be able to stand there and actually touch the blade material. So we mentioned yesterday community engagement. It was just asked over here. So we did a round of community. We had a postdoc come in, and she did sort of formal community engagement process. And this is what she got back. Basically, people loved the design. They understood that it was made from turbines. It was great. They wish there were some bins involved. That's what the bins sign or note is there. The feedback that we got and that Dublin County Council got, it's not big enough, it's always full, there's students there, there's moms there, people feel safe, it's a conversation starter, people actually chat, what do you think about this product? It's used by a wide range of groups. It caused people to stop and consider both material reuse and renewable energy, and then material reuse in renewable energy. And therefore, it led to strong community support for expanding similar repurposing initiatives. And really, this is what we wanted to get to with BladeBridge, is that people are inspired to repurpose construction waste. And if you can repurpose a crazy shaped item like a wind turbine blade, there's a lot of things you can repurpose. Okay, so I'm going to talk briefly about our cost model, and here's another picture of the shelter where you can actually see the bike parking. So this shelter was a little bit on the expensive side at first, but we will, with the work that we did in doing high volume fabrication, the price will come down. So in general, we aim to be sort of high end but competitive for public procurement. We're still waiting for green procurement to come in to give us the price margin that we thought we would have. We're marketing to contractors who bid on active travel schemes, so we're not going directly to public tendering. We're marketing ourselves to contractors. For this product, labor and the wood were most expensive, and the plant hire, but the plant hire will get down as we buy, our own equipment. And let's see, so I just want to talk. So we're a two-sided business again, right? So we are, we have to keep the costs down for public procurement or for building the products. But then there was talk yesterday about getting the costs down for the recyclers, for the wind farms themselves. And my answer to this really is that if we want to get the costs down, we need to keep the asset owners engaged in what happens to their waste. So what we're suggesting is that we share the repurposing fee. So if we can create demand, so if we understand what blades are being decommissioned, we can work first with the wind asset owner to see if they need products made from the blades. For example, there might be a wind farm owner who's decommissioning a bunch of blades but actually developing a farm someplace else. Maybe they want to develop a hiking trail, bridges, furniture on the new farm. So a wind asset owner who wants to order products for their own blade waste, we can waive the repurposing fee, and in this way the waste handling is free to them. An example of this is Energia. We created a memorial for Energia. They commissioned us to create this memorial and a set of furniture which used the entirety of a damaged V52 blade, as I mentioned earlier. So we charged them for the structures, but no repurposing fee was charged. I have QR codes for all of these at the end so that nobody got distracted during the talk. So plans and capacity. So I've changed this a little bit since listening to everybody talk yesterday, so let me do my best here. So we want to get involved early in the decommissioning process so that we can characterize the blades and find customers for blade products. So we want to get involved in the decommissioning planning input for farms in UK and the EU. So this is our aspiration. We want to develop partnerships with UK and EU material handlers and fabricators in order to offer local repurposing beyond Ireland. And we'd like to do this through some sort of a pop-up repurposing line. And then we want to position ourselves more as R&D, so research and development in Ireland as the blades get bigger, while fostering international partnerships for expansion. So I'm going to talk briefly about these. So if we can get involved in the decommissioning planning input, we can create renders, do some life cycle assessment, and allow the wind asset owners to start thinking through, could they send a percentage of their blades for repurposing? Now, in practice, I know that's a difficult thing to do. In general, they want to send all their blades in one place, but we'll work on that, I suppose. We have a catalog of products that are available. I have the link at the end, but this is one example of our catalog product. So we want to develop partnerships for pop-up repurposing lines for local fabrication in the EU and the UK. We want to work with waste management companies to cut the blades to our design and specification and then send them to local fabricators. The main thing I took away from yesterday is that I'm wondering if we're still figuring out where we sit in the supply chain. So could BladeBridge actually, their main customer, be recyclers? Like, for example, I've heard over and over again that the root sections are difficult to recycle. So could BladeBridge focus their offering on repurposing the root sections in order to make recycling less expensive? And to solve a problem for the recyclers. So we could position ourselves in the supply chain as a customer to the recyclers. So that's, or blades that are considered, that are more toxic for recycling. So anything that the recyclers don't want to use. So partnerships, we think, are important, And finally, we know that that blades are only going to get bigger, and so our ideas are getting bigger. I threw in some examples, of specifically root sections. So this is a single-person shelter that we're working on right now, the lower right-hand side, where we're using the root section, and we're cutting out the burnt section of the blades from Scottish Power. The picture on the left is my co-founder and I in Andrew's yard shopping, looking at the blades that he has on offer. So we have our eye on maybe talking to Andrew about blades. We've looked at buoyancy applications through the Rewind network. And we're talking to an SME right now who is a specialist in bifacial floating solar PV, but that's probably a long ways out. And then this is just, if you can see this on there, this is just a whole pile of ideas for the root sections that I pulled out specifically just from yesterday's discussions. And then my favorite product, this is something we've always wanted to get through. Through the Rewind project, we've shown the technical feasibility of building a transmission tower out of a 37-meter blade. So there was a PhD that looked just purely at that. We think that telecoms towers, rail signal towers, light towers would be less structurally demanding than a transmission tower, and therefore we're fairly certain that technically this is feasible. We love the idea of building towers because there's very little cutting and a lot of steel substitution, and we just got notified yesterday that we got a grant, again, from the Department of the Environment in order to pilot this tower. So we're hoping to do that this year, and we have a customer for it already. So the idea of towers would be local repurposing anywhere in the world. Potentially we could put together a local remanufacturing process so that the blades only need to get moved from their decommissioning site to their site of installation. So I am finishing with an ask. So what I've been looking for from this conference has been, I love the collaboration, it's been fantastic talking to everybody here, is possibly looking at a customer relationship with recyclers to repurpose their difficult to recycle blades or sections. So I'd like to explore that now after this conference. Partnerships with waste management companies for pop-up repurposing capacity, as well as looking for local fabricators. And then collaboration with other repurposing companies to see if we can influence blade waste handling regulations. I've had several discussions around the waste handling regulations, and I just don't want us all to get caught out by it and it to, impact our business. And make sure that it's being handled in the right way to foster innovation. So, thanks very much. These are the 3 QR codes. The middle one is the memorial project that we did with Energia on the V52 blade. The right-hand side is our catalog, and then the left is if you want to get in touch. So, thank you.
Thank you for your presentation. Very interesting. Oh, I'm here.
Oh, yeah.
In the back. Just a question, because for repurposing, often you lose completely the functionality of a blade.
Yep.
And yeah, maybe it was not so smart of me, but I cut it apart of a blade to make a table of it for an exhibition. I placed it on my car and it looked like a Formula One, a lot of down pressure. But I was just thinking, is it possible for repurposing to keep the functionality of the aerodynamic profile? I think maybe some spoilers in the urban to direct the wind flows.
Suppose if there's commercial demand for it, we can do anything. But why would you want to create the airfoil, a functionality of it still? I don't know why. I'm not sure that I'd be looking to keep that functionality necessarily, unless I'm missing something.
Actually, I was a bit triggered. Yeah, that's maybe from the negative perspective, because if you set from the pole for the transmission, because then you have a serious problem with vortex vibrations.
That's what we'll have to design for, yeah. And then maybe it'll be two blades that are opposing each other. I mean, maybe that's what we end up doing is one of the blades serves as the cable tray and the other, is the, holds the equipment. So that's work we'll have to do, yeah. But we did, it's in the initial study that was done in 2022 on a transmission tower, and they looked at vibration and wind speeds, wind loading, as well as like cable, ice cable loading, yeah. Okay. Yeah, okay.
Thank you.
May I ask a question?
Sure.
Is there a chance you can go back to your second slide, which shows the bridge? I have a, right at the beginning it was.
Mm-hmm.
And I think we've seen that photo
Yeah.
yesterday somewhere.
Yeah, Paul.
Could you
So-
please explain to me, because I'm thinking engineering, how is that piece of blade contributing as a bridge?
It's replacing the side steel girders.
So it's a handrail.
No, it's,
Well,
it's
yeah,
it's the superstructure for the bridge.
It's not a
It is
weight
carrying,
supporting.
it is a weight supporting and carrying structure. It's substituting the steel I-beams that would have been used for the superstructure of the bridge. Yeah,
But the roadway that
yeah.
is
Well, it's-
going there,
It's a pedestrian bridge only. Now, it is rated for a 14-ton emergency vehicle to go over a couple of times.
but
Yeah.
how is the connection between the blade and the actual road surface?
Yeah, so the bridge deck is hung on so it's an LM13, it's got the short little spar cap legs. So we actually hung the bridge through that kind of 1-inch triple layer of the spar cap that ran the length of the blade.
So there's this, like, you
Yeah.
machined it out? Like there's the
No,
slot in
there's
there?
bolts, so we use blind bolts.
Okay, all right.
I don't know the diameter of the bolts offhand. So, but there's bolts that went through the full. So we basically oriented that. It's a C-shaped spar box in the LM.
Okay,
blades,
yeah,
right?
no, that's fine. That's
Yeah.
fine. Got it. My last question is on the towers that you showed there
Yeah.
with the transmission and so forth. Remember the blade, I mean, it has a narrow side and it has a wide side. Are you not concerned about wind load if the wind comes from that one?
Yeah, that was the
direction?
question over here. So yeah, we'll just have to test it and design for it. And it might be the case that we're using two blades facing, opposing each other to negate the wind load. We'll figure all that out. Yeah.
Okay. Now, fire retardancy. I mean, if somebody puts
yeah.
a little bonfire there,
Yeah.
that whole structure.
We'll
goes
have
up
to
in
figure that
flames.
out. We might be leaning on BladeMate did a lot of that work already. So, if we are collaborating, yes, it's work that'll have to be done. Yeah.
Okay.
Yeah.
Thank you.
Welcome.
Wonderful.
Angie, thank you very
Thank
much
you.
indeed. That's a tremendous presentation. Oh, Derek, welcome. You're going to moderate the final panel, and we can all look forward to that.
Okay. Yeah, sure. Whatever you do, yeah, absolutely. Thank you so much. Yeah, all set? Yep. Thanks. Do we have one more possibly? Okay, great. Yeah, take your time. Thank you so much. All right. Well, welcome to our final panel. The good news, Andrew has told us we can take the last 2 hours of the day of the conference here. Thank you, Andrew, for that. I'm sure everyone's thrilled.
3 hours.
Oh, 3. Oh, you did. Awesome. Good. We have put together our all-star panel here to talk about materials, recycled and repurposed materials, and the reuse of that material in end markets, commercialization of that material, and what has to happen. And so I'm going to introduce the panel here, give you a little background. So Claudia Martins is CEO of Jewelmine. You saw her presentation earlier today, and so you get a sense of what she does. And her background is vast. The cool kids, I'm too old and too uncool to probably say this, would call her the OG of wind energy and blade manufacturing. And spent time at Siemens and GE and Areva, I believe, and over many countries, 5 countries, I believe, and many years. We'll just stop there. And so an expert, hands-on expert in a lot of blade manufacturing activities, procurement, and other things as well. So welcome to the panel, and we look forward to your input here. Harold, down there in the middle of the panel now. Harold, the good news is I've known you for 10 plus years, and I've called you Harold. I'm going to try your full name here. Harold van der Mille-Meyer. Yeah, you're just being kind. I know that's not even close. Anyway, Harold is a senior consultant at TNO for materials and circularity transition in wind energy. About over 19 years of offshore circularity background in materials engineering. And you have, I know, participated in and led many EU and Netherlands research projects over the years. But one of the really important things that Harold does is works on roadmaps and a couple, then a Dutch roadmap for circular offshore wind, but also a roadmap for looking at future price criteria and innovation programs on circularity for tenders, things like that. And you and I have been participating more recently in IEA Task 45 on a roadmap for recycling for blades down the road as well. So a lot of work on looking forward, what our future looks like and how to get there. So thank you, Harold, for all that. Great. Joachim, Joachim Karthauser, okay, great, good enough, got the thumbs up. Since 2023, chairman of Wingbeam Sweden, AB. Background chemistry, PhD in chemistry in Göttingen, okay. All right, university. And so you have over 30 years of experience here, international participation in plastics and energy research here. And so that's bringing quite a bit of experience here. Different companies, I think Shell, NKT and others. And then you have various, I mean, it looks like you've kind of started up a couple of different companies over your time. You're collecting companies. You just keep on saying you've been around for a while. Yeah, exactly. But I think one of the more important things I saw is like to create bridges between research and commercialization. And that's a really important thing. There's no question. A lot of times you see research that kind of sits on the shelf at the end of the day, but having that application, working with industry and making sure there's a pathway for innovation from that research stage through prototyping and getting to commercialization is really important. So great. And then it did say you're a member of, is it DECEMA? I had to look that up. It is the German Society for Chemical Apparatus. Right. Okay. So I learned a little bit when I looked it up, but yes, so perfect. Okay, great. Welcome. Anurag Bansal. And so you saw Anurag present earlier this afternoon, is the head of strategic innovation at Acciona Construction. Over 26 years, also a pretty hands-on environment for you, and kind of bringing things from the ideation stage all the way through R&D, prototyping, and out to commercialization as well. And that's kind of what you've done at Acciona over your time there. I think it was really important. You mentioned looking at both the technology and the economics of what you're doing to make sure that it has a pathway to commercialization as well. You and yesterday we had a celebrity, and Anurag, you're our celebrity on the panel today. Best innovation for building and construction category at I call it JEC. I think over here maybe people call it JEC in Paris, in one of the years past. So congratulations. Great, and welcome to the panel. And then, and I apologize I haven't asked you this yet. Is it Marcello or Marcelo? Marcello. Okay, great, excellent. So Marcello Colodani. Okay, great. Full professor at Politecnico di Milano. And so you are part of the mechanical engineering department there. Great. And so you are, it looks like it says you have done some research in my hometown of Boston, or Cambridge, which is, so MIT is in Cambridge, but spent some time at MIT in Cambridge, Massachusetts, doing some research at the, it is the Lab for Manufacturing and Productivity. So yeah, I spent some time there. That sounds like fun. And really, we saw you presenting on Daremco project yesterday, and a lot of great work going on there. But you're also the co-founder and president of a startup called FiberUse technology, and that's to bring research out of the laboratory and again to commercialization. I think I'll stop there. I think one of the common things we see among all of our panelists today is the fact they're working to commercialize new technology. They're working to get material that is coming out of repurposed or recycled blades into the market. So a lot of their backgrounds are similar in some respects or have some commonality there. So can you welcome our panel and we'll get started. Yeah, go ahead. All right, so I'll go ahead and sit down, switch pages. So what I'd like to do is start the conversation off talking about the recycled material. And so we have a lot of presentations this week on the last couple of days on decommissioning, the on-site breakdown, transportation, a lot on recycling methods and what those look like. But then all of that really cannot exist or can exist, but isn't productive unless we have a way to use that material at the end of life, at the end of life material that is recycled into new applications. And in order to do that, there's a lot that has to happen. That material that comes out, know what that material form is. We have to understand what the characterization of that material is. We have to understand the material properties. We have to understand what type of applications it can be bound for. We have to develop supply chains and develop relationships with other end markets that use composites and things like that. There's a lot of work to be done in order to enable all of the work that happened before that and getting to the point where we have recycled material. So given that, I'll start off to the question for the panel. Given that there are some limited end-use markets now, we're looking to open up more, and what do you see as promising right now that is in place and markets that we can capitalize on for recycled or repurposed blade material? Or what do you see as potential untapped markets that could also be a place where we can use recycled material? So maybe, Marcello, if we start down the end there and maybe go from there and see what you think.
Yeah, I will be. Thanks for the question, because I think that the main difference between this year event and last year is that people and all the community is really concentrating on off-takers. And well, answering your question, I think the most promising, at least for what we are doing, is BMC, is automotive, is electronic components, any application in which BMC material can be integrated. Yep. Since we have this solution for integrating recyclates in the BMC, this seems to be one of the most interesting market for volumes. Untapped potentials, well, many, I would say. I'm starting getting in contact more seriously, intensively, regularly with the boating industry. Of course, in terms of input sector, but also in terms of off-taker. Let's see how it evolves, but it seems that they are mature enough to make some trials and to experiment on some formulations.
Yep. From my point of view, I would say construction is a very good market. Just looking into the amount of material it uses per annum. More than 45% of the material worldwide which is used is consumed by construction industry. Now, within construction, if we see, there are two kind of elements. One is structural and one is non-structural.
Right.
Right. So I see that let us go step by step. Instead of going for a structural element where you have to demonstrate the mechanical performance, start with non-structural applications. And one such application I would say is a foam work. Like whatever you do with concrete, you have to pour it. And what people do normally, they use either a wooden foam work or a steel foam work. So just imagine, those are temporary foam works. Now, if you use these materials in foam work, you can either use them as temporary, or if you design good, then you can use them as permanent. And you can even reduce the amount of concrete and the steel reinforcement.
Okay, yep, excellent.
So I would say start with this simple use case, lot of applications.
Excellent, okay.
Thank you.
Yeah, great. Harold, yeah, go ahead.
Yeah, first I would like to say something that I'm really happy about the creativity over here, because we're working on a sort of black box, difficult to recycle, and we never designed for circularity. It's difficult to recycle. It's only for low cost, high yield, and low mass. So that's the first thing. So to find a market, it needs a lot of creativity and incentives. And at the EOLOS Wind Europe conference, we presented a social perception study. And we've seen that, now we discussed also with Thijs from BladeMate, is that we go for the high volumes, but we've seen for the overall social perceptions that these things like repurposing, they are triggers, and we need the social perception to stimulate also the policymakers and the government. Now, that's the incentive, and we've seen in the projects where we are involved that we need also clarity and transparency to get high value use of the recyclates, and we need to be sure what's the inflow and the outflow. So the markets, I fully agree that we have to focus before the construction markets that we say from now, but there are really large markets, like for instance, the reclaimed fiber to use it in injection molded products. Now, if we use only a few percentage, then we covered the whole problem for the wind. So it's, let's be creative. Yeah. Continue. Yeah.
Good. All right. Great. Yeah. Okay.
Yeah. Thank you. I'm not evading the question, but first of all, I would like to thank the organizer here for putting together the whole spectrum from wind energy to recyclers, and I think it's excellent. We're forming a family here and we need to collaborate. So I enjoyed everything from BladeMate and Angie's Blade Bridge and other contributors. Very inspiring, and I hope we'll meet soon again. So on the potential markets, I definitely agree with that the construction industry is the prime market. We as companies were looking at low-hanging fruits, and like Angie's shelter things or urban furniture from BladeMate and the like. These are quick fixes. They create a lot of positive publicity. Then in the long run, we have the technologies which we discussed here. Specifically, I would say where you can, where you don't have lengthy approval processes like noise barriers or so. These are low-hanging fruits. Structural, before we build a 50-meter skyscraper or something, that'll take a few years. But we do have applications where we replace virgin composites. So like concrete in marine applications is reinforced with composites. And that's a one-to-one replacement, provided you have all the quality guarantees for composite rods or armaments. So low-hanging fruits, as little specification and approval work as possible. I think that's the way to go, and then we'll proceed.
Great, excellent, yeah. Go ahead, Claudia, want to jump in? Yeah, thanks.
Yeah, I think it's very clear that we have to get a lot out of cooperating. And I think, everybody has a little bit of a different philosophy. So, but for example, if we cooperate with for example, with a company like Blade Bridge, that, with difficult parts, that might save me a lot of CapEx, right? So that's great, right? Our philosophy is to take everything apart and insert it into the resource value chain as early as possible, so you have freedom of creation, right? Like you can create anything out of, a plastic component or a foam or whatsoever. And yeah, so basically for us, it's the chemical industry and also the construction industry. That's two major application fields.
Yep.
And then obviously there's always a niche for other products,
So I have a couple follow-up questions, really interesting answers, and one of them is about material characterization. And so all of you mentioned some different approaches to applications, what type of fields to use them in. What are the requirements, and who is it that is setting those requirements when they're looking for a certain material that has certain mechanical or other properties, not just mechanical maybe properties, but other properties. So if you have somebody who is going to use it in the construction industry and they're going to mix it with concrete, there may be a certain set of purity, maybe a certain set of mechanical properties, I'm not sure. Who sets those metrics? And then how do you go about satisfying, testing for, and characterizing the material? And it could be different, obviously, by different applications. I don't know if anyone wants to jump in and talk about that process. Yeah, go ahead, Harold. Yeah, please.
This is, you said I'm working on the roadmap for the government. We defined 7 different routes because from the short term for 2030, and 2 of them are really matching this one. One is the clarity, the standardization. So we, for instance, the digital product passport. Now, I think you mentioned the batteries. Now we use the same method now to roll it out for a use case for the blades. But secondly, for instance, for use it as a constructual component or reuse, then we need also the operational data. So that's the second route within this roadmap, that we want more quality data during the operation of the blade. And that gives it a lot more value, even if you use parts of it. For the digital product passport, it's more than a material passport, because you can put more detailed information about the whole supply chain in it and make essential data available for the different steps in the supply chain. So I think clarity, transparency, it helps a lot, and yeah.
Okay, great, clarity and transparency. Go ahead, Marcello, yeah.
Very quick answer. I mean, this is, as I mentioned yesterday, for our business case, super important. So we call it specification compliant circular economy. We start from the specifications. And of course, I think that this is a must for opening the demand for these materials. Our answer is coming from the adaptability of the recycling system. But of course, there are other ways to tackle this issue. You can use massive inspection in line to just characterize the material. Doable. Definitely, you have to certify that the characteristics of the material respect the specification. So, no doubt on this.
Yeah. Okay. Gotcha. Others that want to jump in on that? Okay. Go ahead. Yeah.
Apart from technical specifications, there's also the issue of customer processes. So does it fit? I mean, the mechanical properties, fatigue, strength, and so forth, those are given, and as a company, you're very wise to work with selected customers and really do what they want. And the second thing is, it has to fit their production process.
Right.
If you come with completely new material or dusty materials and the customer is not used to that, then it's quite likely to be a no-go. So, interview customers, interface with them intensively, so you do the right thing.
Okay, great, excellent.
Yeah, I think it's our responsibility to do a lot of the testing. That's why we, for example, work with Fraunhofer to actually generate the data. If we want it to be accepted into a new, as a new part into a supply chain, we have to bring the proof that it actually works. So, and the challenge is obviously that, when we were younger, we built the wind industry, and well, different things mattered, no? Will it hold up? Can we make it 5 meters longer? So nobody really knows what's in some of the blades. And we have the task to take all of this diverse material, but still output a consistent quality. Right? So that's a huge challenge, actually.
And given what is incoming sometimes is not incredibly consistent on quality, and you have to have a product that goes to the door with consistent quality, and that transformation, that's difficult. No doubt.
That's a major challenge,
Okay. One of the things that I was thinking about while you were answering those questions is it the recycler, and in some cases some of you, that actually develops the relationships and sells it to the end market, or is that sometimes preordained when you are getting material in the door from somebody else has made a decision that, hey, we want to recycle this, but it's going to X, Y, or Z afterwards? Or is it always on the recycler, really, to make that transition, to develop that supply chain of where that materials goes? And I don't know the answer necessarily. I'm coming at this blind a little bit. And is there a consistency there, or is it all over the place?
I can only speak for us, so obviously. It's a little bit diverse, so it starts even earlier, so where usually the asset owner tells the decommissioning company where to recycle because they want it under control. So that's something we obviously like.
Sure.
And then in some of the products, we actually develop because we are responsible for the offtake of our products, so we have to develop, the customer base for H2, syngas, and so on. On the glass side, we cooperate with other companies. So they basically decide sometimes in which type of products it goes in.
Okay, so it varies.
We will have a share on the margin, basically.
Right. Okay, gotcha. Yeah, okay. Any other thoughts about that? Yeah, go ahead, Anurag. Yeah, there you go. Yeah.
So from my point of view, it will depend on the business model of the recycler or the different actors in the supply chain.
Right.
Now, of course, recycler, he has to go. When it comes to meeting the demand of the requirements of the market, because he is the one who is recycling. So what to do after recycling, right? So it is his responsibility to see who would be the potential customer of his product.
Okay.
And even before, because we did all these exercise internally, before Acciona invested in this recycling business, so the first question was, what to do after recycling?
Right.
What to do after recycling? Like, it is good, we are one company, we don't have to go to investors, but convincing our own management is very difficult.
Right.
So the main question that from where we started was, what to do after recycling? Who is going to take the product? What products are you going to manufacture? So I think it is one of the responsibility is of the recycler because it is his business.
Yeah. And go ahead, Marcello, go ahead, jump in, yeah.
Yeah, just to add on this, I think we are talking about recycling, but in fact, what we have seen in these 2 days is circular manufacturers, because they are all recyclers and reprocessors. They come up with the semi-finished products or end products even.
Right.
And so it's, let's say, increasing the value of the simple recycling as we consider it for e-waste, for example.
Right.
I think the best case, at least for us, is when the waste or the post-use products deliverer is also the off-taker.
Okay, right. Yep.
And sometimes this happens, and this is the best case. So if you are a large company with many business units, I would suggest try to think about potential reuse or reintroduction of the products in your own business, because that will be making our life much easier.
Okay, yep, good.
Obvious, but important to say.
Sure, yep, good. Okay.
I would just like to stress the personal thing here. I mean, it's not it's not happening automatically. You need people who are creative and crazy enough to tackle these type of problems. I mean, take Reinhard Kessing, he's fighting 20 years. A few years you were very close to producing thousands of tons. You will succeed in the next phase. So you have to have persons who are engaged and don't really see the difficulties ahead, but have a vision. So I think it's much a personal thing.
Yeah.
The industry as such, I mean, a wind park owner, they don't worry. They are working for a big company. It's not really pressing them. I think it's entrepreneurs who sort of move the needle.
And I think that's a great and an important point, Joachim, that it really takes innovators and people that are willing to take the risks to get this out there and develop new technologies. It's not going to always succeed. We've seen over the many years, companies come and go, but that is an essential part of the process to get where we need to get to, and they try different things, and some things are just not economically viable, at the end of the day, and that has to be at some point. And that brings me to another question: the economic viability of the use of recycled material into new applications. Are the end users, not the end users of the blades, but the end users of the recycled, the companies that are taking this in, so Anurag, like yourself, they're taking in recycled material, are they willing to pay a premium for recycled material because of the value, social value, and circularity value, or does it always come down to economics and cost is king, and so, or is it a mixture of those two? Any thoughts about that? About, do we have that leeway there, that there's a circularity component here, that and we can have a little bit higher cost of recycled materials, or is that not there?
Oh, I can answer
Yep.
that.
Yeah, go ahead.
Sorry. Yeah, we have first-hand experience on that one. With one of our gases. So basically, they see, they like it, and it doesn't matter whether it takes syngas or hydrogen, right? So we basically provide, circular syngas with like an extremely low carbon footprint, and yeah, there is maybe a little bit of an upmark compared to gray hydrogen, but not a lot. Syngas is exactly the same thing. Yeah, by 2030, the chemical industry needs to use circular material. And until that day, they will not pay an extra for it, because their alternative is biomethane, right? Which is like 20 times more expensive, basically. So yeah, no, you have to be competitive at current market pricing.
Okay, yeah.
Basically. So, and for us, that's the goal.
Gotcha. Good. Yeah, right. Exactly. Anurag, did you want to jump in there too? Yeah.
Yes. From our experience, as a user of recycled material, we will pay the premium if our client is ready to pay us.
Okay.
Now, if you see construction industry, basically, I would divide it into two groups. One is the tender business, and one is privately owned, right? When it comes to tender, unless and until it is specified that you will get some points for sustainability, the tender is given to low-cost bidder, irrespective of whether you are bringing a sustainable material or not. Now, when it comes to a private owner, let's say a building, a home, so will the purchaser of that home pay me more for per meter square because I have used recycled material? So those are the things that are like really difficult to convince.
Right.
And that is why our approach is try to reduce all the extra costs so that overall the product is competitive.
Yep.
And one of the things that we have done is reducing the logistics. So that is why we are doing everything in-house. Because it will also depend on LCC, LCA. The more you move the material, the more there is carbon emissions and LCA cost. So we are trying to reduce, not to push the customers to pay us a premium. We are trying to see where we can cut the cost without compromising on the quality.
Okay, great. And I wanted to have a follow-up question here on regulation. So Claudia, you had mentioned the year 2030, I believe, and when something is going to, I'm not even familiar, but something is going to go into effect that changes the behavior of some of those companies, and that I assume is regulation. And so what role will regulation play, if, and should it, is it, should be more of it? How does regulation, and I'm assuming there's regulation on the local, the national, the EU, level here, how can that play a role in increasing sustainability, increasing the use of recycled or repurposed materials in future products? Is there a role for it, and should there be a role for it? If anyone wants to, okay, Harold, please, yeah.
Yesterday, Gianmarco discussed already the landfill ban. And I think that's a good example. The first aim was that it in 25 was already, but now the sector signed it, but it's still not fully accepted. But you see already the drive from operators. They say, now we have a set of blades, but there are two things that they phone us even a lot. We are not a recycler at all, but I think they check the internet and they say we have a pyrolysis. But I think there's a lot of operators now searching for circular solutions, and that's also because of not only the policy, but also the strategy, the company strategy of the operators. And that's very interesting to dive into it. And about I thought clarity and transparency, because it's very difficult for investors to invest in something where there's a sort of vague scenario of what type of regulations will be in the coming years. So I think this is also a push to EU level to be more strict and make a plan. So it's, that's my advice, to make it more stable.
So you want some stability and continuity in regulations. Yeah, go ahead.
Exactly.
Yeah, please.
Yeah, I would actually support that. I think Barack Obama was asked, what's the best invention ever? And he said, the rule of law. So stability in regulations, in taxes, in gate fees, for instance, or subsidies, that creates bankability. You can't go to an investor and say, well, maybe we get a gate fee, maybe not. You can't build a business case on that. So that certainty is okay. And then irrespective of what the subsidy is, I mean, then businesses can accommodate.
Right. Okay. Any other thoughts on that regulation? Go ahead. Yeah.
Oh, all right. So it's, we believe that, if we deliver a competitive product, people would buy it. But if there's no incentive to change, even though at the same price, people take the more convenient way, just do what they always have been doing. And especially, for example, on regulations on hydrogen, we see that is people buy green hydrogen for the certificate, not because they believe in green hydrogen. Mm-hmm. Okay. So we have a very specific customer case, and to change regulations, because I always joke and say, like, well, I mean, regulations were made and nobody thought about us. Yeah, we didn't exist. So we kind of fall through like a lot of, regulatory stuff, especially on the hydrogen side. So officially we are classified as gray, right? And just to change that takes a lot of energy actually to do that. So yes, sometimes regulations can promote very positive behavior on the customer side, but I still believe that, yeah, it's necessary to some extent, but and we really need to be careful, because whatever you measure, whatever you ask for, that's the behavior you get. So we really need to make sure that this is really what we want. Otherwise, I say, like, you have to be competitive so people cannot avoid you. Yeah. That's the best thing, right?
Yeah. Okay, great. Thank you. Andrew, do we have time for one or two more questions here? Yes. Okay. Okay, sounds good. What I'd like to do is actually ask the audience if any one of you might have a question for the panel about use of recycled materials in markets. Yeah, go ahead over here. Yep. Reinhardt? Right there. Yeah, behind you.
Actually, I'd like to chime in on this discussion, do they pay a premium for a recycled product? And my experience is just the opposite. They say, look, you're taking in a gate fee. No, we're not paying the same price. We want virgin. That's the other side of the coin. It happened to me several times.
Yeah.
We're not paying a premium. So we need to get off that, how do you say? It's ideological.
Ideological. Yep, sure.
Yeah.
Yep. Okay,
So
good.
That's.
Yep.
I agree with that, yeah.
Okay. Yeah. Good point. Excellent. Other questions from the audience or comments? Okay. So then I will end off with one last question. Are there markets out there, I'll call them composite markets because that's what we're looking at, recycled material and composite markets. Are there markets out there that are untapped that do not have any composite recycled material? In this case, we're talking about recycled blades. It doesn't have to be blades, but in our case, wind turbine blades, that you think is ripe for use of recycled composite material from blades, and what would be the key to getting material to that market? Is it new technology? Is it economics? And so we're looking for untapped markets right now that you might see a value in. Go ahead, Harold. Yeah, jump in.
A recent discussion I had with my colleagues from PV, because of course within the circular economy we like to have it back in our wind turbine, but we discussed already a lot that, they don't want to do concessions for these high performance parts. But for PV installations, for floating solar, they use a lot of brackets and frames. And so I said there's quite a lot of market. They use a lot of aluminium now. But they say, now let's consider it maybe to use it as make products for the PV, the fixtures of the panels and so on.
Okay, great, excellent. Yeah, go ahead, Marcello.
Well, I think I mentioned this before. We are trying to enter to get involved more in the boating industry.
Sure. Yep.
It's not high volumes as we conceive it, but it could be high value. So coming back to the comment of Rainer before, I think that is true. But if you produce a product that is design as the design value on top of material value,
right,
then you can probably make good pricing out of the product itself.
Mm-hmm.
It has to be started, animated a little bit, but there is an intention from that sector to be more circular in general.
Okay. I like the symbology of that. Most blade manufacturers, when I started at TPI Composites in 1995, we were making all yachts, boats, sailboats. And most blade manufacturers have a history in marine. And it'd be nice to kind of come full circle there and use the blades that were built in at those companies in the marine industry and boating industry. So that'd be nice. Any other final thoughts that you want to get across from the panel? Go ahead.
I think automobiles is an industry where there is huge demand. Automobiles.
Yeah.
Yes.
Yeah.
EVs.
Yeah.
The only thing is you should deliver the product which meets their specifications, and those are very stringent specifications when it comes to tolerances.
Okay. Great.
So those are the things, but there the value is more and the demand is also good.
Okay, yeah, good point. Excellent. Anything else from the panel? Yeah, go ahead, Harold.
Now, we had discussion about fibers, to use recovered fibers into new fibers.
Mm-hmm.
And then maybe we can ask a little bit more flexibility, that we can add a new product like recycled glass fiber with the specification maybe less than the E-glass, the A-glass, or whatever. So that can be so. Maybe we can ask a little bit more flexibility also from the pool, and like Anurag said, for the automotive, we had a project with Fiat, and he said, we directly buy the fibers, but we need a material data sheet, and the data sheet doesn't have to be high performance sized long fibers. No, they say, but we need a standard and just in time delivery. So that's also in there.
Right. Great. Okay. All right. Well, thank you so much. I really appreciate your time, the panel and the audience, and then the panel with all of your experience and background and knowledge, and kind of bringing that out into helping us think about what this end use of recycled materials looks like, what the markets look like, and hopefully for a good future. And thank you so much for your time. Andrew, so I'll pass it back to you, our esteemed chairman of the thing. Thank you.
Thank you, Derek. That was, as always, a very well moderated panel. Thank you, panel. So here we are. In the last 2 days, what have we seen? We've seen that circularity isn't one technology. It's not one pathway. It's not one breakthrough. And we've seen some breakthroughs this week. It's the sum of many innovations moving in the same direction. As we bring this event to a close, let's reflect. We've seen new materials fundamentally changing what a blade can be. From recycled thermoplastics to next-generation composites. We've seen advanced recycling technologies recovering fiber, separating resins and turning end-of-life blades into valuable feedstock. We've seen reuse solutions that gives blades a second life as bridges, walkways, and civil structures. Industrial engineering and manufacturing capabilities that take ideas off the page and turn them into scalable, bankable systems. And we've seen full value chain demonstrations that connect logistics, pre-treatment, recycling, and secondary markets into a coherent circular ecosystem. This diversity is our strength. The future of wind blade circularity can never be solved with a single technology. It needs integration by alignment and collaboration. By willingness of innovators, operators, and researchers, engineers and policymakers to work together across disciplines and across borders. But what stood out most over these 2 days? It's the mindset in the room. A mindset that says, we don't need to wait for perfect solutions. We can scale what works now. We can improve what's emerging. And we can invent what is still missing. And this is how a system can be built. We've also seen the importance of industrialization, the steps that turn promising technologies into real-world infrastructure, the importance of data, policy, and market intelligence. And don't forget those colossal numbers we've seen as we approach into the 2050s and 60s. Maybe I won't be around, but we've got to head that way, haven't we? We've seen the importance of collaboration between recyclers, OEMs, and asset owners, and engineering partners. This forum has shown that the sector is no longer talking about circularity as a future ambition. We are building it, piece by piece, technology by technology, and partnership by partnership. As we look ahead to the next 30 years, a period where the world will install, repower, and retire more wind capacity than ever before. The work we've done here really matters. The conversations, the connections, the shared challenges, the honest discussions about what's working and what isn't. These are the foundations of a global circular system. So thank you. Thank you to every speaker, every participant, every question, every insight, and every challenge. Thank you for your openness, your ambition, and your willingness to collaborate. When we meet again next year, I believe we'll look back on this forum as a moment where the sector shifted from parallel efforts to a coordinated movement, from isolated innovations to integrated systems, from ambition to acceleration. Let's carry that momentum forward. Let's keep building the future of wind blade circularity together. Thank you and safe home travels. And before we go, a big hand to the organizers who have made this a tremendous event. Thank you, Teresa.
Okay, ladies and gentlemen, just few last words from me. I would like to also thank all our speakers for sharing their presentations, all our participants for asking interesting questions and keeping the discussion engaging. Lastly but not least, of course, huge thanks to our chairman, Mr. Andrew Billingsley, for his valuable input, sharing his thoughts, opening and closing remarks. If you have filled in the evaluation form, you can just hand it to me or my colleague at the registration desk. Any feedback, other thoughts for topics, suggested location, you can just drop me an email. Thank you very much. See you next year or even sooner if you find any valuable, interesting conferences. Thank you. Have a safe journey home.